Hello, everyone. I will be sharing this session and we are going to go online with a remote presentation from Cosimo Bambi. Cosimo?
Yes, can you hear me?
Yes.
And now I share the screen. And you should see my presentation.
Yes, perfect. You can start.
Okay. So, hello. My talk is about GR test with black hole X-ray data and in particular NuSTAR data. This is just to remind you that generativity has been extremely successful. It was proposed at the end of 1915 and after more than 100 years and without any modification, it is still our standard framework for the description of a gravitational field and for the structure of a space-time. The theory has been extensively tested in the so-called weak field regime with solar system experiment and radio observation of binary pulsars. In the past, say, 20 years, there have been significant effort even to test generativity on large scale, in part motivated by the problem of dark matter and dark energy. And even more recently, we can test generativity in the strong field regime. This is, say, in the past 10 years. So if you go back 10 years ago, this was not possible. But today we can test generativity with black holes and neutron star with gravitational data from LIGO and Virgo, X-ray data, and this is the subject of my talk, and even with VLBA data from the Event Horizon Telescope. However, let me say that for the moment, the test of generativity with the Event Horizon Telescope, the constraints are very weak in comparison with gravitational wave data and X-ray data. So this is the system that we want to study to test generativity with X-ray data. We have an accreting black hole. There is the accretion disk. The accretion disk is geometrically thin and optically thick. Every point on the disk is in a local thermal equilibrium. So we have these thermal photons, and the full spectrum of the disk is a multi-temperature black body spectrum. Then there is this corona, which is some hot plasma near the black hole. Thermal photon from the disk can inverse Compton scatter of free electrons in the corona. We have these Comptonized photons in blue. A part of this Comptonized photon can illuminate the disk. Here we have scattering and absorption followed by fluorescent emission, and the result is the reflection spectrum. The idea is to test generativity mainly with the reflection spectrum, but potentially even with the thermal spectrum. So, if you want to fit the data, you need a theoretical model. The theoretical model has some assumption. Then you calculate your theoretical prediction and you fit the data, and you can estimate the parameters of the system. So about this assumption, there are two main assumptions. One is the astrophysical model. You need, in any case, a model for the accretion disk, and in the case of a reflection spectrum, even some model for the corona. And then there are assumptions about fundamental physics. Here I have some list. Space-time metric, particle motion, values of fundamental constant, atomic energy levels. And eventually, you can, you have your model, you can make prediction. So in the case of standard physics, generativity, the space-time is described by the Kerr solution. Motion is geodesic motion. So if you know the metric of a space-time, you know everything about the motion of free particles. And an important ingredient is that the atomic physics is the same as in our laboratories on Earth, which I mean, it may not be true in models beyond generativity. I mean, generativity is true simply because you can always perform a coordinate transformation, and locally the law of physics are those of special relativity. But in other theories, this may not be true. Eventually, anyway, you have your model and you make a prediction. So the idea is to, try to relax some of these predictions about fundamental physics and, test if these assumptions are correct. And in the past years, we have developed these two models. RELXIL-NK is a model for the reflection spectrum. And the name RELXIL because it is an extension of the RELXIL package by Thomas Tauser and Javier Garcia. And NK because stands for non-Kerr, because the simplest version is just to test the Kerr metric. And indeed, it has the same architecture as RELXIL. There are some, we modify some part. And the other model is NKBB, which is for the thermal spectrum of thin disk, and it can be considered the counterpart of Kerr-BB. Kerr-BB is for the Kerr metric, and NKBB is for non-Kerr metric. But the code is actually very different. The structure is similar to RELXIL in the sense that we have a fits file for the transfer function and so on. So we have these two models. And about, test of fundamental physics, we can test the assumption, that a typical model have. So first of all, in generativity, the metric around the black hole should be described as the Kerr solution. So we can relax this assumption and test the Kerr hypothesis. In general, we assume geodesic motion. So, well, we can try to relax this assumption and we can test the weak equivalence principle. And we assume normally that the atomic physics is the same as in our laboratories on Earth. So if the K alpha roll line is at 6.4 keV, this is at 6.4 keV, even in the rest frame of a gas in the disk. And you relax this assumption, you can test local Lorentz invariance and local position invariance. How can we test generativity? There are basically two main strategies. One is called top-down and the other is bottom-up. Top-down is the most logical one. So you have generativity and you have some other theory of gravity. And you construct your model for generativity. You construct your model for the other theory of gravity. And you fit your data and you see if your data prefer one of these two models and can rule out the other one. Or at least, in some cases, maybe there is no difference. But first of all, there are many theories of gravity, but the main issue is that, well, you need to know the rotating black hole solution of these theories, and often this is not the case. And this is just an issue, the problem to solve the equation of extension of generativity, which typically are more complicated. So sometimes people prefer this bottom-up approach, in which you don't consider a specific modified theory of gravity, but you parameterize your ignorance with some deformation parameters. These deformation parameters are free in your model. Then you want to fit the data and see if you recover the result of generativity. So RELXIL-NK can be, and NKBB can be used for both this top-down and bottom-up approach. These are some examples of this top-down approach. So, the code is very general in the sense if you have some alternative gravity, you know the rotating black hole solution, you can test this theory. And this is what we have done in, these are some examples in this paper. Einstein-Maxwell dilaton axion gravity, asymptotically safe quantum gravity, Kaluza-Klein gravity, conformal gravity. As I said, the method is very general. And this is an example of Einstein-Maxwell dilaton axion gravity. So in this case, you have an extra parameter, which is this R2, and that is some charge of a black hole, extra charge of a black hole. In generativity, this R2 is 0. Once you have a model, but basically there is no difference. I mean, from the algorithm to fit the data, of course, does not know anything about the physics behind. This is just one more parameter. And you fit the data, and I mean, you can measure this parameter from observation. And in this case, I mean, we find that, I mean, this R2 must be less than 0.011. I mean, this is just an example, but as I said, I mean, the approach is very general, and you can apply this for, I mean, any theory in which you know the rotating black hole solution. We can also use these models for this bottom-up approach, and this is another example. I mean, in the case of a test of a Kerr metric, there are a few parametric black hole spacetime in the literature. These are just some deformation from the Kerr metric. This is an example, the Johansen metric. There are these deformation parameters for set epsilon n, alpha 1n, alpha 2n, alpha 5n. And I mean, if these are 0, you recover the Kerr metric. So if you consider, for example, one of these deformation parameter, alpha 1, 3, okay, you consider the reflection spectrum. Alpha 1, 3 is 0, you recover Kerr. If alpha 1, 3 is different from 0, you have a different prediction. So modulo some degeneracy dal parameter, you can imagine that you can fit your data and get a measurement. And the same is also true for NKBB for the thermal spectrum of a disk. This is still alpha 1, 3 of this Johansen metric. Alpha 1, 3 is 0, you recover Kerr. If you change alpha 1, 3, keeping all the other parameters of a model fixed, you change the prediction. So modulo degeneracy with other parameter, I mean, you can imagine to measure this alpha 1, 3. And this is what we have done. This is an example in this paper in which the first author is Ashutosh Tripathi. We analyze some high quality data of NuSTAR with even some Swift snapshot. And I mean, we consider this Johansen metric with this deformation parameter alpha 1, 3, and I mean, we eventually we were able to constrain this deformation parameter alpha 1, 3, and so this is GX3394. I mean, in this case, there were both strong reflection feature and a prominent thermal spectrum. So you use the combination epsilon K and KBB. In other sources, we only see a strong reflection feature. And this is the case of X1846. But eventually, I mean, this is the summary of the result of the stellar mass black hole analyzed. And this alpha 1, 3, I mean, this is, as I said, I mean, this is an example because, I mean, you can consider other deformation from Kerr. We consider this alpha 1, 3 of a Johansen metric. Alpha 1, 3 is 0, you recover Kerr. Here in green, there are the constraint. These are the measurement with the error bar, the constraint from stellar mass black hole. And these are all NuSTAR data except GRS 1915. We used Suzaku data. So this we use only epsilon K, so only analysis of reflection feature. In red, we have the same constraint from LIGO and Virgo data, so with gravitational waves, which is a completely different approach. In magenta, we have LMC-X1, which is the constraint come from the analysis of the thermal spectrum only. And well, basically, we cannot really constrain because I mean, the thermal spectrum is very simple, which is just a multi-temperature black body spectrum. So if you have only the thermal spectrum, this is, I mean, the case of LMC-X1, but basically, if you try to constrain even if you consider other data, you have the same result. So I mean, the thermal spectrum only cannot in general constrain the possible deformation from Kerr.
2 minutes.
And in blue you have some sources in which we have at the same time strong reflection feature and strong thermal spectrum. This is GRS 1716 and GX3994 are with NuSTAR data, and the GRS 1915 we have Suzaku for the reflection spectrum and RXT data for the thermal spectrum. I just say that I mean, we need to be careful to select the source because, well, if you want to measure the spin, only a small amount of data observation are suitable for measuring the spin. And in this small amount of data, just even a smaller amount are suitable for testing GR, because you need, I mean, some data in which the relativistic effect are particularly strong. I go to the next slide. This is the last slide. I just say that, I mean, the idea is to improve this model, in particular, I mean, RLK to limit the systematic uncertainty. And in principle, as I said, I mean, this approach is very general. You can test not only the Kerr metric, but even weak equivalence principle, local position invariance, local Lorentz invariance, and this is what we plan to do in the future. And I stop here. Thank you.
Any questions? Yeah, then.
Hiya, thanks for the interesting talk. So you talked about the sort of ideal setup of the inner accretion flow for measuring deviations from a Kerr black hole, needing a compact corona close to the black hole and preferably a high spin. So my question is, when you've got some observation, how confident can you be that you have those things? Or do you end up running into degeneracies between your deformation parameter and those other parameters of the system?
Yes, this is what happens. So basically, if you don't have really strong relativistic effect like a slow rotating black hole, or simply, I mean, the inner edge of the disk is not close to the black hole, or it is not illuminated well by the corona, you have a degeneracy. You have a degeneracy typically with the spin, but even with other parameters.
Okay, thanks.
There is a question on Zoom by Brian. The question is, okay, well, I don't know if you want to maybe say something else, Cosimo. I'm going to read the question. For the deformation measurements, do we have an idea of what a detectable deviation from GR would be?
Well, this depends. I mean, if you consider some specific modified theory of gravity, there may be some ideas. But otherwise, in the agnostic approach, no. I mean, there are no. I mean, you consider just some deformation parameters, and I mean, these are free parameters in your fit, and I mean, you try to your best to get the strongest constraint.
Any other questions from audience Zoom? There is a question on Slack. If your method using X-ray spectroscopy superior or complementary to LIGO measurements for some of the parameters or models?
Okay, in general, I would say it is complementary because basically, I mean, there are scenarios in which you can have you can see some deviation from generativity in the X-ray spectrum, and you don't see any deviation in gravitational spectrum, and vice versa. So, for example, you may have an alternative of gravity in which the motion is geodesic motion, and the black hole, uncharged black hole, are still described by the Kerr solution. So in this case, in the reflection spectrum, everything is like in generativity, but the field equations are different. So the gravitational wave signal may be different. On the other hand, you can also have the opposite case. So for example, you may have some different, some violation of a weak equivalence principle. So maybe some particles follow the geodesic of a space-time, and photons do not, or something like this. And in this case, or for example, you may have a variation of fundamental constant, and in this case, some interaction between the gravity and the matter sector. In this case, you can have a signal in the X-ray spectrum, and you may not have any signal in the gravitational spectrum. So it depends on the theory.
Okay, I think we can. Thanks, Cosimo, again.
All right, thank you. Thank you everyone for being here so early in the morning. I was asked to give a review talk, but I was not told on what. So that was kind of fun for me. So this is a session in accretion power. So that's what I thought in talking about. Basically, I started thinking all the cool, important results that NuSTAR has enabled in the last decade. And then I started, this is literally taken from some of my notes, and I started writing, the things that I would like to talk about. And I came up with a very long list. So obviously there's no time to cover all this. I'll cover some of these topics. If anything is left out, please don't take it personally if I don't mention your work, or it's not because it's not important, it's because there is just some time limit that we have to manage. So I'll jump directly in something that I know a little bit about, which is X-ray reflection spectroscopy. We heard about this already in this conference. And this is a technique that has been enabled quite well by NuSTAR. The basic of it is when we talk about reflection, X-ray reflection, we really talk about reprocessing of radiation in a material. In the case of this cartoon picture, what we think happens is any accreting compact object like a black hole or neutron star forms an accretion disk, and the X-rays that are produced in the central regions are reprocessed in the disk. So that component, the reflected component, carries a lot of information about the structure of that material, which is characterized by different atomic lines. And if the reflection or the reprocessing occurs very close to the compact object, it's going to be further influenced by gravitational effects. So that gives us information about the black hole itself, like how fast it's rotating. And my slides are not showing. Yeah. So by now, reflection is a very well-established technique, but it was not always the case. Is it the cable the problem? Okay. So back in the day, before NuSTAR, there was quite a bit of a discussion about whether we were seeing, not about the technique itself, but whether you were actually seeing broad iron lines, which is the hallmark characteristic of reflection. And this is because if you don't have high energy coverage, so if you were only looking back at the day with instruments like XMM and Suzaku, that give you coverage up to 8 to 10 kV, you will only see the iron line and nothing else, higher energies. So some groups propose the idea that obscuration could actually give you a profile similar to the one of a broad iron line, where it really what you're seeing is something more like a truncated disk with different clouds causing different amounts of absorption. So this was called the partial covering model. And there used to be conferences like this that the entire conference was just hearing the two groups fight about it. It was actually not so much fun until NuSTAR came. And to me, this is one of the first really nice results of NuSTAR. This is a paper by Guido Risaliti on NGC 1365, where they show in combination with XMM and NuSTAR how well you can see the signatures of reflection, in particular the Compton hump, which is produced by electron scattering in this atmosphere. So the model for partial covering wouldn't have the same prediction at high energies. And this was really put the whole debate to rest and really cemented the idea that we're seeing relativistic reflection in all these different AGNs. The importance of this technique is because it gives us access to measure the angular momentum of the black hole. What we really are sensitive is to the location of the innermost stable circular orbit, or the ISCO. So the closer the ISCO is to the black hole, the more you feel the gravitational distortion in the spectrum. And this is a function of the spin of the black hole. The faster the black hole spins, the closer is the ISCO to the black hole, ergo you see more blurring in the spectrum. Measuring the spins in supermassive black holes is a fundamental problem in astrophysics. It's very important because the distributions of spins in supermassive black holes in the local universe tell us something about how they form. If you think about supermassive black holes, they don't form by direct gravitational collapse, so they have to form through either accretion. They acquire their mass through either accretion or mergers. And how this happens, if it is via accretion, if it is mergers, how these mergers are, if they're organized, if they're chaotic, they will give you different distributions of angular momentum as a function of mass. So we want to measure this as best as we can. This is taken from a recent review by Chris Reynolds. This contains spin measurements for Cipher AGNs. This is quite annoying. Sorry. Just keeps happening. Okay.
Another port.
There's just one. All right. So this is the distribution of spins, all measured with reflection spectroscopy. There are many authors that have contributed to all these different measurements that I'm sorry I'm not listing. I just want to show a recent work by our postdoc Labani Malik, where she's measuring the low mass end of this distribution. So we're trying to do sorry.
What do we do now? Okay. So, okay, Javier is gonna continue his presentation.
Okay, let me back down a little bit.
You won't have the whole 30 minutes, you know, huh?
And this is way far. So now you see everything backwards. All right. I think I was here. We're talking about black hole spin with reflection, the great improvement of NuSTAR in measuring, even for bright sources. This is GX339 on the left, measure with RXD, which is a decommissioned mission now, with a resolution of 1 kV, 6 kV. And in the right, you see the same object now observed with NuSTAR and Swift XRT. So I'm not going to cover binaries too much because this was covered in a great presentation by Aaron Shaw yesterday. So if you have the recording, just go and look at that. Aaron actually showed this, or a version of this plot. This is the current distribution of spins for galactic black holes that we have measured with both reflection and with continuum fitting method. As you can see, there is some sort of distribution. There is a preference for a lot of the spins to be towards the upper limit, towards the maximum. Aaron actually also mentioned this. I'm showing now a comparison with the current, maybe not so current, but the O3, the first parts of the O3 campaign from LIGO, and these are the estimates for the black hole spins from the gravitational wave measurements, and it looks quite different. In general, it looks like for most of the gravitational wave sources, the spin seems to be very, very low. They don't have any preference for high spin. So there is currently a lot of discussion about what we see in X-rays and what we see in gravitational waves. So I think this shows how important it is to measure spins for a large number of sources. I'm not going to go into the details. This discussion points towards possibly looking at different populations of black holes. The masses are different. The kind of black holes are different, but it's still interesting enough. There's going to be later a talk by Paul Draghis, where I believe he's going to talk about even more measurements of for spins of galactic sources. Yesterday, Andrei Sidiarsky talked about the lamppost geometry in measuring reflection, and he pointed out something that is important, that is a very simplified model. It's kind of, I like it to make the comparison with the spherical cow. We don't believe that the coronal source of photons is just a point source, but it is a good representation in many cases. And I wanted to show a couple of cases here by Don Walton, two bright AGNs, in which we measure both the spin using the lamppost geometry. And what you see in the bottom is are the constraints to the reflection fraction. So this is just the amount of reflection that you expect to see. In this case, it was treated as a free parameter, and it's compared the blue shaded region is the theoretical prediction from the lamppost using GR ray tracing. So that in very good agreement, even for the case, for example, in the Rye, it has very extreme values of spin and very low lamppost. So it is a model, it is a spherical cow, but sometimes cows do look like spheres. I guess that's the point here. And he also showed that there are very good agreements in inclination in some of these sources as well when compared to optical interferometry measurements of the disinclination. So again, it's a powerful tool that works very great. NuSTAR has done a lot of really great work as well on measuring outflows, and in particular UFOs. These are ultra fast outflows. These are winds that you see moving at a fraction of the speed of light. If you're alive and you've been to an X-ray conference, you're probably sick of seeing the figure in the left, but it's such an emblematic representation of what can be done with NuSTAR in combination with soft energy detectors. This is the P-Cygni profile on the UFO in the source called PDS456. And on the right, I'm showing the results from Francesco Tombesi in a different source, IRAS F111119. First, discover a UFO at a quite high velocity using Suzaku data, and this was definitely confirmed by NuSTAR in a different campaign. This work was important because they were able to connect the outflow seen in X-rays with outflow scenes in the infrared. So that suggests that these wind ejections can carry on over quite long distances. There was a talk yesterday by Kigo Fukumura. He didn't talk about UFOs in AGNs. He talked more about these winds, but it still shows that connection of how well NuSTAR can do in measuring absorption properties in different X-ray sources. Another very prolific area for NuSTAR has been measuring coronal properties. This is done through measuring the slope of the X-ray continuum and the cutoff at high energies. When you see a cutoff at high energies, that's related to the temperature of a corona. If you assume that the power law emission, the non-thermal emission, is actually produced by comptonization of C photons in a hot corona. So these plots shown here on the left are very typical. What I'm showing here is from a couple of papers by Andy Fabian, where they plot the compactness parameter. This is basically a proxy for the luminosity, or this is actually luminosity over the scale of the corona, and they basically assume a corona of about 10 RGs or something like that. So what you're seeing is for different luminosities, the coronal temperature derived from measuring the high energy cutoff in X-rays. And this is something you definitely cannot do easily with any other instrument. You need imaging a hard X-rays to measure this, because you are in the regime of hundreds of keV for these temperatures. The different lines in the plots show different predictions, theoretical predictions for the per production limit, which you shouldn't see. It acts like a thermostat. You shouldn't see temperatures much larger than that limit. And what NuSTAR have been able to show for a sample of sources is that actually those limits hold very well. The spread out of the points there gives you an idea of what's the property of the plasma, because they don't perfectly align at the limit, which means that what you might be seeing is a hybrid plasma. It's a combination of thermal and non-thermal electron distributions. On the right, I'm showing results by Alessia Tortosa, where they measure, if you can measure the temperature as well as the optical depth, if you have both the cutoff and the slope of the power law. And you can derive an optical depth assuming different geometries, either a slab or a sphere. Unfortunately, the data and the statistics is not good enough to distinguish these two possibilities. It might require polarimetry detections, and I think Francesco Orsini will talk later about this. I hope I'm right on saying this. Very recently, Nikita Kambraj and others have shown what can be done with an entire sample of AGNs. There's hundreds of sources here from the BAT survey now measured with NuSTAR. You can see the population growing in the same plot of the compactness parameter versus temperature. And very recently, Alessia Tortosa also showed that for this source on the upper left, IRAS 04416 is a very hyper Eddington source. I think it's accreting at something like 400 something the Eddington rate, and it just is in the right place where you would expect it for a very high luminosity source. It's probably the lowest coronal temperature measured today with NuSTAR. So I invite you to see Alessia talk later. I believe she's going to talk more about this. A very relatively new thing for NuSTAR is looking at tidal disruption events. We heard about this yesterday from Yuhan Yao. A few years ago, Erin Kara showed with excellent data in jetted TDE. This is a TDE with a strong jet emission. What appears to be an iron line blue shifted quite a bit in energy. So the explanation was that you're seeing through this funnel, and the reflection occurs in the walls of this funnel that is outflowing at a very high speed, a fraction of the speed of light. This was interpreted or used as to discuss that the X-ray emission might actually be produced in the jet and not some other ways as had been proposed before. So Yuhan had shown very recently, this is unpublished work just in an ATIL. With NuSTAR, we can see this is a new source. The one on the right is AT2022 CMC, where with NuSTAR we can detect the power law emission all the way to almost 50 kVs, and appears to be a break at around 12 kV in the rest frame of the mission. So this could suggest that it's actually synchrotron emission from the jet, and that break will give you an idea of the minimum Lorentz factor of the electrons there. So this is still on the analysis phase. Another source that she discussed yesterday, also Yuhan Yao, is the non-jetted TDE, where NuSTAR provides a beautiful X-ray spectrum all the way to 30 kVs. And this is the source where we believe they're seeing signatures of reflection in something like could be an accretion disk or just optically thick material. So this is quite exciting. If you didn't see her talk, I invite you to go to the recordings because I believe she gave a fantastic talk yesterday reviewing all the science of TDEs. This is another very, very beautiful observational campaign for a changing look AGN 1ES 1927. This is work led by a grad student, Megan Matterson at MIT. And you see here is the light curve over about almost 4 years of this source. As I've been monitored intensively with NICER. Those are all the blue points, and the red ones are XMM plus NuSTAR. So you see very radical changes in the luminosity of this source over the time that is covered here. I think the greatest contribution of NuSTAR here is to show very strong changes in the coronal emission. You can see here 2 different spectra in blue and orange and white, which are maybe 2 to 3 years apart. And in the blue one, 2018, you see a very soft spectrum, no coronal emission. There was actually no NuSTAR detection. And a couple of years later, completely different, you see strong power law. So this is a beautiful paper I recommend to read, where everything is discussed. The soft emission is interpreted as another TDE, as a tidal disruption event in this AGN, and this is based on spectral fitting, where we see different spectral emission lines. In particular, there is a strong line around 1 kb that we were able to explain by doing some additional calculations of reflection spectra specifically tailored for this source and blue shifted. So this is another case in which this funnel that was proposed before might be taking place. You have a geometry in which you don't have a thin accretion disk anymore. You have a pop-up disk. It's outflowing at a high speed, and you have reflection on the walls of this funnel. Neutron stars were also covered in this talk, in this conference by Renee Lotlam. I stole this plot from her website, where she shows this collection of beautiful broad iron lines in many different sources. So this is another place where NuSTAR has contributed quite a bit. Even though these are typically softer spectra, what she showed yesterday in her talk is the combination of NICER and NuSTAR is providing us the opportunity to measure reflection very well in accreting neutron stars. And by modeling the properties of this reflection, we can determine then the radius of the star, and this puts very important constraints on the equation of a state. So this is, I'm not going to go into more details than this. I, again, invite you to see Renee's talk if you can, where all the details are covered. I just wanted to mention, we produce models specifically tailored for neutron stars. But the change is very simple. You change from power illumination to a black body illumination. But I just wanted to signal that even though this is a black body emission and it's soft, most of the changes happen at the NuSTAR band. So you do need that imaging hard energies to understand what's going on. With these models, there was an interest in development. Riley Corners mentioned this very briefly in his talk yesterday. We see signatures of what we believe is returning radiation. These are thermal photons that are light bent due to strong gravity, go back to the disk and produce reflection again. And the reflection follows more of the thermal emission of the disk, not a power law. So we use these neutron star models that we created to fit black hole binaries that show this sort of tendency. This is an effect that has been predicted many, many years ago, but it's the first time we have an evidence for this. This was done actually with RXT data. But now with NuSTAR, we have further evidence that it is a plausible effect that we see in data, particularly in the softest state where the thermal emission is very intense and bright. I listed here a few other sources where this effect has been claimed to be seen. And there's also a lot of theoretical development currently happening. Dan Wilkins will talk later about possibly about this and other effects near black holes. And Thomas Hauser has just posted a paper where the effects of returning radiation are included in our model, in the RELSIL model, to at the level of how it changes the illumination profile in the disk. So there's a new version of RELSIL 2.0 that you can download now and have fun with. Spectral timing is, I believe, is a new frontier in X-rays. It's been around for quite a while, but now we have new detectors like NiSTAR that produce lots of amazing data. Reverberation, in particular, for binaries is fairly recent because of the high frequencies involved in this. So it's been shown for a few sources now. Jing Won talked yesterday about this. Our chair of the session, Gulo Mastroserio and Adam Ingram, have created a beautiful model called RELTRANS that is capable not only to do relativistic reflection for the flux spectra, but simultaneously produces all the timing properties like lag versus frequency, lag versus energy, and you can fit everything simultaneously. One of the cool things you can do with models like this is that now you have the possibility to fit for the black hole mass as well as the spin, if you have data for all these different regimes. Gulo will talk more about this, and there was a talk by Ed Nathan yesterday as well, applying this model. I'll skip over this. NuSTAR can also do really good timing. The only problem is because of the low orbit, there are gaps in the data. But in a very recent paper just submitted by Colin Lewin, a student, he shows that you can use modern machine learning Gaussian processes to basically fill the gaps, and therefore that allows you to apply all these Fourier techniques that are so powerful. And he does that in both NuSTAR XMN, fitting timing and flux spectra all together using the RELTRANS model, and produces a very good fit of different frequency regimes for the lag spectra, and he can determine the black hole mass for this source as well. Very recent now and future developments for reflection is including polarization in the reflection component. We're working currently on this very hard because we already have a flying mission called IXPE that is measuring polarization. And I wanted to show with all of you a very exciting new result from a campaign that ended a week ago or so on Signal X1. This is still technically under embargo. They told me that you're cool people and I can show it to you, but please don't do photography of this. What I'm showing here is the measurements of polarization for Signal X1 in the 2 to 8 kV energy range, which is the one covered by IXPE. We measure around 4 degrees of polarization in this band with a very high significance, over 20 sigma. And I don't know if you can see that it's actually a trend of a slow increase of polarization with energy, which is quite interesting. This amount of polarization is unexpected for the source. It's a very complicated discussion that I don't have time to get into it, but basically all the current models that we have will require a larger inclination for the accretion disk than the inclination of the orbit. So that's quite interesting. The polarization angle actually aligns very well with the jet, which I found very beautiful. So this is a paper that was just submitted to Science. The lead author is Henry Kruszinski. So it should be posted in the archive very soon. I will just quickly give you takeaway messages. NuSTAR is obviously a super important mission to do accreting sources in the universe. I believe is probably the most efficient one in terms of money per science per dollar, sorry, if you compare to almost any other mission. And I invite you to close your eyes and imagine a world where NuSTAR doesn't exist. If that word scares you, then I'll ask you to please come to the last session on this conference where we're going to talk about HMXB, which is our proposal for a successor mission for NuSTAR. So I'll stop here and take questions. Thank you.
Yes. Yeah, one question from the audience, Fiona.
So is it easy to explain why 4% is surprising? I mean, is there a simple...
Sorry, can you say that again?
Why the 4% polarization is surprising? Is there a simple explanation for why it should be less?
Because the known orbital inclination for SIG-X1 is like 27 degrees. So at that inclination is very hard to produce that amount of polarization almost with any construction. So that's why everything points out, well, if we allow the inclination to be substantially larger, more in the ballpark of 40 to 50 degrees, then it's easier to for almost any model to make that amount of polarization.
So you mentioned that AGN, that changing look AGN that had like the corona disappear and how it's like been said to be the result of a tidal disruption event. But there's also been a few recent papers on it saying that it's a magnetic flux inversion event. Do you have an opinion on that? I
don't. I know exactly what you're, well, not exactly. I know what you're talking about. I think the group in Colorado and Gila, Mitch Biegelman and Jason Dexter and these guys, they wrote papers about flux inversion. It seems to me like you can go both ways. I don't think that, as far as I understand, I don't think there are strong indications of one model winning over the other, but it's not my area of expertise. So yeah, thanks.
So there's one question on Slack and one question on Zoom. Claudio Ricci raised his hand, so I think you can speak up, Claudio.
Yeah, just a comment on the last question on 1ES 1927. We are about to publish a few additional papers on this object, and what we are seeing is that the H alpha and H beta are definitely not virialized, and their motion is consistent with an elliptical orbit. And I think this is a strong indication that actually this was a TD rather than, because like with the magnetic flux inversion explanation, you cannot really explain any motion and weirdness of the BLR.
Great. Oh, thank you. I wasn't aware of that.
I will conclude with Daniel Stern question on Slack regarding the XP Sinus X1 result. Tomsik also noted a misalignment between the orbit and the disk inclination back in 2014 from an early NuSTAR paper.
Yeah, that's very true. I just didn't have the time to go over details, but
I didn't say the question.
Oh, sorry.
Is the XP result surprising given that result?
No, it's not surprising. So when we measure reflection for Cygnus X1, typically we find that the inclination is larger than the orbit as well. It's hard to make any of the reflection models to work with the orbital inclination. So it works in our favor in that way. But it's a longer discussion than yeah.
Yeah, maybe you can continue it on Slack. Well, let's thank Javier again.
Thank you.
Just Gotthelf and Monacontin, I don't have your posters. Please get those to me. That session is in 40 minutes. Thank you.
So next speaker is Dan Wilkins. See if we are luckier this time.
It should be on Zoom. There we go.
Yeah.
Excellent.
Floor is yours.
Okay, well, thank you, everyone. It's a great pleasure to be here today and celebrating 10 years of NuSTAR. And I thought today I would talk a little bit about some of the work we've been doing with AGN with NuSTAR. In particular, looking at AGN that emit bright X-ray flares and using those flares to learn something about general relativity, the environment just outside the event horizon of those black holes, and about the corona. So thanks to Javier for setting me up here. I can probably go fairly quickly through my introduction. I was just going to go over how we can use X-ray reflection and reverberation measurements to measure the extreme environment outside of the event horizons and to understand more about the X-ray emitting corona. And then I'm going to talk about a couple of results we've had from X-ray flares that we've been fortunate to observe with NuSTAR that have actually let us observe the effects of strong gravity and light bending in action around the black hole, and also learn something about the processes that are happening in the corona to produce the X-ray emission that we see. So the basic picture we've got here is we've got this corona above the accretion disk around a black hole. We're seeing the X-ray emission from that corona, but some fraction of that X-ray emission is shining down onto the accretion disk where it's being reprocessed, producing the reflection spectrum that we see. But we really don't know a lot about the corona. The idea is that it's some population of energetic particles close to the black hole that's Compton scattering seed photons from the accretion disk up to X-ray energies. But exactly how those particles in the corona are heated and accelerated is one of the big mysteries in accretion physics. We think the corona's got something to do with magnetic field lines that are getting tied up by the orbit of the accretion disk and by the spin of the black hole. But we don't know how the corona is connected to the jet. We don't know if the corona is the base of the jet, or if in the AGN that we're seeing the strongest reflection signatures are actually radio quiet AGN without big jets. So maybe the corona is something that happens when you fail to launch a jet and all that energy is getting dissipated close to the black hole. So we'd really like to be able to learn more about the corona to try and answer some of those questions about its formation. Now, NuSTAR is ideal for observing the reflection from the inner accretion disk and using that reflection to map out the inner accretion flow and the corona. And I thought just for fun here, what I've done is I've taken all of the Seifert type AGN that were observed with NuSTAR in which we've seen an ion K reverberation time lag, and I've stacked all of their spectra together. And you can see that NuSTAR really does a fantastic job of picking out that broad ion K line, a narrow ion K line, that's reflection from material further from the black hole. We're seeing absorption signatures coming in there, whether that's from warm absorbers or if that's from ultra-fast outflows closer to the black hole. And we're getting that fantastic view of the Compton hump. And if we see that broad ion line and that Compton hump together, it gives us a really good handle on that reflection spectrum to separate it out from the other emission components that we're seeing. And that reduces a lot of our uncertainties and a lot of our degeneracies in the modeling. And X-ray reverberation is caused by that reflection spectrum responding to variations in the luminosity of the corona. When there are variations in luminosity, we can measure the average time at which different X-ray energies respond. And we see, just due to the additional light travel time between those rays that come straight to us from the corona and those that reflect off the disk, we see that the ion K line and the low energy X-ray reflection, so this is the X-ray reflection contribution to the soft excess, respond later relative to those energy bands that are dominated by the continuums coming straight from the corona. And we can interpret this time lag, this reverberation time delay in terms of the height of the corona above the accretion disk. And this is kind of my sales pitch about X-ray reflection and reverberation. The ion K line that we're seeing is the integral over the entire surface of the accretion disk. We've got different Doppler shifts and different gravitational redshifts on different parts of the disk. The ion line that we see is made up of all of those different energy shifts. And if we can measure the profile of the ion line, we can start to understand how much reflection we're seeing from different radii on the disk. We can then use that measurement to work backwards and tell us where the location of the corona and the geometry of the corona has to be in order to illuminate the accretion disk in such a way that it produces the distribution of reflection that we're seeing from the shape of the ion line. So the energy shifts of those line photons are a function of the position on the disk. And then if we can measure the reverberation time delay at each of those different energy shifts, we can then work out how far each of those bits of the disk is away from the part of the corona that is illuminating it. And by putting all of that information together, we can start to build up a three-dimensional picture of the inner regions of the accretion disk and where the corona is sitting around there. Now, one of the real reasons we're interested in X-ray flares, if we're getting a short, bright burst of emission coming from the corona, we're going to see the emission from the corona, and then we're going to see the response from the accretion disk to that isolated event. And what we're going to see is at different times, the reflection from those different parts of the disk. We can see those reflections are coming from different parts of the disk because the INK photons that we're seeing are shifted to different energies. And we're going to see those responses at different times, just according to the light travel time from the corona to each patch of the disk, and then from each patch of the disk up to NuSTAR, or whatever your favorite X-ray observatory is. We won't mention the other ones here. Another measurement we can actually make to better understand the corona is actually quite a simple parameter that we call the reflection fraction. This is simply the ratio of the total amount of flux we observe coming to us directly from the corona and the total amount of flux that we observe coming reflected to us from the surface of the accretion disk. If we have an isotropically emitting point source corona above an infinite disk in a flat space-time, no GR, no gravity, we expect exactly 50% of that emission to go up to us, to be seen as the continuum, and we see 50% of that emission to shine down on the disk. So that reflection fraction should be approximately unity. Strong light bending in the vicinity of the black hole focuses more of those photons onto the inner parts of the accretion disk. Fewer of them are able to escape directly to our telescope. So that means where we have strong light bending from a compact corona close to a black hole, we see reflection fractions enhanced above unity. Now, the final case is if we measure a reflection fraction less than 1, assuming we've accounted for other things that can make it look like our reflection's less. So we've taken account of the absorption, we've taken account of the ionization of the accretion disk. We think we're counting all of the reflected flux across the entire bandpass. Reflection fractions less than 1 could be telling us that we have a corona that is moving at a mildly relativistic velocity upwards, away from the accretion disk. In this case, we get relativistic Doppler beaming of that emission, pushing it away from the disk, away from the black hole. So more of that emission comes straight to us, less of it gets reflected from the disk. So reflection fractions significantly less than unity can tell us that we have relativistic motion of that corona away from the disk. Now, our story with observing AGN flares with NuSTAR really got going in about 2014. Right at the end of 2014, our swift monitoring of Markarian 335, which had been in this long, low flux state, saw that it launched for a period of about 30 days, this bright X-ray flare. And we were given a target of opportunity observation with NuSTAR to really follow up in detail what was happening here. And we found, almost quite surprisingly, that this flare corresponded to the corona being gathered up and ejected away from the accretion disk before the corona collapsed back down at the end of the flare as that launching event sort of failed and the corona collapsed again. But today I'm going to be focusing mostly on a galaxy called Wandswicki-1 that we've devoted a lot of observation time to recently. This is Wandswicki-1 as seen in the Pan-STARRS survey. You can see it's a fairly typical Seyfert type 1 Seyfert galaxy here. You can see the spiral galaxy with the bright AGN in the nucleus. But Wandswicki-1 is a great source for studying reflection and reverberation from the accretion disk because its X-ray emission is incredibly variable. It shows extreme variability. It changes between high and low flux states, and it emits bright flares. The NuSTAR spectrum of Wandswicki-1 shows us this nice, clear reflection spectrum. We can see that broad iron K line and that Compton hump that give us a really good handle of that reflection component. And using XMM Newton, we can measure the reverberation time delay across the soft X-ray band. And measuring the time delay between the continuum and the peak of the broad iron line is completely consistent, given the spectral model that we have and that we can measure with NuSTAR. Inputting that spectral model into our reverberation model tells us that this reverberation time lag is consistent with a compact corona that's at a height of about 4 gravitational radii above the accretion disk. But we had a joint observing campaign with NuSTAR and XMM right at the beginning of 2020, caught these 2 bright X-ray flares launched from 1 Zwicky 1. And this immediately caught our eye when we saw this in the data. Short, bright flares, almost ideal for looking for the reverberation signature in response to them. So what I show here is taking those two flare profiles and stacking them on top of each other, and then looking at the light curve in different energy bands. The 1 to 3 keV band, which is dominated by the continuum, the 3 to 5 keV band, which are the redshifted ion K line photons from the inner parts of the disk, 5 to 7 keV, which is the core of the ion K line around the rest frame energy, and 6 to 8 keV, which are the blue shifted ion K photons. We see the profile of the flare in each of these, but we also see rapid variability superimposed on top of that. The red line shows that just some of this variation is simultaneous between the energy bands, and that's easily explained by just rapid variability in the broadband continuum. But we also see, if we assume that these light curves in all the energy bands should be the same shape, so we take the 1 to 3 keV continuum band, and we use that as a model, and we realize that in the other energy bands, we see these residuals indicated by the blue lines. These are detected above random red noise variability to about 99.99% significance, but they appear at different times in those different energy bands. So these are not just rapid variations in the continuum that should happen simultaneously across the energy bands. In the interest of time today, I'll cut straight to the punchline, but it turns out that these peaks are exactly predicted by the GR ray tracing model we constructed of X-ray reverberation from that compact point source at 4Rg above the black hole that we inferred from the NuSTAR spectrum and from the time lag. So we can build this model that tells us after this flare, we should see photons, these number of photons appearing at different energies as a function of time. And what these narrow peaks are in these light curves, these echoes of the flare as the flare decays, are what we call the re-emergence. This is the fraction of the reflection that's coming from the portion of the accretion disk that should classically be hidden behind the black hole. We shouldn't be able to see this part of the reflection, but the light bending around the black hole bends these photons into our line of sight, so we can see them. However, they're delayed as they travel through the gravitational field. But the reason these appear as such sharp, narrow peaks is that gravitational lensing is actually magnifying that emission from behind the black hole. And we can actually fit this model to the light curves. And we find that this model exactly predicts the timing of these peaks. This model has a few different parameters, the mass of the black hole and the height of the corona. And we find that the mass of the black hole and the height of the corona agree completely with these peaks with the measurements that we can make using other methods. The catch of this model, though, is that it requires that the disk is only responding to the first part of the flare. The end part of the flare we're not seeing in this reverberation signal. So what exactly happened to the corona to cause this flare? Well, we can measure the changes in the NuSTAR spectrum. We can apply our reflection and reverberation model to the spectrum that we measure at different times. I should also say that this was simultaneous between the NuSTAR and the XMM spectrum to get the broadband coverage here. And we find that a few of the key parameters that describe the corona, we can actually measure changing between the periods before, during, and after the flares. We see the photon index change. The X-ray spectrum is softening during the flares and then hardening afterwards. And then using NuSTAR to measure the high energy cutoff of the spectrum, we actually see that not only does the spectrum soften during the flares, we can directly attribute that to a drop in the temperature of the corona during the flares. At about 2.7 sigma confidence, we're measuring a drop of the temperature of the corona from 120 keV to around 40 keV during the flares. The reflection fraction drops significantly, showing that the corona is being accelerated away from the accretion disk during the flares. And we're also finding some very tentative evidence from the shape of the ion line that the corona is expanding during the flares, but then it's contracting again to a compact corona around the black hole after the flares subside. But just a quick comment on the timescale of these flares. So I said that in order to see those sharp echoes in the light curves that we attribute to the emission from hidden behind the black hole, we require that the corona is only producing a strong reflection during the first 2000 seconds of the flare. But this is actually consistent with the corona accelerating away from the disk. Because when the coronal velocity is low, close to the black hole, we get a lot of reflection from the disk. But as the corona accelerates, that emission gets beamed away. That is decoupling the corona from the reflection signature. So we're not seeing the reflection and the reverberation in response to the later part of the flare once the corona has been accelerated. Now, my last comment on the timescale here is that this 2000 seconds that we say the corona needs to accelerate in is the light travel time from the inner edge of the accretion disk around the black hole to something around a height of 4 Rg. So this means that whatever's causing this flare must be propagating at the speed of light. This can't be a flare caused by viscous changes in the accretion disk. This needs to be something propagating at the speed of light. And if you have a force-free magnetosphere, so a low-density environment, say in the corona, the speed of light and the Alfvén speed are approximately the same. So that's hinting that these flares really must be magnetically generated around the black hole, not by the fluid in the accretion disk. So we're getting this picture that during the flares, the corona is being launched away from the accretion disk. In WANSWIKI 1 in 2020, we actually saw for the first time that the corona cools as it gets launched away, but then it contracts down, it collapses down to this compact corona, going back into a low state after the flare. So just to summarize, X-ray reflection and reverberation are let us probing what's happening right down to the scale of the innermost stable orbit and mapping out the inner disk and the corona. We're starting to see general relativity in action around the event horizon. We're seeing strong gravitational lensing, and we're seeing the re-emergence of X-ray echoes from behind the black hole. And the reflection spectrum is showing that the corona is cooling as it's accelerated away from the disk during X-ray flares. And NuSTAR and hopefully HEXP will be the ideal tools for observing the physics that's happening right outside the event horizons of the black holes. And just before I finish, I thought I'd share one of my favorite press clippings. When you talk about things shooting away from black holes, of course, the press starts to get interested. This is from one of Britain's finest tabloids. Let's not read too much into the radioactive light in the headline, but I think one of the crowning achievements of one of our NuSTAR observing campaigns is that we elicited this survey to the readers of Britain's Daily Mirror. Are you scared of black holes? So I'll let you decide for yourselves, but I'll stop there and take questions. Thank you.
Yeah.
Great talk as always, Dan. It just occurred to me, all these coronal changes, we sort of see something similar in MAXIJ 1820. And I was wondering if you have thought about it and if this sort of a scenario will work equally well there.
Yeah, and actually, I'd like to refer here to Jingyi Wang's paper that she published on the archive just a couple of weeks ago, showing that during the state transitions and she talked about this yesterday, in MAXIJ 1820 and in the other X-ray binaries in NISA, we're seeing this picture in the state transition where the corona's getting, looks like it's expanding upwards away from the black hole. And in the binaries as well, that tends to coincide with the ejection of knots in the radio jet. So yeah, I think there's a lot of overlap in the physics here. I think if we can do more to understand what's happening to magnetic fields getting tied up around black holes, how they're powering the corona, and how that translates between the supermassive and the stellar mass ends. Yeah, there's certainly a lot of physics in common here. Thanks.
Yeah, we are a little bit late, so I encourage you to continue the discussion on Slack. There is a question popping up already, so well, Dan can answer on Slack. I think we can go to the next speaker. Yeah, and thanks again. So next speaker is Deborah Lankova, maybe. Yeah, go ahead, Deborah.
Okay. So hello, everyone. Thank you for having me at the conference. I'm very happy to, okay, maybe take this off. So I'm very happy to see people in person again. So my name is Deborah Lancha. I'm a PhD student in the Institute of Physics in Opava University in Czech Republic. And I would like to present our project with this quite extension collaboration about the numerical model of accretion sub-Eddington disk. So for many years, there was a problem with analytical models of accretion when in the sub-Eddington regime, there are basically two models which we can use. One of them is a slim disk, which works well for above the Eddington limit. Then there's a Shakura-Sunyaev or Novikov-Thorne. There's just a thin disk model, which works well for mass accretion rate or luminosities quite low. But in between them, there is a regime where the accretion disk is not stable. There are viscous and thermal instabilities, and there were many attempts to solve that, but it was also shown in simulations that this regime is actually not stable, and we don't know what is happening in there. Also, the observation doesn't work very well in this regime. So, for example, this is this nice work by Hornstrup, 2011, when they took these two models, CatBB and Slim BB, to fit LMCX3 in outburst. So they had a observation for this different luminosities, and they fitted with these two models. And when the slim disk model was actually at the beginning motivated by solving this problem, but you can see that for different luminosities, the spin obtained from the fits is actually decreasing. So we are not expecting that the black hole is slowing down that fast. It's just something wrong with the model. And there's something wrong with both of the models. So slim disk is not the solution. So Marek Abramovich, who was one of the authors of the slim disk model and one of the co-authors of this paper, was looking for some other way how to look into this accretion regime, and they decided to try the numerical approach. So what we are doing a global GRMHD simulation of accretion of this regime. Basically, for you who don't know, MHD is solving a flux of conserved quantities and plus some source on a numerical grid, which is logarithmic in our case, because we have to cover the equatorial plane of the plane of the accretion very well. So, and because radiation is super important in this regime. Basically, we are talking about regime when a gas pressure is lower than the radiation pressure. We need to include the interaction with radiation in our simulation. So we are using radiative GRMHD when the conservation of stress energies of the fluid is coupled with the conservation of stress energy tensor of the radiation. And they are exchanging energy and momentum through this radiation 4-force density. And we are using M1 closure to obtain the whole radiation tensor. Basically, we are saying that there exists a frame in which the radiation is isotropic, and then we can get the whole tensor in this frame. So this is the method. We are using a code which is called Coral. It was written by Oleg Sondowski. There are many papers about the results for both optically thin, very low mass accretion rate, accretion about stellar mass or supermassive black holes, also for optically thick and high mass accretion rate simulation. The code is robustly parallelized with MPI, but still we need millions of car hours of supercomputer to run the simulation. Actually, it's very, very huge work to do. So we got several grants on a Polish supercomputer PL Grid, where we are running our simulation. So because we want to see how the accretion is behaving in a, and we don't want to be looking at something which starts from an analytical model, which we know is not stable. We are starting from just a source of matter quite far away from the black hole, and we are looking how the matter is falling on the black hole and what is happening in this innermost parts of our domain. So the whole disk, the whole all the results I will be showing you are based on only this small part of our huge domain. But since we are using logarithmic grid, half of the resolution is actually hidden in this domain. So it's very well resolved. So in order to have a long enough simulations to see how it behaves, we need actually a stable solution. And it was a problem because, as I was saying, this regime is unstable. It was shown by several papers for several simulations, but there was one work by Oleg Sondowski, author of the code, who showed that if you use a quadrupole topology of the magnetic field, you will actually get a stable solution in this innermost part. In his paper from 2016, that's it. He actually tested several topologies and how stable the solution will be, and came up with this quadrupole as the best and only stable. So our inner edge of this source of matter is at 40 M, so we are looking on the lower radii. We have non-spinning stellar mass black hole. So, and if we run the simulation for quite a long time to enable the matter to actually fall on the black hole, we will end up with this kind of solution, with this. This is a snapshot from the simulation. You can see that the magnetic field and the plasma is very turbulent. And we actually run the simulations for a very long time, averaged over this very long time, and look into the results. So the disk is turbulent. There's a lot of accretion of radiation. We can see how this is the radiation flux. This is the density in the midplane of the disk. This is equatorial plane. And you can see this dashed line is density scale high. So we actually got a thin disk. Okay. But this solid line is the photosphere. So for distant observer, this will be the observable surface of the disk, and we won't see what is happening inside at all. This is logarithmic scale of density, so we see that inside the density is very, very high. Here in this region it's lower, but still it's optically thick. So because the disk is not like any other analytical model we know, we decided to give it a nice name, and because it's not thin, it's puffed up, we call it the puffy disk. Puffy disk has this dense core, which resembles a lot a standard thin disk in a many way. But then it has this puffy region, and actually most of the mass transfer is happening in this puffy region. It has a funnel in which we have a strong outflow, and on the right side, you can see a optical depth. So this is the observable surface, but you see that the disk itself is very optically thick. And this is the contrast of temperature, so it's quite hot. So after we run this simulation, we, together with Ramesh Narayan, used his code Heroic to do a full radiative transfer of our results. So we can see how would the disk would look for a distant observer. And since we are still trying to compare it with a analytical thin disk, we see a lot of differences. So, for example, since the observable surface is very, very thick, if looking at the disk from the axis, we see nicely the innermost region. This is free mass accretion rate. We have 1.5, 0.9, and 0.6. This is the same pictures for a thin disk with mass accretion rate 0.6 for comparison with this. So we can compare these two columns. So looking from axis, it looks quite similar, but if we are going more towards the equator, we can't see almost nothing from the equator, but from a thin disk we can still see actually even the black hole shadow in the middle. And this will have a huge influence on the observable signal. So if we look at the spectral energy distribution, it's going down. The energy peak is going down very fast with the inclination. It's not moving at all, like where the energy peak is, but it's much lower luminosity. We have also this nice Compton hump in the spectra, going quite high energies. And we see that much more important than the mass accretion rate is actually the inclination, because these three curves are for three different mass accretion rates, but these three colors are for three different inclinations. Also, we can see a very strong beaming, since, you know, if the radiation is reflected from the funnel wall and it's going more towards the observer from the axis. So if we compare a thin disk for the same mass accretion rate and a puffy disk for the three mass accretion rates we have, for example, for 0.6, a thin disk would still look sub-Eddington close to the axis, but puffy disk was almost to Eddington. So we have a beaming factor of 0.25 to 0.3 approximately. And this is not changing that much. The beaming factor is not changing that much with mass accretion rate again, but more with the inclination. So when we had this spectra, we would like to try to fit it with existing models, with the one which was, for example, used to fit the MSCX3 I was talking at the beginning. So we simulated the observation of puffy disk and fitting it with the two models, SlimBH and KERBB, plus thermal Comptonization. And we got actually not that bad fit. But the problem is that the parameters was completely wrong from our simulations. For two different inclinations, in both cases, we got high spin, especially in the 10 degree. This was a zero spin simulation, so that it overestimated the spin value a lot. We got actually a higher luminosity for high inclination, for a low inclination, and lower luminosity for high inclination, which is not that surprising, taking into account the obscuration. And overall, the fit is not that, doesn't look that bad, but still, it's very, very far away from what we were actually simulating. Also, the hardness luminosity development with the inclination is behaving completely different than what we are used to with slim or thin disk models. And also, which is something which is still kind of puzzling us, but we think is a connection to the disk temperature, is that these three lines are not the same as are not growing, the hardness is not growing with the mass accretion rate, rather that the 1.5 is in the middle. But it is much more luminous, and it's still it's probably connected with the disk temperature. So when the disk is sub-Eddington and has lower mass accretion rate, it's more compact and the temperature is higher. Okay, so it wouldn't be a MHD talk without a fancy video of turbulent plasma. So here is one. I was trying to more focus on the observational properties and the consequences for the observation, and that maybe the standard analytical models, if we use them to fit like complex simulation, are not working very well. We have some guess that this simulation can correspond to some intermediate state for microquasars. and or the ultra luminous state of ULXs. But we would like to do more simulations with more spin, more values of spin for more masses, because since it's radiative, MHD is not scalable with mass anymore. So, and also to compare it with a real observation, but for that we would really need to run a whole new simulations to use a few million core hours to actually have something we can compare with. So thank you for attention. And at the end, I would like to advertise a conference we are organizing in Prague in September. The abstract submission deadline is close, and it would be great if we can see some of you in Prague. Thank you.
Yeah.
So if you go back to that set of figures where it's like you're comparing the observations of the puffy disk to the thin disk, why is it that you can't see the puffy disk edge on?
This is because of the here. So it's because of the photosphere. If you are looking from here, you wouldn't see anything because photosphere is here. So only when you're looking like above the photosphere, even in this, for these angles, you can see only the reflection of the funnel wall, not the very like middle with the black hole inside. So if you're going from, if you are looking from the like equatorial plane, the whole view of the innermost part will be obscured. This is not like that there is nothing in this picture. It's not black. It's just showing the same flux for all four inclinations. And there is actually some signal from it. You can see that we have a spectra for high inclination, but in comparison with the low inclination, it is nothing. It's not comparable.
Okay.
Hi, great talk. Thank you. So I guess building on that, so we can see that the puffy disk looks very different from the analytical thin disk model. Have you compared it at all with what you'd expect to see from a kind of super Eddington slim disk model?
How do I compare it with a slim disk model?
Yeah, observationally, have you?
So we use the slim BH model to do the comparison. Actually, for a sub-Eddington, the slim BB and Kerr BB is almost the same. It's not that different, but we are trying here comparing to a thin disk rather because it's like the well-known picture of it. The problem of a slim disk is that it is not that easy to say what's the vertical structure of it. So you can actually have a slim disk which is quite thick, depending on other parameters. But here the comparison with a thin disk is like what we are most used to from a sub-Eddington accretion.
Thank you.
And yeah, right. Quick one, if it's possible.
You hesitated, so I figured that I have time. So obviously, it's a bit of an issue that when you fit with these more standard models, you recover a different spin. But are you saying also that you cannot fit your simulation, sorry, with a zero spin?
No,
model?
we can't. The fit was very, very bad.
Okay.
Because you can see it here. So here you see that the innermost part, where the disk is truncated, is super small in comparison with a standard thin disk. Also, the temperature is much higher. So our disk has actually nothing significant on its scope. We were trying to find anything, but no, there's nothing. It just goes all the way to the horizon.
Okay, thanks.
Well, we can move on. We can thank Deborah again. And we have the last talk of the session is a remote talk from Kohei Ichikawa.
Yes. Can you hear me?
Yes, we can. And we can see your slides.
Can you still see my slides?
Yes, go ahead.
Can I start or should I wait? Hello?
Yeah, we can hear you and see your slide, Koi.
Okay, so hello everyone. I'm Kohei Ichikawa. I'm a Frisk Fellow at Tohoku University in Japan. So today I would like to introduce one interesting population of AGN, a kind of dying AGNs, which has been discovered in one galaxy of 187. And I would like to introduce how NuSTAR helps to discover such interesting populations. And actually, we are now conducting a kind of more follow-up observations of such dying or fading agent candidates. And then the NuSTAR will probably give us more fading agent candidates. So if you are interested in our recent studies, please check those 3 papers. And actually, Zhao and Chen is attending in person there, and then he will give a poster talk tomorrow. So I don't have to start here, but probably, this is AGN talk, and the AGN is, I don't have to say, but it's a Accreting event to the supermass black holes, whose mass is 10 to the 6 to the 10th times the mass of the sun, which is very huge. And then AGN is really important populations to understand the growth of the supermass black holes, because the AGN is actually the black hole is increasing their mass. One beauty point for observing AGN is that they're really bright in multi wavelengths from radio to up to a hard X-ray band, including a NuSTAR. This is one image of the AGN in a radio band. If you look at the AGN in a radio band, we see 2 important features. One is obviously this beautiful radio jet, and then the other is a radio core, which should be associated to the close to the accretion disk, and then related to the synchrotron or free emissions. So such kind of beautiful image can be seen once AGN is ignited, once the gas falls into the center. But the question today is that if there is a starting point, there should have an ending point. So can we find the final phase or the dying phase of the AGN? So the answer is, should exist, but finding them are quite difficult. So the reason is that AGN phase should be really long, should be longer than the 10 to the 5 years, even a one AGN life cycle. So the Saskatchewan dying phase should be also very hard. But today I'd like to report such a discovery of the dying AGN serendipitously. That galaxy is in UP127. So one day we observed UP127 in Arma band, and we found a very beautiful bimodal jet, which is a hallmark sign of the radio AGN. But UP127 shows interesting signature that there is no clear radio core, even by observing very deep ALMA and Gray observations. This means that radio core seems quite faint. So in other words, accretion current AGN activity should be already really faint. So in order to check this point much more, we obtain multi-wavelength data of these galaxies, because if you look at the different AGN component, which has a different physical scale, and then this might give us a past AGN activity. So first, we check narrow line regions of AGN. This is a kind of typical narrow line region of AGN. AGN is really bright, and then ionize the surrounding area, and then that area expands over 1 kiloparsec level. And then this narrow region can be easily traced by oxygen 3 emission in optical spectra, and then UP127 definitely shows really strong emissions. The expected AGN luminosity from the O3 reached to actually the 10 to the 46 parsec, which is a quasar level, or the limit luminosity of the 10 to the 8 solar mass black holes, so which is really bright. On the other hand, if we look at the mid-infrared band, mid-infrared is a good tracer of the AGN dusty torus activity, whose size is less than 10 parsec scale. Luckily, we had a Spitzer IRS spectra, and then this is a spectra as shown in gray solid lines. Actually, this is well described by the host galaxy emissions alone. And then we don't have to see any dust torus emissions. Actually, the expected dust torus emissions from the oxygen 3 should be located here. So that I naively expected that the spectra should be dominated by the agent torus emissions, but actually we don't see any dusty torus emission for them. This gives quite strong upper bounds of the less than 10 to the 44, which is already 2 orders of magnitude fainter than the value expected from the narrow regions. So finally, we wanted to check much more on the current agent activity. Definitely, X-ray is the best tracer to check as a current agent. And then, especially the NuSTAR is the best because there's still the possibility if the central engine is highly obscure, this otherwise seemingly the central engine might be faint. But the NuSTAR covers energy band higher than 10 kb, so we don't have to worry so much, even the central engine is constant thick level of absorptions. So after the 80 kilosec observation by NuSTAR, the result is like this. And then we don't see any emissions from R27. So this is a spectra, as you can see, the spectra is quite background dominated. So even by using deep NuSTAR observations, we don't see any agent emission from them. So this gives a most strong upper bound of the current agent activity, which is less than 10 to the 42.5. So this is a roughly at least 3 orders of magnitude fainter than the value expected from the narrow regions. So what is happening to R27? So generally, if we observe AGN, they are bright in the nucleus. That is the definition of AGN. And as well as such nuclear emissions, we always see extended ionized gas regions radiated by the AGN central engines. So that we see both of the compact and the large scale component of AGN ubiquitously for most of the AGN. But that is not for R27. We don't see any nuclear emission from them. So that looks like the central engine is already quenched. But we still see a very bright narrow region emissions. So that probably this AGN died very recently, less than the light crossing time of the narrow region, which should be around the order of 1,000 years. So, so we probably R27 is a dying AGN who has experienced the luminosity decline over 3 orders of magnitude within 1,000, 10,000 years, which is a quite interesting accretion disk event. And then I'm also surprised to find this. Okay, and then we found such a really interesting diamond agent, but it's a kind of like lucky discovery. But can we find more diamond agent, or even if it's not dying, can we find more such fading or final phase of the agent? So the one way to find such candidates, like try to check the final phase agent candidates. So one way is that, look at AGN showing a really, really strong outflows. If there is a strong outflows, if we believe agent feedback, such outflows blows up the central gas, and then which might produces central gas deficit, and then finally central engines might be quenched. So Zhao and Chen in a meeting actually compiled such kind of candidates. He made let us say 0.5 LIRGs samples, and then after the Subaru O3 follow-up, and then he has found very, very strong O3 outflow components as shown in a figure. And then some of them actually is y-axis is outflow velocity of the O3, and then some sources show the really, really strong outflows, which is exceeding escaping velocity of the host galaxy potential. So this is a good candidate, and let's check their current agent activity by observing NuSTAR. So the expected luminosity is bright enough, So the NuSTAR should detect them, even the central engine's Compton thick level, which is a quite typical value for ULAGs over scale region. So we picked up as a pilot program in Akari J0916, which is the O3 brightest sources, and then we conduct 100 kilosec NuSTAR observations. So the result is like this, and then again, the NuSTAR non-detections. And then this is a quite background dominated spectra. This gives us the strong upper bound of the X-ray luminosity is less than 10 to the 43.5. Even by assuming the Compton thick level absorptions. This is 30 times fainter than the value expected from the neuron lesions. So generally, most of the agent has a good luminosity correlation each other between X-ray luminosity and O3. This is a kind of the indication that most of the agent is on average the luminosity is stable in time scale of 1,000 to 10,000 years. But in case of J0916A, does not follow this. They are locating in this red arrow is the location to J09, which is the upper bound. And then this upper bound is well below at least one of the magnitude fainter than the other typical agent. And then some people might wonder, okay, but it's ULAG. So the ULAG is a high accretion-based sources. So sometimes X-ray emission is saturated. So that we also overplot other ULAG candidate, ULAG sources. And actually, even compared to other ULAGs, J09 is still tentatively smaller values of the X-ray compared to other ULAGs. In addition to that, J0916A shows one interesting trend that there actually X-ray luminosity is still fainter compared to the agent torus emissions, which is a good trace of the past agent activity of the 10 or 100 years time scale. So the most of the sample is located here in X-ray emitting luminosity ratio in the y-axis, and then mid-infrared O3 luminosity ratio in the x-axis. And then J0916A is located here. So they show the very X-ray faint source compared to mid-infrared bar. So this source is a kind of fading agent, but still continues to fade in time scale of the 100 years. We are actually conducting much more fading agent candidates, and then 4 more agent has been accepted for observation by NuSTAR, and then 1 source has been recently observed, and then they show a similar trend. So the NuSTAR gives more fading agent candidates in the future. So this fading agent is quite interesting in terms of the life cycle and agent feedback, because they are actually fading or dying agent, but we already know that this agent finishing their life cycle at least one time, whose lifetime is 10 to the 5 or 6 years. So it is a really good candidate to check how agent feedback is effective after the 10 to the 5 or 6 years of the agent. We are now conducting more ARUMA observations to check how such agent feedback is effective. And then John Chen already got the time, and then so he will soon show the result in the future. So the NuSTAR is, again, I would like to emphasize that the good, really best probe to find the current agent activity, and it gives a really most strongest upper bound of the current agent activity, and then increasing the fading agent candidate now. So it's conclusions that we have found interesting agent whose final phase of the black hole growth, and then NuSTAR gives most strongest current agent activity. This poses that might be a good challenge of the accretion-based physics, or might be, and also gives us a good candidates of the agent feedback test with a combination of the ARUMA observations. Okay, that's it from my side. Thanks.
questions? Yeah, on Zoom, Daniel, you can speak up.
Yes, a very interesting talk, Kohai. I had two questions. One was the lack of the radio core in that source. My understanding is it's pretty common in double-lobed radio sources not to see the core. Was your limit very strict compared to what's typical? Maybe you could comment on that. And then the second thing is just, unfortunately, it's been kind of a joke even in Pasadena with the sources that I observe. I'm often looking at AGN that don't get detected by NuSTAR. And typically we think what's going on is just very, very heavily obscured, very deep into Compton thick. And I've unfortunately many examples of that. So I'm wondering, it's not clearly that these things are turning off. It could just be that they're heavily Compton thick. And even the torus can get hidden if there's enough obscuration in the mid-IR. Thank you.
Okay, so about the first comment of the double radio lobes, I have checked that at least for 4.7, it's not a double radio lobes by checking the field of view of the VLA and ALMA. And then, so one interesting point for this is, the jet lobe is quite compact with a 5 kilopascal very young jet. And then, but we don't see any extended second component. And also as well as the NuSTARs, and then Spitzer also gives non-detections. And then this is why we think the central engine would be a good candidate of the fading agent. Yes. And then, yeah.
Well, since we are extremely late, I would end here the session. I would thank all the speakers of the session again.
Since we're doing this by Zoom at the moment, I think it's easiest if the people giving posters, you can actually present up from the front of the stage today, and I will just have everything on Zoom on my laptop right here. So there are, I believe, 10 of you in person who gave me posters. Plus, we're going to start with Brian Greffenstedt, who is going to be doing this remotely.
All right, hi from Dark 30 in California. So this, so our poster is really just an advertisement for Stray Cats, which you can go back, is the, oh, let's look, okay, sorry, which is auto-playing, yeah. So basically it's a project we've been working on for the last few years to turn the nasty backgrounds that you can see in the bottom left there, which are stray light from sources outside the field of view, into scientifically productive data. So this is basically looking at every single NuSTAR observation near the galactic plane where we see excess background and turning all of that background into an additional treasure trove of new observations. So version 1 of Stray Cats came out last year, had about 400 or 500 observations through 2020. Version 2 is now in press. So Renee has a paper adding the data up to the end of 2022. So 490 observations, 83 sources. With all of these things, you get serendipitous monitoring of various binaries in the plane. McKinley's got a great paper on timing of SMCX1. You can do spectroscopy all the way up to greater than 100 keV, and Gulo actually has a paper coming out soon on that. So thanks.
So I'm going to be enforcing Kristen's 1 minute, very strict enforcement policy.
Good morning, everyone. I am Moaz, and I'll be talking about JWST today, which is the most luminous TeV source in our galaxy. And one of the reasons studying these sources is important is that they are often associated with pulsar wind nebulae, which suggests that pulsar wind nebulae are somehow responsible for the production of the high energy particles, which in turn produces high energy photons. what we did is we analyzed X-ray data from Chandra to characterize the emission from the pulsar, and then extrapolated our results to the higher X-ray energy range, only probed by NuSTAR, to get the properties of the PWN. We then used our results along with broadband data of our source from different missions and fed them to a one-zone time-dependent leptonic model, which eventually improved our understanding of the system. Thank you.
Hi, I'm Victoria Grimberg. I'm presenting on behalf of my PhD student, Camille Diaz. We are using Gwela X1 to understand wind and accretion structure in high mass X-ray binaries. So what Camille has done, she used 100 kiloseconds of simultaneous XMM and NuSTAR observations in a time resolved way, so spectra on time scales of just 300 seconds. And she used that to both trace the accretion structure by looking at the cyclotron lines and the spectral shape, and to trace the onset of the accretion wake, so of the complex structure that the neutron star is inducing in the wind of the star as it comes into the line of sight. This is exciting work, and Camille is going to be on the job market this fall and winter. So take a look at her poster that is over there. And if you're online and don't have access to the poster, drop me an email and I'm going to send it to you. Thank you.
Hello, everybody. I'm George, second year PhD student. We have performed several simulations using reflex ray tracing code to find how the circumnuclear material affects the Compton shoulder, a low energy tail formed by downscattered iron line photons. So we have found that the column density, along with other physical properties, affect the shape and the flux of the Compton shoulder. Moreover, we have performed different simulations, adding complexity with several geometrical objects. And finally, we have simulated spectra using CRISM so that in the future, the Compton shoulder can work as a tool to constrain both the physical properties and the geometry of AGN. That's it.
Right. He didn't actually send me a slide, so I put his poster on. Oh, you're good.
Hello, everyone. I'm Georgios Vasilopoulos, and I'm presenting on behalf of Sotiris Karaferias, who is an undergraduate student on the University of Athens. So what we did is model the super Eddington outbursts from data from GBM, BAT, etc. We investigated degeneracies between all the parameters, so that has to do with intrinsic spin up and the orbital parameters of the systems. And I think the most exciting result is that for Swift J0243, we found evidence of super Eddington transition in the disk. That means that the disk actually shows evidence where the spin up does not follow the linear relation that we expect that you see on the upper plot, but we see some transition between sub-Eddington and super Eddington structure in the disk that you can see on the lower part. And this is an agreement with theoretical prediction by Sastina et al. And thank you for your time.
Okay, my poster is advertising the NuSTAR Serendipitous survey and our imminent release of the 80-month catalog. This is by far the largest survey with NuSTAR and with a focusing hard X-ray mission. It's been a mammoth effort with the 80-month catalog led by Lizelka Clint in Durham. For those unfamiliar, we achieved this survey by taking essentially all NuSTAR data and detecting sources in the blank sky areas around science targets to build up a large unbiased survey. And we've had a huge campaign over the years of follow-up with ground-based telescopes to get spectra, redshifts, and multi-wavelength information. If you want to know more about the science possibilities with the survey, please come and talk to me for more.
Hello, my name is Joseph. I'm a PhD student, however, in informatics and automation, something completely different. And what we did is that we developed a tool based on a convolutional neural network that can classify the type of variability and using dynamical power spectra. But the tool was built on XM Newton data, so we had to modify the data to match the NuSTAR, and created two types of time maps, one with strict window length, one with a variable window length. What that means, please check the poster. And what we found is that the result with the strict windows length is better, and that's caused by the, probably by the resolution of the periodograms when you have the variable window length. So yeah, that's all.
Hello to everyone, I'm Andrea Marinucci, and my poster reports an analysis we are doing on this bright quasar, which is RBS 1055, at a redshift of about 0.5, and it has all basically the spectral features we see in the local universe. You see that there is a reflection spectrum, and there is a double corona, not corona, and a warm corona, and it can be well explained in terms of the double corona model we use for standard sources in the local universe. What I find amazing is that after 10 years ago, we were talking about these features above 10 keV in local sources, and now we are observing the same spectral features in sources which are much far away at about a ratio of 0.5. That's it.
I'm trying to understand the pulse profiles of accreting X-ray pulsars. You've seen a lot of images where the accretion happened onto two poles like perfectly. It's a beautiful image, but unfortunately it's very wrong. We can actually often see both poles even at the same time because of gravitational light bending or reflection of the surface and so on. So we really don't know what part of the emission comes from which pole. And that's a problem if we want to model and understand these sources. So I'm trying to do this with a new method based on the blind source separation. And if you want to know how the method works and the first results that we got, come have a sip of water, because that's where my poster is.
Hi, I'm Stefan Fladutescu from the University Observatory in Munich. And we performed X-ray mock observations of cosmological simulations, which came from our group as well. And I implemented for our mock observations a new method to also look at X-ray binaries in the simulations from the stellar component. And what we did, we compared to observations from recent survey of the Virgo cluster galaxies, and we match observations very well. And another advantage of our new method is that we can really separate not only the spatial distribution of X-ray binaries, but only their contribution to the total X-ray spectrum of a galaxy and galaxies in general. If you want to know more about what I did in my work, my poster is also near coffee and water. So thank you.
So for those of you who have posters, if you have not put them on Zenodo yet, please get in touch with me. I'm the person who's orchestrating that. We'd like to have your posters accessible for virtual access. Otherwise, one more round of applause for the presenters, and then it's coffee time. We'll reconvene in 20 minutes.
Hello, welcome back, everybody. We'll start the next session. To our session, we have 6 talks, 20 minutes each. And our first speaker is Guillermo.
Okay. Hi, everyone. I'm Guglielmo, and Gulo is totally fine. And today I'm going to talk about modeling X-ray reverberation lags in supermassive black holes. I'm going to do that on behalf of the Black Star collaboration, which is black hole spectral timing and reverberation. You see some of the names listed in my first slides. I highlighted the one that are participating to this conference. Please feel free to talk to them and to me. We always welcome people that like to analyze accreting black holes with spectral timing techniques. Oh yeah, here. So my talk is divided in 3 parts. One is the quick explanation of reverberation. We heard a lot about that from Jingis Wang talks yesterday, and then Wilkins. So I'm gonna go very quick on this. Then I'm gonna give you like a quick and probably not complete overview of the observations that we have of this particular signature, and something about modeling this. And if we have, if I have a little bit of time, I wanna also try to explain how we can use this reverberation not only to constrain accreting black holes parameters, but something else. So let's dive in my cartoon picture where we see these accreting black holes. So we have an accretion disk, some seed photons shining the corona upscatters these photons, and we have some direct emission and some reflected emission. So the spectrum usually looks like a 2-component spectrum, a featureless direct component and a reflection with its characteristic features, the iron line, the Compton count. This is from a spectral point of view. I want to look at from a timing point of view. And we know these systems are variable. The variability comes from the corona, and this variability is transferred to the reflection. So immediately from a timing point of view, we understand that the variability of the reflection should lag behind the variability of the direct emission. So if we look at particular energy band dominated by the reflection emission, we should see this energy band lagging behind the energy band, another energy band dominated by the direct emission. And this is exactly what we see in several sources, in several supermassive black holes. So here goes to my second part, the observations, and I want to point out a very, very nice review done by Erin Kara in 2016, where she collected the whole XMM archive and measured X-ray reverberation for more than 20 AGNs. So we have a sample, but I like to divide this sample in what I like to call the good kids. And here are some lag energy spectrum, because when people usually show you reverberation, they show you usually these sources, or maybe the first one, which is very clear that the iron line, in the iron line energy range, there is a clear enhancement of the lag compared, for example, to another band, 1 to 3 kV, that is dominated by the direct emission. Well, of course, this is some of the good kids, but there are also the bad kids. These are other AGN that are in the catalog and classified as showing reverberation signal. And you can see that, yes, it's significant, the enhancement at the iron line of the lag. But if we want to fit this with a model, then it's going to be quite complicated. So when people talk about reverberation lags, be aware that not all the AGNs are like the first one in this slide. What can we do, especially with this not well-behaving AGN? Well, usually if someone doesn't behave, you ask some help. And the help here should and could come from NuSTAR. Here are 2 examples where actually reverberation lags have been detected in NuSTAR as well. So the first one, I believe, is the first detection of reverberation lags in NuSTAR, is from Abdul Zogby in 2014. This Seyfert AGN MCG -5 -23 -16. But even more is the Swift J2127 detected by Erin Cara, the signal detected by Erin Cara in 2015, where you see clearly how NuSTAR can detect the iron line, but also the Compton hump in the lag, and does an even better job than XMM in this particular case. So with the help of NuSTAR, we can probably constrain more about the lags. How do we do that? Well, of course, when we want to extract information from a particular signature, we need a model to do that. And this is what I've been done together with Adam Ingram during my PhD. We developed this model called RelTrans. It's a spectral timing model, it's a full ray tracing model of the photons close to the black hole, is a Lampos model, and the Lampos is an approximation. And here I want to make clear that nobody, I think, believe that there is a Lampos on top of the black hole. The real question is how bad of an approximation is the Lampos model? And we believe that in some cases, especially in some safer galaxies, the corona is quite compact. So this approximation is actually not that bad. So what we do, we tested this model, we applied this model to the data. First case for us was Markarian 335. And this is important, and here is important to understand that we fitted not only the lag energy spectrum, but the time average, so your normal energy spectrum, together with the lag, so simultaneously, in different time scales. The lag behaves differently in different time scales, and everything is encoded in the model. So I'm going to show you just the result. The interesting result is that we are sensitive now to the mass of the black hole. Why? Because now we are probing the timing, and so we are probing the actual physical dimension of the accretion disk. So we can calibrate the gravitational radius and measure the mass. Also, fitting together with the time average spectrum, we break the degeneracy between the height of the source and the height of the Lampos source and the mass of the black hole. You see here a contour, and our measurement lays on 1 million solar mass for this particular black hole. If you pay attention to the contour, there is a 3 sigma contour with a higher mass. Why I point out this? Because our measurement doesn't agree with previous measurements with completely independent methods, for example, optical reverberation mapping. So do I believe that we are wrong? Yes, in this case, I believe we are wrong. In this particular case of Markarian 335, I think the model is not exactly reporting the correct mass. I've been contradicted before. We measured Sinus-61 mass 3 years ago. We published the result and we try our best to lower down the mass, find every caveat, because we got like a 20 solar mass black hole. 2 years later or 1 year later came out a paper that actually said the mass of Sinus-61 was 21 solar masses. So we were kind of right, or actually our model was right. But in this case, why I believe it is wrong? Well, because of this plot, the black hole mass is a function of optical luminosity. This is where Markarian 335 sits when with the optical reverberation mass estimate. In our case, Markarian 335 should be an outlier of this plot and also super-edited, which is not impossible, but probably unlikely in this case. Well, so what is the problem of the model? Maybe is the Lampos assumption. Maybe in this particular case, the corona is more extended. I have a slightly different explanation, but first I want to show you another fit to understand that explanation. This is another safer galaxy, Arcadian 564, and this is a work led by Colin Ewing, a brilliant grad student at MIT. He collected tons of data of this source, both XMM and NuSTAR, and he fitted together time average spectrum for XMM and NuSTAR, and the lag energy spectrum in different time scales. You see in the bottom plot, fast variability, you see the reverberation signal. This is fit with Reltrons, and in this particular case, the mass that we get is 2 million solar masses, which agrees perfectly with the previous estimates. Also, the coronal temperature coming from our feet seems a low temperature, which agrees again with previous measurements. So in this case, the lamppost seems to work. Maybe Arcadium 564 has a more compact corona, or maybe in this case, the NuSTAR data is the one that really plays a role. In Markarian 335, we didn't have any NuSTAR lag energy spectrum to fit. So maybe that solution at 3 sigma is actually the correct one, but XMM is not able to constrain that mass, which is the correct one. Just an idea. So we need, of course, to do more. These are just 2 examples. So I think we have a full archive of NuSTAR and XMM to explore. And just in the last 2-3 minutes, I'd like to go a little bit beyond just the parameters of these accreting black holes and try to explain you how we can do cosmology with reverberation. Actually, we can constrain the Hubble constant using X-ray reverberation. How? Well, if you remember at Nathan talk, you probably know how. So I'm gonna just flash through these slides. We now, thanks to Javier Garcia, have some reflection models with not a fixed density, but we can fit for the density in the reflection. So now the ionization parameter, not now, but the ionization parameter depends on the flux, the impinging flux of the corona to the disk and the density. And now we can fit for the density. Of course, we can fit for the ionization, so we can derive the flux, the illuminating flux. Now, knowing the size of the disk, we can derive the intrinsic luminosity. And of course, we can compare it with the observed luminosity and deriving the distance. There is a caveat here, which is the size of the disk measured by the reflection depends on the, is in units of gravitational radii, but we need physical units, so we need to know the mass. But you know that this model is sensitive to the mass, so this is another parameter of the model that we can fit. So with this X-ray reverberation, we can actually fit all together self-consistently, mass, distance, ionization, density, and derive the parameter that we are interested in. In this case, the density. Knowing the redshift, we can measure the Hubble constant. And maybe in the future, when we have a big sample of AGN, we can actually play a role and distinguish maybe between this dichotomy that is creating between these 2 measurements of the Hubble constant. One is the lambda CDM, and the other one is the distance ladder. So I'm gonna just show this last slide. This is like a simulation of NuSTAR plus XMM data, both the time average spectrum and lag energy spectrum fitted together. And you see that the contour, so our model is sensitive to the distance. So here is translated in the Hubble constant for this particular AGN and the mass. There is very little degeneracy in this simulation. So we are confident we can actually put some constraint on these variables. So I will leave with my conclusion, and yeah, I'll take any questions.
I have a question for Dan.
Yeah, thanks for the nice talk. So one thing I was interested in, when you're applying the RelTrans model to the lags that are calculated in Fourier space, you're having to bin over ranges of Fourier frequency, and you need to bin over a wide enough range of frequency to get signal to noise. However, the time lags, so when you've got a transfer function, the time lags change, and they can change quite rapidly as a function of Fourier frequency. So my question is, how do you decide what frequency bins you're using? It looks like in your plots, you're just picking specific frequencies and modeling them. So how do you choose those frequencies?
Is, as you said, a signal to noise. So it comes from the data. Basically, we first work on the data to do the rebinning in frequency to see if there is enough signal to noise to detect this reverberation feature, because that's the important, that's the one that constrains the parameters. Also, not seeing any reverberation is constraining as well, because the model has a prediction for a certain amount of lag. But let's say it's easier when you see the feature and the model constrains the feature. So once you pick the frequency range in the data where you see this, then the model picks the same frequencies. So basically, the average is done inside the model of the transfer function. So it's all in the Fourier space. So basically, yeah, that's internal to the model. So the model does this average as is done in the data. Right. So yeah, if there are like faster time scales, then we are going to neglect an average over that. So this is a problem. Actually, in black hole binaries, we pick much shorter, much smaller frequency range. So we can probe different time scales and see how it evolves. But in this case, we cannot. We have to average over the frequencies.
Sure thing. Thanks a lot.
Yeah, you're welcome.
We have time for one more question.
Understand? I think you didn't describe it, that in your modeling for variability, you assume a variable power law in some kind of, no, I would say arbitrary way. So then how much, no, this was something I puzzled already for a long time. How much your results depend on those assumptions? And
yeah. So what Andre is talking about is something that I haven't discussed in the talk, of course, like limited amount of time. You see here, for example, that depending on the frequency range that you pick, the lag could look very differently. And we know that at low Fourier frequency, so at longer time scales, the lag is dominated by something that we call like hard lags, continuum lags. We don't really know where it comes from. There are some models like propagating fluctuation through the disk. And then the reverberation lag is at higher frequencies. Our model accounts for the hard lags with a pivoting power law. It means that the direct emission is not stable, is not varying just up and down in the normalization, but is also varying in its slope, just fluctuating, I would say. Not so how much our results depend on this? Well, what we do in AGN, we actually fit the first lag, so the low frequency lag with this pivoting, accounting also including reverberation, but the reverberation is almost negligible there. And then we shut down the pivoting in the high frequencies. So basically what is fitted in the high frequencies is just reverberation. And the mass, so the pivoting has nothing to do with the mass. So what constrains the mass is the reverberation signal. So I would say it's probably that it doesn't affect any of our mass results. So I don't think it can solve the problem of Markarian 335. I also don't think that Arcarian 564 is affected by that. So yeah, that's my answer.
Thank you. Okay. Our next speaker is Lehmer who speaks about Mr. Observation of blazars.
All right. Okay. Good morning, everyone. My name is Lehmer Cotulli, and I'm an Einstein Fellow at Yale University. And today I'm going to talk about something a bit different to what we've heard so far, and that has taken most of my PhD and part of now my postdoctoral position, which is chasing some of the most distant and powerful jets using NuSTAR. So to bring everybody up to speed, the sources that I care for are the so-called blazar sources. Those are supermassive black holes actively accreting gas from their surroundings and are also capable of powering relativistic jets from the core. When this jet is pointed very close to our line of sight, those guys are called blazar sources. And usually it's been shown that these are multi-band emitters. They emit from radio up to gamma ray energies, and their spectral energy distribution usually shows two broad humps. Shown here is the SED of a famous blazar, Mercurian 421, and all the data collected up to that publication for this specific source. As you can see, there is a low energy hump that is usually attributed to synchrotron emission of relativistic electrons spiraling along the magnetic field lines into these jets and producing this first broad hump. And then the high energy peak instead is usually attributed to inverse Compton emission. So these relativistic electrons find a low energy photon field and upscatter it up to X-rays or gamma rays. This photon field can be either the same photons produced by the synchrotron emission, so we refer to it as synchrotron self-Compton, or it could be external to the jet, so coming from the accretion disk, the broadband region, the torus, and so we refer to it as external Compton emission. Within blazar population model, it's been understood that these sources, if you bin them in luminosity bins, they follow a specific sequence called the blazar sequence. So if you look at this plot here from Ghisellini et al. In 2017, what they showed is for low luminosity sources, both of their peaks peak at higher energies, but then as the source luminosity increase, you see that both of these peaks shift towards lower energies. And in particular, the most luminous of the source class have the high energy peak peaking way below 100 MeV. And we refer to this class as MEV blazars, and those are the ones that I'm really interested on. Why should we care for these sources? Well, first of all, they have extremely high jet powers. They're some of the most powerful and persistent objects in the universe. And you can see here, they can reach up to 10 to the 49 erg per second bolometric luminosity. They're so powerful that we can actually detect them up to the very high redshift, even beyond redshift 5. And this means when the universe was barely 1 to 2 billion years old, so very early on. Not only that, these sources have been shown to have extremely massive black holes of billion solar mass and beyond. Shown here is a histogram of black hole masses of blazars detected below redshift 3 in blue and above redshift 3 in red. As you can see, the distribution of the even higher redshift peaks to be even higher masses. So now the question comes, if we keep finding more and more sources with these black hole masses, how did this black hole form so massive so early on? Then how did they grow? And we can also think about this question if you look at the supermassive black hole space density shown here as function of redshift from the work of Sbarrato et al. In 2015, where the authors pointed at this dichotomy between radio quiet sources and radio loud. Radio quiet are those AGNs that do not have jets. And as you can see, they peak around redshift 2 in this distribution. But if you look at the orange line, which is the jetted AGNs, you see how their peak is actually quite earlier on at a redshift around 4. So again, this very fast black hole growth probably is linked with a jetted phase of an AGN. But for doing these kind of studies, we need to find more sources, constrain their number density, and also do some more luminosity function studies. But blazars are really important for these studies because every time you find one that is the one pointed directly at you, you're lucky, but because you're really seeing down the jet. However, when you see one, you can actually infer the size of the parent population. So all those jets that are too faint and pointed away from us that we cannot see. And this is the so-called 2 gamma square correction, where gamma is the bulk Lorentz factor of the jet. So how fast are these electrons moving along the jet lines? And if you think that gamma is usually around 10 to 15, for every blazar we see and we can constrain the gamma of, we're actually implying the existence of 200 to 400 such sources at the same redshift with the same black hole mass. And finally, to prove that these sources are really interesting, they're also being understood to contribute a bit of the cosmic X-ray background. Shown here is the total cosmic high energy background from soft X-rays up to gamma rays. And these MEV blazars in the hard X-ray part shown highlighted here in pink, they actually contribute little, like 5 to 10%. We know mostly it's AGN without jets that do the cosmic X-ray background. But these MEV blazars are actually the ones that could contribute up to 100% of the MEV background, which is the most uncertain part of this plot, because we are yet to have another MEV mission. The last one flew in the 2000s, and we need to find more sources to constrain these predictions. So I hope everybody now is convinced that MEV blazars are extremely important sources to study, but how do we find them? They're really, really bright, but they're really difficult to find. So this is a plot of luminosity versus redshift of the BAT sample of blazars. BAT, again, it's a hard X-ray all-sky instrument. And as you can see, beyond redshift 3, we barely have 5 to 10 sources. And the problem is that, again, what we hope to have one day is an MEV instrument that samples the peak of the emission. But since we don't have that, we have to follow another strategy. So what we do at first is use the capabilities of the Fermi Large Area Telescope, which is a gamma ray telescope, scans the whole sky every 2 hours. It's been in orbit for since 2008. And so can provide a view of the whole sky, and most of the sources detected by the LAT are indeed blazars. Now, if we have the LAT data for these sources, we can actually constrain very well the falling part of the external Compton emission. Shown here is a high redshift MEV blazars. And again, this is an SED, and maybe it looks a bit different than before, because if you look from left to right, we're going from radio up to gamma rays. The first peak is our synchrotron peak, as we shown before. At the high energies, we have the external Compton peak. And then in the middle, you have a third peak. Well, this is actually the big blue bump, the accretion disk that is revealed for these kind of sources, because our high energy peaks are, our SED peaks are shifting towards lower energies, unveiling the accretion disk. And we will talk about the importance of this in just a few slides. So again, the LAT can sample the falling part of the inverse Compton emission. And so when we have the LAT data, what we want to do is pointing with NuSTAR. So we propose for time with it, and we look at the specific sources, because with the great sensitivity that NuSTAR has, it allows us to actually sample the rising part of the external Compton spectrum very well, up to 50 to 60 keV sometimes. So now we have the NuSTAR data samples the rising part, the LAT data sample the falling part, and this allows us to put precise constraints on the location of the peak, and therefore confirming whether the sources are actually MEV blazars. And then we can constrain jet parameters from this for this source. Indeed, the lines that you show here, that I'm showing here, is a physical model for these specific blazars. And if you can fit the physical model to the NuSTAR plus LAT data, you can actually constrain the jet power. You can constrain the bulk Lorentz factor, the gamma factor we care for, the viewing angle. So it's really important to have this constraint. Then, of course, those are multi-band emitters. So and they're also known to be extremely variable sources. So what we want to do is trigger as simultaneously as possible a multi-band follow-up. So we ask for time with Swift, for which we use both the XRD data as well as the UVOT data. And then we had access to the Sarah Telescope Consortium, just optical telescopes that can get us optical photometry. And why do we want that? Well, first of all, we're constraining the average state of the source, having this simultaneous broadband coverage. The XRT is very good to complement the NuSTAR data, as they sample the onset on the external Compton emission. So again, jet power, electron distribution, really good constraint on the jet parameters. And then the Serapius UVOT, so optical and UV data, actually allow us to sample the accretion disk peak. Now, this is extremely important because first of all, this allows us to derive the luminosity of the accretion disk. And if you model this with a standard circular tsunami model, you can get the black hole mass of these sources, which is extremely important because sometimes these sources do not have masses derived from spectroscopy, for example. And these two methods have been shown to be in good agreement. So we actually can get our black hole masses and gammas from the high energy. Now you may wonder, why is NuSTAR so important? Do we really need those observations? And here's the proof that yes, we do. So here is the same source that I showed you before, studied by Ackerman et al. In 2017. And what they used here, they had the lab data and they took all the archival data for the source and performed the same kind of modeling that we did. And this is the best fit that they found and report in their paper. Now let's add NuSTAR to this. As you can see, the addition of XRT and NuSTAR can actually constrain very well the slope of the inverse Compton rising part, as well as precisely constrain the peak position. And you see how also the luminosity of the source now, the total luminosity has decreased quite a bit. In terms of some parameters of the model that you may care for, here are, for example, the slope of the electron energy distribution producing the emission. Of course, the slope now is softer, so the electron energy distribution is softer than previously derived. Our bulk Lorentz factor derived here was actually a bit higher than previously thought. And importantly, the dissipation distance, what was derived before was that this emission region was within the BLR. So most of the photons were coming from the BLR. But with NuSTAR data, we find that it's outside the BLR region. So the photons contributing to this emission are mostly coming from the torus, the torus size. So here for reference, the size of the BLR that you have. So we really, really need NuSTAR. And just to sort of summarize what they've done throughout the last few years, we have, with this method, find 9 more sources that are high redshift. So like 2 or 3 were below, just above redshift 2, but most of them are above redshift 3. The farthest one being a redshift 4.31, which is the highest redshift that LAT has detected blazars. And all of them are have black hole masses of billion solar mass black holes. And their average bulk Lorentz factor, if you take all of them into account, is actually around 10. Now, this again reminds us of the supermassive black hole space density predictions, right? Because 10 means 2 gamma square more sources, so about 200 instead of maybe 400. And this plays a huge role when we look again at the supermassive black hole space density plot. Shown here, this is a reminder of the first plot that I showed you. The yellow line is the one from Sbarrato et al. And all the dashed line that you see are the ones derived using the latest BAT X-ray luminosity function that is soon to be published. But if you take the latest X-ray luminosity function and you do this 2 gamma square correction, you can see that depending on the gamma factor, you can have order of magnitude difference in number of on supermassive black hole space densities. And it seems like the green line now is the most favored one, also from the luminosity function study. So those high redshift sources may be a bit lesser powered than what we, or lower bulk Lorentz factor than what we thought before. So I'm just gonna leave you here with this take-home message. MEV blazars are really, really cool. We need NuSTAR to study them and to find them and characterize it, in fact, that they are MEV blazars, and study them throughout multi-wavelength campaigns. And apparently we've been very good to convince the NuSTAR panel that this is actually something we really need, because we already have 4 more sources beyond redshift 3, which were part of an undergraduate thesis that I supervised at Clemson University. And also in this latest cycle, we were approved for 10 more sources above redshift 4, which is going to be very exciting to see what they look like even at higher redshift. So thank you very much for your attention.
Questions? The audience? Once again, questions in the chat, but go ahead, write them in the chat if you want. I have a question. When you derive gammas for individual blazars, what is the main other parameter that it's degenerate with?
There are quite a few. So actually gamma is sort of an input parameter for our model, which unfortunately is not yet, it's a fit by eye model. So we kind of have several about 8 input parameters, including black hole masses and slope of the particle population. So we have quite a few degeneracy, to be honest, but yeah, I guess that's the answer.
Question?
Yeah, this is a more technical question about your NuSTAR observations. For these Redshift 3 blazars, roughly what exposure times are you using, and what's the count rate that you're normally expecting for these sources?
So they're actually some of them we can observe for 20 to 30 kiloseconds, and we get sometimes less than 100 counts total. They're very faint. It's a point in the NuSTAR band, but we still like some of them can be quite bright. But usually also at Redshift 4, I saw the first one that got approved this cycle came in, and it's really faint.
Okay. If my Italian is any good, somebody's typing a question, but I don't know how long we will wait. Okay. Dan Stern asks, how essential is it? Is the MEV data for this work? They're higher redshift blazars, but undetected by lab.
MEV data would be fundamental because we will see the peak of these blazars. And actually using the luminosity function study, I made some prediction of how many blazars would be detected by forthcoming MEV missions. And we could actually detect some thousands of sources even beyond Redshift 4, not thousands of sources beyond Redshift 4, but total. So about some 20 sources even beyond Redshift 4 with MEV instruments, depending on which one you pick. It would be great to have an MEV instrument.
Okay, I don't see more questions in the chat. If there's any last questions from the audience? Okay, then let's thank the speaker. Our next speaker is Paul Dragas. He will tell us about exploring spin distribution of stellar mass black holes.
There we go. All right, let me restart my timer here. Hello, everyone. Thank you for being here. Thank you for not being at the beach, and to those who are at the beach, I can't blame you. My name is Paul Dragas. Over here, you can see a QR code that points you to my website, and there you can find more information about my work. And I'll keep talking until you have enough time to take a picture of this slide. I'm a graduate student at the University of Michigan, and my work with John Miller has been focusing on exploring the spin distribution of stellar mass black holes. And I will specifically talk about our efforts to use relativistic reflection with NuSTAR to look at the black holes in X-ray binaries. I noticed that similarly to our poster, NuSTAR is pointing at my face, so let's change that. This is my first in-person talk at a conference, so as soon as I start saying controversial stuff, please don't eat me alive or throw stones. I will first touch on the motivation to measure black hole spins, and then I will move on quickly to the basics of relativistic reflection and move on to give 2 examples of spin measurements and then talk about the entire distribution. And just as a side note, because I was asked to stick to 16 minutes, I cut about 50 slides of results. And I will focus more on the details of each individual measurement and what we added to this process. So I believe that repetition is the mother of all learning. So hopefully now seeing those points again will fully convince you that it is important to measure black hole spins because, well, astrophysical black holes are simple. So they're fully described by their mass and spin. So knowing their spins tells us half of what there is to know about them. And knowing the spin of a particular black hole can tell us information about its formation mechanism, its evolution, pointing towards massive star evolution, supernovae, physics of accretion disks, of X-ray binaries, jets, coronae, and so on. And also, as we saw earlier, knowing the spin of a black hole can also allow us to test general relativity in its vicinity. Currently, there are 6 main methods that could in principle be used to measure black hole spin. The first 3 in the top row are discontinuum fitting, relativistic reflection, and quasi-periodic brightness oscillations, or QPOs, and all of those have been used for a while now. And the 3 methods in the bottom row are just now starting to become a possibility, and that is the polarization of the emission from those binary systems, the shape of the gravitational wave signal from binary black hole mergers, and direct observations of black holes. And as relativistic reflection is the main topic of my work, I will keep focusing on this. So what we do in order to measure black hole spins is observe the emission from the innermost regions of the accretion disk around the black hole, and we probe the direct emission from the disk, we probe the coronal emission and the emission reprocessed by the disk, which we call reflected. And each one of those features has a specific spectral shape. And NuSTAR is an ideal instrument that allows us to separate the reflected emission from the underlying continuum. And this is because of its sensitivity and its wide band pass that covers the 2 main features of relativistic reflection, and that is the iron K band and the Compton hump above 20 keV. If you have more questions about this picture, come and talk to me and I will point you to Javier after this talk. Now, once again, raise your hand if you've seen this plot before. The spin of the black hole comes into play through the size of the innermost stable circular orbit, and a black hole that is rapidly rotating in the same direction as its accretion disk will allow a smaller ISCO when compared to a non-rotating black hole, and even smaller so when compared to a black hole that is rotating in the direction opposite to that of the accretion disk. And as matter orbits closer to the black hole surface, gravity imprints stronger effects on the emitted radiation. And by measuring how distorted those features are, those reflection features, we begin to directly infer how close to the black hole the radiation was emitted from, and therefore we can probe the size of the ISCO and the spin of the black hole. And as an example, as a first example, I will talk about Swift J1728, and this is a young black hole in an X-ray binary system. And here in the top left, we see the NuSTAR spectrum. So what we first do is we describe the emission from the accretion disk and from the compact corona, and that points out the features of relativistic reflection. Then we fit multiple theoretical models in order to probe the full extent of the physical processes that can take place in this system. And we do that in order to obtain a best fit solution. Then we run an MCMC analysis in order to fully explore the parameter space of those models. The spin of the black hole is one of the 3 parameters of this analysis, and focusing on this, we can directly infer the dimensionless spin of the black hole. Now, yesterday we saw, I think, 3 or 4 great presentations and 1 fantastic poster about Maxi J1820. So I figured might as well let's do another one. Sources like Swift J1728, the previous one, are relatively straightforward to analyze, especially when compared to things like Maxi J1820, which currently has 27 archival NuSTAR observations. First, what we want to do is select the observations for which we expect that the accretion disk extends all the way to the ISCO. And for that, we use the Eddington fraction of the observation. So based on theoretical predictions, on numerical simulations, and even observational constraints, we expect that for Eddington fractions between somewhere like 0.1% to 30%, the disk should extend all the way to the ISCO. So we only analyze observations within that range. Of the 27 available NuSTAR observations of Maxi J1820, 19 are within those limits. And now, in an ideal world with unlimited time and extremely powerful computing power, we would fit all of those observations simultaneously and link parameters such as the black hole spin and inclination and iron abundance and so on. But still, as you probably know already, as soon as you have multiple very high quality spectra being fit with complex models, it becomes nearly impossible to fit all of those simultaneously, and even worse, to run an MCMC analysis. So instead of doing that, instead of fitting everything together, what we do is we fit each observation individually, and then at the end, we combine the results. So 19 observations times 6 models tested, and I will talk more about that in a second. That means about 120 fits, which at roughly half an hour each accounts for 60 hours of me sitting in front of a computer. And that's just terrible. And when doing that, there's one thing that you learn to hate, and that's local minima, which are very frequent. So in order to bypass that, what we do is, instead of fitting each observation by hand, what we do is, for one observation, we apply one model and we generate one combination of parameters. And then we take that combination of parameters about 30 times and we slightly vary it. And by having all those variations of initial sets of parameters, we fit all of them simultaneously. And now it is not necessarily guaranteed that all of those will reach a global minima, but some of those fits will reach what hopefully approaches a global minimum. So we take those parameter combinations of the fit, and we shake up the parameters again, and we fit again. And this time we expect that, if not all, most of those runs will end up around that minimum. So we obtain a combination of parameters that produces a global minimum. In summary, we take one observation, we apply one model and shake up the parameters and fit, and obtain the parameter combination that produces the best fit model. And then we apply the other models. We test for the effects of coronal geometry, different incidence spectra, different accretion disk densities. So in total, we test at least 6 models. And then we apply the same treatment for all of them and reach the best combination of parameters for all. And then we choose the model for which the fit is most statistically significant. So for each observation, we find the best performing model and combination of parameters, and we do that for all observations. Now, that seems like doing a lot more work, but doing 30 fits and then shaking up the parameters and doing 30 more, that's 60 fits per model. So that's 360 fits per observation. And for MaxEJ1820, that's about 7,000 fits. But the initial 30 fits are all run in parallel. And if they don't converge after about 5 minutes, they're stopped. So 60 fits per model take about 10 minutes to run. So one observation takes about 1 hour. The 19 observations take 19 hours. And while that does seem like only a slight improvement by a factor of 3 or so, it is fully automated, and it performs much better at finding the global minima than, you know, a tired grad student would. So we fit all the observations, and we make sure that the fits are indeed acceptable. And then we run an MCMC analysis for each observation. And I won't go into details about this, and they will probably just be in an appendix of some paper at some point. Our code automatically generates plots showing the posterior distributions for spin and inclination in the analysis, and a corner plot. And those are done as a way of checking our analysis visually to make sure that things are sensible. And then we combine all the posterior distributions for spin and inclination into a single measurement, and we report the mode of that distribution. As a fun side note, our analysis for MaxEJ1820 finds an inclination of 64 plus or minus 3 degrees, and the radio jet inclination is 63 plus or minus 3 degrees. So take that, non-believers. This plot, I've seen a couple of versions earlier. This plot shows all current spin measurements in black holes in X-ray binaries. And I spent about a month going through the literature for those. The red points represent measurements made using continuum fitting. So that's a different spin measurement technique. The green points are our new measurements made with NuSTAR data. The blue points are reflection measurements made with NuSTAR data by other authors, and the yellow points are reflection measurements made with NuSTAR data, reflection measurements made with other instruments. We focused on systems that did not previously have spin measurements with NuSTAR data, and we ran our analysis pipeline for a total of 30 systems, and we were able to measure 10 new black hole spins. And as you can see from this plot, and has been mentioned extensively earlier, it appears that most of the known black holes in X-ray binaries have high spins. And looking at the distribution of spins inferred from all those measurements, the conclusion becomes even stronger. Again, the green curve represents our new measurements. That is a subset this time of the blue curve, which shows all reflection measurements made with NuSTAR data. And that is a subset of the yellow curve, which shows all reflection measurements with all instruments. Red curve is again continuum fitting. The black curve represents the complete inferred distribution of black hole spins in X-ray binaries. And the numbers quoted on the left represent the modes of those distributions together with the 1 sigma credible intervals. And when we compare this spin distribution with the distribution measured in black holes detected through gravitational wave signals from binary black hole mergers, we see that the distributions do not agree, with the gravitational wave black holes preferring low spins, while black holes in X-ray binaries preferring high spins. In the previous slide, I plotted the posterior distribution from the second gravitational wave transient catalog, simply because I couldn't find the data from the third one. But if we look at the distribution that they put in their paper, we see that it pretty much agrees with the one from the second catalog. Now, one very interesting result was found by the authors of this paper that this figure on the right is from. They show that if instead of treating the black holes as the heavier and the lighter one in the system, if they treat them as the more rapidly and less rapidly or slower spinning black hole in the system, the distributions of spins can be much better separated, and there is much better support for rapidly spinning black holes in their samples. And this was also confirmed by LIGO in their third gravitational wave transient catalog. So while we talked about the importance of measuring one spin, I would like to briefly mention that measuring the distribution of black hole spins helps with understanding the entire stellar mass black hole population. It helps with relating binary black holes and X-ray binaries. It provides informative priors for gravitational wave measurements, and it serves as a foundation for next generation gravitational wave and X-ray observatories such as CRISM or Athena. And lastly, and probably most importantly right now, it allows us to identify possible biases and systematics of our methods. One thing that we can look at is possible observational biases in order to explain the spin distribution that is peaked at high values. These plots show the ability to recover the spin and inclination that we assumed when we generated some fake NuSTAR spectra. And unexpectedly, we find that it is much easier for models to recover low spins and low inclinations. So it's very unlikely that this is what is biasing our distribution. One other thing that we looked at is all our spin measurements from each individual observation versus the inclination measurements. And while looking at those measurements, especially at the ones with relatively small uncertainties, it does seem like there is on the right there an increasing trend of spin with inclination. But if we look closer, it appears that way simply because of the many observations of Maxi J1820. And if we take out Maxi J1820 and we take out the points with huge uncertainties, the story becomes much nicer, and then there's no apparent bias. So what is happening with Maxi J1820? If we look at it, things again are interesting. The transparency of the points in here is proportional to the ratio of reflected flux to the total flux in the observation. And we use that to weight the combined measurements. And previously, any of those measurements would have been regarded as a good measurement. But now, having all this data and all those measurements, we increase the accuracy of our spin measurement at the cost of somewhat decreasing the precision. So one sin that all or most spin measurements are guilty of, including most of mine, is that the uncertainty quoted is simply statistical. And by doing this sort of analysis, we begin to understand the systematics of our analysis as well. And lastly, what we can do is look at the effect of other parameters on spin measurement, and this can allow us to test possible biases in the model and learn about the entire distribution of X-ray binaries. So for example, here I'm showing the relationship between the spin and the iron abundance on the left, and the iron abundance and reflection fraction on the right. And this is a huge data set. We have 50 observations of 10 different black holes, each with 20 or so parameters. So for those 20 parameters, if we plot one against another, we have what, 20 choose 2, so that's like 190 combinations. So that's 190 plots with 50 points. It's huge, but we're trying to look at those and try to identify possible biases and interesting physics in those measurements. So to summarize, we looked at about 30 systems, in total about 120 observations with 2 spectra each. We tested more than 6 models per each individual observation, and we measured 10 new black hole spins, and there's a plus there because there's more stuff that I don't have time to talk about. For those 10 new spins, we obtained the measurements from 50 observations, and as an interesting note for those interested, of those 50 observations, 15 prefer the default RealZill model, 26 prefer the Comptonization variant, and 9 preferred the maximum allowed disk density in the high density model. So that's 10 to the 19. And never was the lamppost model the preferred statistical version, RealZill variant. And for my grand closure, I will show you the 10 spins that we measured and pause for half a second to give you some time to take a quick look at them. And I will keep this up for you to read and judge and, you know, possibly be upset until I reach the end of my sentence. And with that, I would like to thank you for your attention and leave you with my very poor attempt at painting that beautiful picture up there. We were getting rid of seeing the same picture, so I tried and I failed. So let's leave it at that.
Thank you. We have time for one quick question.
Yeah, it's a very impressive work. I'm interested in the case of Maxi J1820, the stuff with inclination. Previous papers like Douglas Buisson and others have shown that the data really looks like it needs more than just one reflection component. Maybe we have used 2 lampposts. So I wonder how much of that different inclinations that you're measuring, different observations have to do with maybe changes in the proportion between the 2 possible lampposts that you need, or just simply 2 reflectors.
So please excuse my my joke that I'm about to give you as a beginning of an answer. There's a saying that all models are wrong, but some of them are useful. The idea is that we're trying to apply a consistent treatment to the entire sample to apply the same set of simplistic models. Now, naturally, in some sources, such as V4641 Sagittarius, that is impossible because of all the junk that is around it. But for sources that are slightly more well-behaved, such as Maxi J1820, when we look at the residuals, so in this plot that I'm showing right here, the top panels in each one of the chunks of 2 represents the residuals when fitting with a power law, and the panel below that are the residuals when fitting with the models that are written there, which are mostly absorbed disk plus reflection. So we see that generally the residuals look pretty good with a single reflection component. Now, in some cases, there might be some extra features, such as right here or there. It is possible that some of this might be affecting each individual result, so each spin measurement from one of those observations. But the point is that by doing this enough times on a large enough sample, all of those will kind of average out. So when we go to this plot over here, you see that all of those average out around the true value.
Okay, we do need to move on, but thank you all. Let's give him a round of applause. There are some questions on Slack as well if you
Yeah, of course.
Our next speaker is Alicia Tortosa, who'll tell us about extreme accretion onto supermassive black holes.
This is working. Okay. Hello everyone, I'm Alessia Tortosa, and today I'm going to talk about this work, which is about the analysis of a sample of AGN which accrete in an extreme regime. We are talking about super and hyper Eddington sources. So first of all, I want to underline why it is important the study of super Eddington sources. We know that from super Eddington accreting flow, we expect a very strong emission of winds and also a big feedback. And we know also that, for example, in tidal destruction events, the mass accretion rate is going to exceed the Eddington limit. So studying AGN, which accretes in this regime, can help us to understand something about this process. And also it can give us the some insights of the fast growth of the first supermassive black hole at high redshift. But which is the most important difference between sources accreting in different low and moderate accretion regime and in the super Eddington regime? The main difference is in the accretion disk, as we have seen already, because in sources that accrete in the low accretion regime, we know that they have this simple Sakura-Sonaive standard Sakura-Sonaive accretion disk, while super Eddington accreting sources show a slim disk, so optically thick and geometrically thick accretion disk. And in this kind of accretion disk, phenomena as photon trapping and advection cooling are very important. And they will give rise to an emission which is mainly anisotropic, and also, as I said, they can power winds and outflow, and the expected X-ray spectrum is going to be pretty steep. So the sample of the sources that we are going to that we analyzed is composed by some sources which belong to the super Eddington accreted massive black hole sample, which is a sample of sources in which all the objects have the mass estimated via reverberation mapping. These sources are all classified in the optical as narrow line Seyfert-1 galaxies. We have property NuSTAR observation simultaneously with the XM and Newton or Swift. But the most important thing that I want to underline is that, as you can see here in this plot in which I show the mass and accretion rate of our sources compared with the Seyfert-1 sources from the BAS-DR2 sample, we are going to explore a very extreme region of range of accretion. Before telling you something about the sample, I want to focus on this source, which is IRAS 04416 plus 1215, which is the most extreme source of our sample. As you can see, it has a very high mass accretion rate. So given the amount of matter that this source is eating, and giving also the peculiar spectral shape, we refer to this source as the dinosaur. And you can see it is the best fitting model of the spectrum of these sources. So actually the best fitting model is this one. Here I plot the XMM and the NuSTAR data of this source compared to the median of the Seyfert-1 spectra from BAS. You can see there are a lot of different components. In the soft, we find very high soft excess component and 3 warm absorbing component. If we extrapolate the position of this warm absorbing component using lower or upper limits, we can infer 2 different scenarios, but actually it's not possible to disentangle which is the real one, because it's with just X-rays it's not very simple. And in these 2 scenarios, we can say that this warm absorbing component can be multi-phase if we and in different position, and they can give also very strong feedback if we consider the upper limit, while if we consider just the lower limit, these components are co-spatial and probably they are accelerated by magneto-hydrodynamical process. In the hard X-ray, we found a very strong reflection, but the most important thing is that we can, thanks to NuSTAR and its high resolution at high energy, we can constrain very well the value of the coronal temperature, which is one of the lowest coronal temperature measured by NuSTAR. These are the sources of our sample. As you can see, all of them show very peculiar spectral shape, which is actually very similar of what we expect for NuLANDS C41 galaxies with very steep primary power law, some warm absorbing component, and a very strong reflection. So speaking about the reflection, yes, as I said, they have most of them, they have a pretty high reflection fraction, and most of them are well fitted by a model which include the relativistic reflection. And actually you can see here from this plot in which there is the 3 to 10 keV spectrum, the residual of the 3 to 10 keV spectrum fitted by simple power law. The iron K alpha line appear to be pretty broad and probably also ionized. And looking at the equivalent width of the iron line, of the iron K alpha line, okay, we can see that also the super-Eddington sources follow what it is expected from the literature about the X-ray Baldwin effect. In this plot, we extrapolate the equivalent width in 2 different ways. Here, we consider the broadband spectrum fitted with the best fitting model plus a narrow Gaussian line, while here there is just it is just extrapolated from fit in the 3 to 10 keV band with just a power law plus a narrow Gaussian line. So the fact that here we found a pretty high value with respect to the one which include the best fitting model, so also the relativistic reflection, it can be related to the fact that the broadening of the due to the relativistic reflection can enhance the narrow core of the iron K alpha line. These are the results about the parameter of the primary continuum. As I say, they have all, and these are compared with the values that we found in 2008 for the low and moderate accreting sources with NuSTAR. As you can see, the photon index is pretty steep. We cannot constrain the cutoff for most of these sources, just for the dinosaur, and this is Markarian 3A2. Probably the point is that these spectra are truncated at around 20-25 keV, and they are very steep, so it's not very easy to find a good constraint on the cutoff. And but the most important thing that I want to underline here is that when we fit the model with the comptonization model, and we find also a lower limit, but still of the coronal temperature, and we extrapolate also the optical depth, they still follow the relation that we found in 2018. We use these values to see which is the position of these sources in the compactness temperature diagram. In this diagram, L is a parameter which is related to the dimension and the luminosity of the X-ray emitting region, the corona, and theta is the coronal temperature normalized. You can see there are different regions which tell us something about the behavior of a thermal finite plasma. This is the forbidden region in which the Baire production exceeds annihilation. And as you probably know, most of the EGN are located in this region. As I show here, these are the median of the sample from Ricci 2018. In this region in which the Baire production and the comptonization results to be the most important process in the X-ray production. Also, the super Eddington sources are located in this region. I reported also the case of two peculiar objects with a very low coronal temperature, 5654 and GRS. And this is the dinosaur, and this is Markarian 382. So what can we say about these sources? It seems that they, the X-ray production in these sources is not due, there is no component from the Baire production, but actually we have to take into account the fact that the plasma can be hybrid, so that there can be the tail of the non-thermal electrons that can reach the high temperature that are needed to for the Baire production. So also in these sources, actually, the Baire production can play a significant role. Moreover, they have also very high optical depth. So we can say that we can expect a low coronal temperature from this kind of sources, especially because they are super Eddington accreting, hyper Eddington accreting sources. So that can be the base of the jet of the outflow that have a pretty high optical depth that connect also as a corona. So what's next? The analysis of these sources includes also the analysis of the soft energy band, so the warm absorbing component and the soft excess component. So the next step will be the detailed analysis also of the soft energy components. And we would like also to analyze the variability property of these sources because they're pretty interesting. And we would like to extend the sample, of course, because as I said in the beginning, it is really important to study the super Eddington sources. There are not a lot of them, actually. There have been a lot of improvement in the theory, but not in the observation. And also we have a new simultaneous XMM and NuSTAR observation of the dinosaurs. So we are digging and we hope to find something very interesting. So stay tuned. And I will leave my conclusion here, and thank you for your attention.
Question?
Hi, very nice talk. Have you ever looked into applying the same analysis or a variation of it to other super Eddington sources like Galaxies maybe?
Yes, I am focused on AGN, but yes, can be also something interesting to do to expand the sample.
Other questions? There was sort of a question in the chat, which sort of dinosaur would fit best? Is it the Brontosaurus?
Yes.
Okay, if we have
no more questions. Let's take Alicia again. Our next speaker will be Francesco Sini, talking about X-ray corona, constrained with spectropolarimetry with NuSTAR and XP.
Am I supposed to do something? No? Yeah. It's the wrong slides. Yeah, okay. Okay, thank you. So good morning, everyone. Yes, so today we'd like to talk about the X-ray spectropolarimetry for AGN in particular. So a new perspective enabled by a very interesting and significant synergy between IXP and NuSTAR. So first of all, very briefly, to recap, the point of this idea is to constrain the geometry of the hot corona in accreting compact objects, in particular in AGN. The hot corona is the region that produces the X-ray emission, comptonizing the optical UV photons from the accretion disk. From spectroscopy, we can constrain the physical parameters of the corona, in particular the temperature and the optical depth. However, the geometry is pretty much left unconstrained by the spectral data, which are not really sensitive to geometry. So geometry is unknown, and so it is the physical origin of the corona. For example, the corona could be a slab sandwiching the accretion disk. It could be more of a spherical blob, for example, placed on the symmetry axis of the system. Or it could be, for example, an outflow like the base of jet, and then have rather a conical shape. So in any case, spectroscopy, as I said, is not really sensitive to geometry, so we cannot really distinguish between these cases, but polarimetry is, because the polarization signal measures essentially the deviation from spherical symmetry. And polarization measurements will become possible, are already actually now possible thanks to IXP that is being launched in December of last year. And we'll provide the first X-ray polarimetry measurements for AGN, thus constraining the coronal geometry. For bright objects, the minimum detectable polarization of XP in its bandpass, which is 2 to 8 keV, is roughly 2% with an exposure of 500 kilosecond. So having this new instrument, first of all, we want to simulate what is the expected polarization signal for AGN, and in particular, we focus on radio quiet and unabsorbed AGN using a Monte Carlo code, MONC, developed by Zhang et al. 2019, that calculates comptonization spectra in Kerr space-time, so taking into account all relativistic effects. And first of all, what we did was to set the physical parameters consistent with one of the first IXP target for first year MCG 52316, which is a very bright, X-ray bright civet one. So the results are, in a nutshell, contained in this plot. So in the upper part, you can see the polarization degree plotted here against the cosine of the inclination angle of the system. So for this lab geometry, we find the largest polarization degree up to 10%. For the conical geometry, we have an intermediate polarization degree, while for the spherical one, we have clearly low polarization, even below the minimum detectable. And in any case, at least for MCG5, given the constraint that we know for the inclination of the system, it will be quite possible to, well, to say something, at least to constrain the geometry in this object. And even if we look at the polarization angle, again, we see a clear difference between the different geometries. So a 90 degrees difference in polarization angle between the slab case and the other two. So this is also quite constraining, provided that we can have a preferential direction in the sky plane for the source, like in the presence of a radio jet or a ionization cone, as is present in MCG5. Very similar result we obtain if we plot these two the physical quantities as a function of the energy now in the IXP bandpass 2 to 8 keV, assuming a given inclination. Against lab cone sphere, as you see, are quite well, relatively well separated. Concerning, however, I mean, why there has to be a synergy between IXP and spectral and spectroscopy instruments such as NuSTAR? Well, spectral information is actually crucial to interpret the polarization measurements. For example, in this case, we have two completely different power laws with photon rings of 2 or 1.6. So a completely different spectral shape in the NuSTAR bandpass. And this produce completely different polarization signal, like the polarization degree, as you can see, is very different between the two. And it would not be easy, let's say, to put a good constraint on polarization based only on the IXP spectrum, which is, I mean, on a limited bandpass 2 to 8 keV. So having NuSTAR is really important here. And well, very similar cases also for the spherical geometry. Again, if we set different spectral parameters, we end up with really different results for the polarization signal. Just to say a few words, what I said, of course, was I mean, focusing on AGN. However, Monk also gives the opportunity to simulate what happens in low mass X-ray binaries, for example, black hole low mass X-ray binaries. This is a work recently submitted by Zhang et al. In this case, the main difference is that I would say, I mean, apart from the geometry that can be, I mean, a little bit different with respect to the one for AGN. However, the main point is that in black hole binaries, of course, the disk emits X-rays. So the first scattering here really plays a major role, meaning that even in the spherical case, we expect some significant polarization, possibly. This is an example for a moderately inclinated source. In this case, the cone is actually the base of the jet with the gamma 4, produces a very high polarization degree, more than 20%. But even the spherical geometries here, the one which is, again, in this case is in outflow, and in the second case is an orbit, produce anyway a quite significant polarization degree. So this is also very interesting case study. Similar, I mean, also for neutron star low mass X-ray binaries, Monk has the capability to perform this kind of simulations. But I'm not going to go in detail on this because tomorrow Romana Mikushintova is going to talk about it. So please see her talk. Okay, so I think I can just leave my conclusions. I want to stress once again that it is very now exciting moment because we can start building very, very interesting results, putting together polarimetry and spectroscopy thanks to this to the synergy between IXP and instruments such as NuSTAR. So thank you.
Okay, questions? Is that a hand up? on Zoom, Dan's turn.
I was just clapping, eagerly awaiting the actual results.
If you're speaking, we don't hear you. Questions from the audience? A question, would AGN be easier in a way to distinguish with polarimetry in the harder X-ray, having polarimetry in a harder X-ray band?
Sorry, you mean? I didn't hear you what the mask.
Oh, sorry. For AGN coronal geometry, would it be easier to distinguish things in a harder band, having polarimetry in a harder X-ray band?
You mean if we had the polarimeter in the hard band or something?
All the way in the NuSTAR band or something?
Means less photons. So, I mean, we need quite high flux and many photons to distinguish probably things. So I think
as many photons as you like.
Yeah, I mean, this band is probably better also because it is less contaminated, for example, by the reflection component that can increase maybe the polarization degree, but with the 2.8 kV band, we really can see the continuum.
Thank you. Any other questions? If not, let's take the speaker again. And we have one more speaker remotely. Mayra Gonzalez Martin is going to present on AGN torus reflector and its connection to mid-infrared dust emission. You have the connection?
Hi everybody, can you see me? And can you hear me?
Yes,
hi everybody, at this very early morning from Mexico, it's like 6:10 in the morning today. I'm gonna present you on the AGN obscurer and how it can be inferred from the X-ray reflection component, and also its connection with mid-infrared dust continuum emission. I have to say that I'm just a presenter of this talk, while most of the work have been done in a large collaboration. Some names here. Among the names, I'm going to highlight my own students, Jafet, Ulises, Natalia, Cesar, and the one that I want to highlight the most is Donahi Esparza Redondo, who did most of the work that I'm presenting here. She already finished her PhD thesis and she's working in Canary Islands right now. So the hope of this collaboration is to try to understand the geometry, distribution and location of this obscurer and its plausible evolution along the duty cycle of the AGN activity. We want to understand whether it is wind-like, torus-like, disk-like, if the distribution is patchy, smooth, or a combination of the two. And we also want to explore the location of this obscurer. And all of this, we wanted to study it in an evolutionary way because we believe this should be changing over time along the duty cycle of the AGN activity. And in fact, we have found some evidence in favor of that. For instance, at mid-infrared, we have found that high luminous AGN tend to present more dusty winds, while at the lower luminosity, they tend to present more dusty torus-like geometries. So, and the way to do it is there are several technical ways to study this obscurer. I grouped them into 3 categories. One is time domain, the second one is imaging, and also spectroscopy. I'm showing you here a beautiful interferometric image taken with Matisse on NGC 1068, done by Violeta Gámez Rosas and colleagues. But I'm gonna focus most of my talk. I will talk a bit at the end of the talk about this object, but I wanna focus all of my talk on the spectroscopic analysis because it's the one that can be provided for a large collection of objects, and because it's less restrictive from the observational point of view. So if we want to infer the properties of this obscurer from spectroscopy, what you have to do is to assume a certain geometry. composition and distribution, like a toy model, that you put inside of a radiative transfer code to produce an SCD library. And this SCD library is what you compare with your real data to tell if your toy model is in fact can describe the data, and also through spectral fit if you want to infer, or at least try to infer, the parameters involved in this SCD library. And this is something that have been done at both X-rays for using the reflection component for the gas, and at mid-infrared for the dust, using the continuum dust emission. However, nobody has tried to put together both tools at the same time, and this is certainly needed because neither of the two wavelengths can do the job by themselves. In order to illustrate that, I'm showing you here a pioneer work done by Cristina Ramos Almeida in 2014, and some other colleagues. I was also involved in this collaboration. What we did is to try to infer the minimum set of data that is required to fully describe this. In this case, was the Clumpy Torus model. What we found is that at least we need N1 spectroscopy plus near-infrared photometric points. And in fact, these photometric points are very difficult to get because at near-infrared there is a huge contamination from the host galaxy. In a subsequent paper, we studied not only this Clumpy Torus model, but a bunch of models, including not only torus-like geometry, but also this one is including this plus a wind model. We use synthetic spectra in a set of instrumental setup, including even future James Webb observation, to try to understand if we could distinguish between the models using mid-infrared or near-infrared spectroscopy analysis. And we found that in fact we can distinguish among most of these models using only mid-infrared observation between 5 to 30 microns. However, when it comes to the determination of the parameters, this is very difficult. What I'm showing you here basically gives you the larger the color area is, the larger the error bars of the parameters that we estimate from the synthetic spectra. And what you are seeing is that, for instance, in this plus win model, which is the more complex model that we have with 7 parameters involved, neither of the combination of instrumental combination can reach to a conclusion on the parameters within a certain error bars. And this can be worse because, in fact, at mid-infrared and near-infrared, as I was saying, there is a lot of circunuclear contributors that make the analysis worse. In a recent paper by Zhao, Markowitz, and Buchner, they did a similar analysis with synthetic spectra, but now at X-rays with a bunch of X-ray reflection models. And what I found is that using Bayesian evidence, they can certainly distinguish between the models, but with only if they have sufficient energy coverage. They prefer the combination of XMM and NuSTAR. However, as long as you go to lower luminosities, and my wonder is that it might be an issue with the circunuclear contributors in these objects. I'm going to leave it like that, just point to Natalia's and Jaher talks tomorrow, because they have been doing a terrific work trying to restrict this reflection component in such a low luminosity systems. And when it comes to the parameters, let me say that I believe this is even worse at the X-rays, because the photon index, even the photon index depends on the model used. And we also knew that there is an internal degeneration among these parameters, so this is very difficult to get the parameters only at X-rays. And with all that in hand, our idea was to combine infrared and X-ray data on the hope that both structures are coming from the same component, so we can produce a comprehensive picture of this obscurer to try to better, and also to try to better constrain the parameters of the model by fixing some of the parameters that are in common in both at both wavelengths. For instance, an obvious parameter would be the inclination angle toward the observer. We did it in a sample of 36 AN, 15 CF1s, 21 CF2s, with speed cell data at mid-infrared and with NuSTAR, of course, data at X-rays. The models that we use are 4, 2 at X-rays, 2 at mid-infrared. We select these models because are the ones that have a clear contour path at both wavelengths. So in particular, what we are testing here is a clumpy torus model and a smooth torus model. And the first thing that we did is to try to understand if we could distinguish between the smooth and the clumpy distribution at each wavelength separately. And what we found is that indeed the mid-infrared is very good at it. We can distinguish between the smooth and the clumpy distribution in almost all the objects except for 5. However, when it comes to the X-rays, this is much worse. In 14 objects, we couldn't distinguish between these two models. And this is something already Zhao and colleagues suggested, that we need to combine NuSTAR and XMM Newton in order to improve that. But anyhow, what we wanted to do is to study the complexity of the torus. And for instance, from this kind of analysis, we can study the distribution of the material. Either it's smooth at both wavelength or clumpy at both wavelength, or it could be a combination of a smooth and clumpy. And the result that we got is that indeed a smooth distribution of gas and dust is a good representation of less than 25% of the object. Much better work is done with the clumpy distribution at both wavelengths. Almost 60% of the sample can be understood as a clumpy distribution at both wavelengths. However, the best combination is with almost 70% of the object is the smooth distribution of gas at X-rays plus a clumpy distribution of dust at mid-infrared. This is the first time something like that is proposed. We also, as I was saying, we also wanted to know the location of this obscurer, and for that what we did is to look for, in the literature, to look for NH variation, column density variations. If the objects present such a kind of variations, what we believe is that the source must show a clumpy distribution, and these clumps should be close enough to the accretion disk to move fast enough to produce such a short-term variations. Otherwise, either there is no clumps in the inner part of the system, or the distribution is smooth in the inner parts. So among our sample, we found that 15 are non-NH variable, equally split into type 1 and type 2 AGN. 8 are NH variable, mostly type 2 AGN, but also a couple of type 1 AGN. And what I wanted to show you is that this is in a full agreement with our X-ray model selection, in the sense that all the 15 non-NH variables are nicely fitted with a smooth torus distribution, while all the 8 NH variables are nicely fitted with the clumpy torus model. So at least we are producing a self-consistent picture. And another thing that we wanted to explore is the thickness of this structure. We found that it is thin at both X-rays and mid-infrared in only 3 cases, all of them interestingly type 1 AGN. A thick structure is needed in both wavelengths for 10 objects, equally split into type 1 and type 2 AGN. And there is a mismatch between the X-ray results and the mid-infrared results for another 10 objects. This could mean that of course, that the medium that is producing the X-rays is not the same that the one is producing the mid-infrared, but another solution would be that it is too complex the complexity is too high. And in fact, this is something Donna did for her PhD thesis very nicely. She tried to put the minimum combination of gas and dust, able to explain all the sample. And she found that at least she needs 4 combinations of gas and dust for type 1 AGN, and another 2 combinations for gas and dust for type 2 AGN. So the torus geometry is not a single one, as it was initially assumed for the unification at ABS. Of course, this is something that should be left in the past for many, many reasons. But look at this picture, it's very complex. So let's leave it in the past. But what we can learn not only from what we can fit, but also what we can poorly fit. Kind of 30% of our sample cannot be fitted at both wavelengths with these simple models. There are several aspects to claim here, and some related to the signal to noise of the data, but I wanted to show you or highlight a couple of them. For instance, the geometry that we haven't tested so far is the dusty winds. We know these winds are important in infrared to explain the dust. In fact, they are needed to explain the brightest sources. But unfortunately, we don't have an X-ray contour part of this model to test with. And also, I wanted to point out that maybe the geometry is much more complex. In order to show you or convince you about that, I'm going to show you a particular example, a very famous object, NGC 1068. This is a work done by one of my students, Cesar Victoria Ceballos, published this year. He tried to fit mid-infrared data to this object, to several models, and none of them were producing good fits. What he did is to produce new SED libraries, and the best fit was obtained with a combination of two concentric tori. And in fact, this is pretty similar to what it was obtained also this year from interferometric analysis, where Violeta Gámez Rosas and colleagues found that at least they need two components of dust. And in fact, I wanted to highlight that this is what it was. It is completely consistent with what it was obtained by Bauer and colleagues already in 2014 using NuSTAR data, finding that they need at least two reflection components for this particular object. So just to conclude, I strongly believe we need new SED libraries. Not only complex geometries, also consistent results at X-rays and mid-infrared SED libraries at both wavelengths, so we can test real data. And from the observational point of view, for sure we need James Webb that will provide good sensitivity or great sensitivity and great isolation capabilities to really isolate the nucleus from the host galaxy and to test these kind of models. And from the X-ray point of view, what I believe is that we need the combination of NuSTAR with high spectral resolution data from these microcalorimeters that are coming, because the resolving power will allow to resolve the convolved compton shoulder, and this might help to descend among models too. So the future is bright, and I leave it like that, and I take any questions that you might have.
Thank you very much. Do we have questions from the audience? We'll wait for questions from the chat as well. In the meantime, a question about, I know the situation is relatively complex, but are there any semi-clear trends that you could point out within going towards low luminosities, for example, in parameters of the torus?
Well, from this analysis, we couldn't go further toward lower luminosities. The luminosity range is quite narrow. We know from mid-infrared and also from some studies at X-rays that there is, for instance, a lack of a torus below certain luminosity. So in my opinion, what is happening is that it's contracted toward the center as long as you move toward lower luminosities. And at some point, it collapses at the center, and the torus is not longer there.
Thank you. Last minute questions before lunch. Another question.
Hi, yes. I saw that you were mentioning some discrepancies in covering factor, or well, torus thickness between the infrared and the and the X-rays. Do you see any sort of discrepancies between torus thickness, as in density, torus density, between the two wavelengths?
About the opacity of the torus, what we found is that, in fact, this is something already mentioned in several papers before, that the ratio between the dust and gas is much lower than much higher than for the interstellar medium. This is what we found. And this is completely in agreement with previous results. The point here is that we are measuring the opacity of the torus itself, while in previous results, what they did is to measure the extinction. But it's completely consistent, yeah.
I see, thank you.
Any more questions? If not, then let's thank the speaker again.
All right. So I think we're ready to get started with the AGN Census Part 1 surveys session. So, Donamar, are you there? Can you?
Yes, I'm here. Can you hear me?
Yes, great.
Yes, thanks.
All right, well, welcome, and tell us all about AGN surveys and population studies.
Thank you. Hi, everyone. I'm Tunima Tasnim Ananna. I'm a postdoctoral research associate in Dartmouth College in Professor Ryan Cox's group. First, I want to thank the NuSTAR team for inviting me here to give this review talk on AGN surveys. Today, I will also be talking about population synthesis models, which we make using these surveys. Since this is late afternoon, I'll try to keep things very simple, but I apologize because it won't be very short. So given this audience, I will just briefly touch on why X-rays are ideal for studying AGN. So we know that copious amounts of X-rays are produced on the corona above this accretion disk. Because of the penetrating power of X-ray photons, X-rays are a more unbiased tracer of AGN than optical and UV photons. And because X-rays are relatively uncontaminated by galactic sources, it is also a more efficient tracer than infrared wavelengths. These aspects of X-rays will help us produce an unbiased and complete census of AGN using X-ray surveys. A census which will include rare luminous AGN, for which we have to probe very wide areas, and obscured AGN, which are more difficult to detect because a lot of the light coming from them are extinguished. So let us look at the nature of the obscuring matter and its impact on X-ray spectra briefly. So it is widely accepted that clumps of gas and dust are distributed in a roughly toroidal shape on a scale of about 10 to 100 parsecs from the center of the AGN. Depending on the underlying population and our line of sight, we will get varying levels of obscuration and transmission from the torus. The primary emission from the corona has a power law form with photon index gamma and a cutoff energy, exponential cutoff energy. This emission is further reprocessed by reflection from the accretion disk and attenuation by gas and dust in the torus. Now, let us look at how much the spectra changes due to obscuration. So these are some physically motivated model spectra of AGN at different obscuration levels. So this blue line, so this x-axis here shows the photon energy and the y-axis shows the energy flux at these photon energies. The blue line here shows the spectra of unobscured AGN, which is in the range log NH 20 to 22. And then this green line here is absorbed quantum thin AGN, which is log NH 22 to 24, so 100 times more obscured than these objects. And this red line is quantum thick AGN, which is even 100 times more obscured than even this green line. So you can see, in order to detect this heavily obscured AGN, we will either have to move to higher photon energies or we'll have to go very faint fluxes in these softer bands. Now I will show you some of the typical energy windows in which we observe AGN. So this is the soft band, 0.5 to 2 keV. Then this is the hard band, 2 to 10 keV. XMM and Chandra observe the universe in these two bands, and NuSTAR observes the universe in 3 to 79. So it is better suited to see this heavily obscured AGN compared to the softer bands. To constrain all parts of AGN spectra, we need observation from the same survey fields using different energy bands. For example, this is an extra mosaic of NuSTAR observation in Chandra Cosmos field. These extragalactic sources shown here, here have XMM Newton, Chandra, and NuSTAR observation covering a wide energy window. This is UKID's ultra deep survey with these three, with these three instruments, XMM Newton, NuSTAR, and Chandra. Other extragalactic surveys of NuSTAR include ECDFS, Extended Broad Strip, Hubble Deep Field North, and NuSTAR Serendipitous survey that we heard about earlier today. As a resolution power of previous high energy extra observatories were limited, and NuSTAR led to 100 times increase in sensitivity for observation over 10 keV, it greatly improved how well we can sample obscured AGN and study their spectra. Redshift evolution can be difficult to constrain because obscured AGN are harder to sample and because spectral parameters may also evolve, and it is difficult to get sufficient photon counts, especially for higher redshifts obscure sources. NuSTAR allowed us to constrain AGN spectra in a larger energy window and at higher redshifts, and probe the evolution of AGN more completely and gain a better understanding of the structure of the obscuring torus and accretion physics. To summarize, extra surveys help us sample AGN more efficiently and study the torus, accretion, and AGN evolution. And high energy focusing telescopes, NuSTAR, contribute significantly to our understanding of these aspects of AGN populations. The way we combine all these different samples that we see using extra observatories is by using extra luminosity functions. My cartoon image of what these functions are is that it tells us how many AGN there are per co-moving volume of the universe at different redshifts. But at different redshifts, these AGN are not identical. They're divided into different luminosity bands. So that adds an extra dimension. And then there is also an added complication of AGN because intrinsic brightness of AGN is also attenuated by obscuring tori. So we add an extra axis obscuration. Now a luminosity function tells us at each redshift and in each luminosity bin, how many AGN reside at different levels of obscuration. So essentially it is a 3D function of AGN space density. That combines data from different surveys, takes into account the energy window and flux limits of each survey. This data can be combined using either a Bayesian or a frequentist approach. Maximum likelihood estimator is a good example of a frequentist approach, whereas Bayesian approaches allow us to apply physically motivated priors on these functions. To constrain these functions, we need three quantities: redshift, intrinsic luminosity, and obscuration, and the uncertainties associated with each of these quantities. While spectroscopic redshifts tend to be very accurate with little uncertainties, photometric redshift algorithms usually assign a full probability function, such as the one shown in the lower panels here, of how the redshift of an object may be distributed given its photometry. In such cases, taking this uncertainty into account becomes important, as it can be even more dispersed than the example shown here. The other two observables are similarly affected by uncertainties, but maybe not to such a high extent. For example, this is a spectra of an object that has XMM Newton, NuSTAR, and SWIFT pad data, and it shows that there is degeneracy between obscuration and photon index and obscuration. The object has a lot of X-ray data associated with it, but without high energy data or enough photon counts, the uncertainty may become considerable and should be treated carefully when doing population studies. The uncertainty in intrinsic luminosity can be dependent on the uncertainty on the other two observables. Now let us look at these observed quantities from a survey and how observed quantities and how it can be used to constrain a model intrinsic population. As I promised to keep things simple, I will just explain what this means. So this just tells us for the ith object, what is the probability of seeing that object given given a set of parameters that defines the underlying population. Then we multiply the probability of all of these different different objects observed in a survey, or we add up the log of these probabilities and try to maximize it. And in doing so, we optimize the parameters that define the underlying population. My comic image of this is, so this is how these objects are distributed. The observed objects are distributed in 3 dimensions. And we try to find the parameters that define the underlying population from which this energy band and these flux limits should have observed this observed population. However, because of the measurement errors we have just discussed, just taking individual discrete points will not be sufficient. What we really need to consider is probability clouds associated with each of these objects by convolving the errors and integrating over all of these observed quantities. So by considering the selection effects and measurement uncertainties carefully, we should be able to find the true underlying distribution. Once we have a model, how do we verify that these calculations? How are these models useful? So it is necessary for such functions to be able to synthesize population statistics, such as the cosmic X-ray background. So what is the cosmic X-ray background? In 1962, when the first X-ray rocket experiment was carried out, a background of X-ray radiation was detected, but the origin of the emission was unclear. The source could have been emission from a lot of distant sources or diffuse emission from some galactic hot gas. This is what the X-ray background looks like. The x-axis is energy, and the y-axis tells us energy flux per solid angle as a function of this energy. In the 70s, it was confirmed by the first all-sky surveys that this emission is isotropic. And in the 80s, several studies showed that the shape of this emission is consistent with AGN spectra. Since then, multiple X-ray observatories have been used to resolve this emission to individual sources, and a lot of luminosity functions have been synthesized to reproduce this cosmic X-ray background using X-ray luminosity functions. As shown in this plot, this is the galaxy contribution below 100 keV. We expect that the rest of this contribution comes from AGN. At some observed energy, if we add up all of the contribution from all the AGN galaxies from for the entire duration for all time, then we should be able to produce the cosmic X-ray background. The peak of the CXB is consistent with Compton hump of heavily obscured AGN. 100% of the CXB has not been resolved by any of our observatories yet, especially in the harder bands. And so the shape of the CXB is usually considered an indication of hidden population of heavily obscured AGN, which are yet to be detected by our current flux limits. And the extra population synthesis models also indicate this to be the case, which I'll present in a few slides. So first, to calculate predicted cosmic X-ray background from a given luminosity function, we need to integrate over redshift luminosity and log image, and we have to take into account the space densities, which comes from the luminosity function, as well as the spectra, which is why it's actually really important to be able to constrain whether or not these spectral parameters are evolving over time. So most X-ray luminosity function constrained prior to the NuSTAR era were calculated using softer bands less than 10 keV, except for the WEDA model, which also takes into account the BAT 9-month survey. So these are the regions in luminosity redshift space covered by the WEDA 2014 model. And after all of these luminosity functions were constrained, all of this new data became available. So as a result of this new data, in this region of the luminosity redshift space, we had more data by the time I was trying to reproduce these results, this new data using the older luminosity functions. So in a number count plot, this new data corresponds to this region. You can see that this is the flux limit is getting fainter. So as we observe deeper data, we go to fainter fluxes. And you can see that all these previous luminosity functions were struggling to reproduce this end of the number counts. The same thing happened with Compton thick counts from Chandra Cosmos Legacy Survey, as you can see, because we had so little data on Compton thick populations before. As we go deeper and see rare objects or more objects, models start to fail. Similarly, SwiftBat also had more data from the 70-month survey, and the number counts from that survey was also not very well reproduced by the previous models. So we formulated a neural network to vary the space densities in luminosity obscuration beams to find out where exactly are these missing sources, and found that these discrepancies mainly occur due to underestimation of space densities of Compton thick objects. The luminosity function that resulted from this analysis does take into account all of this deep data, and we found that it fits the newer constraints better. It's the back number counts. This is the Compton thick counts. Now, more data was also available from NuSTAR, from the extragalactic surveys and CXP measurement, and we use that to show this resolve fraction of sources within the CXP as a function of energy here. So these data points here show the fraction of the CXP that has been directly resolved by NuSTAR. Before the launch of NuSTAR, our understanding of CXP above 10 keV came from wide field observatories with limited resolving range. So only about 1% of this was resolved in the 2 to 16 keV band range, but due to NuSTAR, it went up to above 30%. At softer bands, XNM and Chandra were doing better as they had more resolving power, and they resolved up to 80%. So due to NuSTAR, we were really able to resolve a lot more of the CXP in higher bands. This red dotted line shows the fraction of AGN that should have been resolved according to the WEDA 2014 model using NuSTAR, whereas our 2019 model matched this date was in much better agreement with the data, with the observations. These data points say the green. There are NuSTAR stack signal of Chandra sources, and again, you see that this data is better matched with our model, which predicts a higher Compton thick fraction than previous models. So these are some observed indications from higher energy windows, deeper data, that there must be more heavily obscured Compton thick AGN than we previously realized. To resolve CXP beyond 30% and beyond this 2 to 16 keV window, we need sensitive high energy extra observatories such as the proposed mission HMXB. So going back to the data used to constrain our 2019 model, newer deeper data is available now. For example, this is EFIRS data. It goes to higher redshift and to very faint luminosities. This is where we had the CDFS MMS data that was already included in our models. This is again the back 70-month data, and this is NuSTAR serendipitous survey data. This is where ART-XC is observing right now. And this is the area that HMXB will observe, but at a higher energy window than eROSITA. And we will be able to constrain spectral parameters better and study their evolution, which is currently a huge piece of the puzzle about agent population. As you can see, eROSITA, with the EFIRS field recently released some data, and here is a luminosity function measurement. There's only one data point here at redshift of 6.5. All of these luminosity functions that have been constrained they are within a redshift of 5, so they have to be extrapolated to try to match this. And we find that our model is still in good agreement with IFED's results at redshift of 6.5, which is reassuring for now, but we do need more data to really constrain this population at higher redshifts. And hopefully future missions will allow us to do just that. So after looking at how we constrain these models, it might occur to us that whether or not these models are purely phenomenological, or if it even gives us any physical insights about what's going on close to AGN. Recently, we have used SwiftPAT 70-month survey data to not just constrain the extreme luminosity function, but also intrinsic mass function and intrinsic Eddington ratio distribution function of AGN. And we also divided up the AGN in obscured and unobscured samples because this higher energy window of FAT did a great job of making such a great unbiased selection of both of these samples. And we found that while the mass function of obscured and unobscured AGN are not significantly different, their accretion rate distribution, so this gives us the Eddington ratio on the y-axis, and this gives the space density in the y-axis and Eddington ratio in the x-axis. And this blue line is for unobscured AGN and red line for obscured AGN. And you can see that at low Eddington ratios, these two functions are very similar, but at higher Eddington ratios, they deviate significantly. So the geometric unification model might actually apply to this low Eddington ratio n, but at higher Eddington ratios, it's probably a temporal relationship because the radiation pressure is so high over here. The dust and gas gets blown away. So this ratio of type 2 to type 1 probably tells us how much time AGN spend in each of these phases at high Eddington ratios. So we also found that Eddington ratio distribution function are independent of mass, but dependent on level of obscuration. Which is what we showed in the previous slide. So if you just take unobscured AGN and we divide it up in 2 bins of mass and independently constrain the Eddington ratio distribution function, we see that the shape is very similar to in both bins, and it's the same for obscured AGN. So these are the physical insights that we got from constraining functions like this, the intrinsic statistical function that define AGN population. So it goes beyond just the phenomenological aspects of constraining populations statistically. So to summarize, X-ray surveys are highly useful in understanding AGN populations, and NuSTAR has been particularly valuable in probing obscured AGN. Different AGN surveys different part of luminosity, redshift, and obscuration space, and together they allow us to constrain intrinsic AGN population in the form of luminosity function, mass function, and Eddington ratio distribution function. These functions in turn reveal physical insights about AGN. Parts of the AGN population are still poorly sampled, and therefore future surveys such as HMXB are needed to provide us with better constraints on obscured AGN population, better constraints on AGN spectral parameters, and better constraints on evolution of the obscured fraction. So before I finish, I would like to congratulate the NuSTAR team on the 10-year anniversary, and thank you again for inviting me and listening to my review talk.
Thank you. Questions for Tanema? Go to the mic, or if you're online, raise your hand or ask a question in the chat. Right, Dan Stern has a question. Are you there, Dan, or do you want me to read it?
You could read it.
Okay. So I don't know if you're on Slack, Tanema, you can read it, but I'll say, do you want to go ahead, or I can read it to you?
Can you go ahead and read it to me? I'm just, yeah.
So for everybody else, can you comment on how the type 1 to type 2 ratio varies with AGN luminosity? Receding torus would imply that the most luminous AGN are generally unobscured, but various IR selected surveys find luminous, heavily obscured AGN which typically aren't detected in X-ray surveys?
In our SUVPAT sample, we see that the difference in the Eddington ratios are much more stark than the difference in luminosity space. So the XLF doesn't show as much of a variation as the Eddington ratio distribution function does. We are actually leaning towards the radiation regulated unification model, given our results, than just the receding torus model, because then we take into account both the mass and the gravitational effects, as well as the radiation pressure, rather than the receding torus model, which just takes into account the luminosity. So I think considering mass in this case was important, and then we could see that the real difference might be coming from Eddington ratio and not from luminosity. So our paper on this is actually on arXiv now. So if you want to look at the differences in mass bins as well as the Eddington ratio bins and luminosity bins, you can look at it. Also, I can talk about it in person.
Thanks.
Thanks.
Any other questions? I had a quick one about, so in your modeling, or maybe I missed it, but are you using the CXB itself as a constraint on the models?
Yeah, for our 2019 model, we did use CXB to vary. So what we did with the CXB is we just found using the neural network all of the different populations that could satisfy the CXB, and then we use the other constraints as a kind of a validation test to rule out the ones which would not fit them. So that's how we can use CXB as a constraint. Yes.
Okay, great. Thank you. All right. Well, thank you very much.
Thank you.
And we can move on.
Thank you very much.
Okay, so next up is Mislav. He will tell us about nearby heavily obscured AGN from the first decade of NuSTAR.
Almost. I would first like to thank the organizers for having me here. Celebrating it was fun. 10 years of NuSTAR. My name is Mislav Balokovic. I'm a YCA Prize postdoctoral fellow at Yale University. When I put up this title for the talk, I wasn't expecting to end up in the surveys session, so I'll change that slightly. From nearby heavily obscured AGN to nearby obscured AGN survey that happened for the most part in the first 5 or so years of NuSTAR. The motivation for that is, as Trima just presented, is the fact that we observed the cosmic X-ray background. We sort of know by now that it's due to obscured AGN at higher redshifts. That's a good idea. But we obviously don't understand all the details and all the obscured AGN population. We do know from surveys that were available even before NuSTAR that obscured AGN comprise an even bigger part of the population early on at higher redshifts, like this result from Buchner et al. From Chandra surveys. Furthermore, the motivation is also that we don't really know what obscures AGN. I'm not putting up the classical unified model of AGN, where the obscure is very simple torus. A torus can be a range of things. Some of them are sketched here, others are listed. I don't think we're quite sure whether all of this exists in every AGN, or whether some of these structures exist in some AGN. Maybe some of them are more common in some regimes, but it is important to know and understand what is potentially obscuring the majority of the AGN population. In order to solve that or address the issue, NuSTAR, this was one of the big things for NuSTAR, the primary mission, to directly observe and resolve the obscured AGN population as much as possible. And for that, there was a wedding cake strategy with a narrow and deep field. There was more than one of those. Just listing one of the first ones here. There was a medium wide, medium depth survey in the cosmos, and then also wide and shallow survey that used the Swift-BAT catalog, all skies catalog, and also other observations where you get a bright point source for pointed observation, and then you get all the rest of the field of view to look for serendipitous sources in the background. And George Lansbury worked on that, on the first iteration of that, and also mentioned today at the poster session that we now have doubled the depth, and you can see that in his poster here. So the NuSTAR Swift-BAT survey I thought was a particularly neat idea, where the Swift-BAT survey has already identified about 1,000 or so brightest hard X-ray sources in the sky. And so by observing those, you get unprecedented quality of spectrum in the hard X-ray band, whereas you have a lot of the field of view still available here, for example, as serendipitous detection for looking for background AGN at higher redshift. I was myself more interested in detailed modeling of the spectra. And so this is one of the first quantum thick AGN that I worked on, where really is the continuous band between 3 and 79 keV, covering both the iron K alpha band around 6 keV and the Compton hump at around 30 keV is what enabled some of these constraints on the reprocessing spectrum that comes from scattering, fluorescence, and absorption in the structures that we love to call the torus simply. In order to focus more on obscured AGN, where NuSTAR can make a big contribution, in my thesis I focused on obscured AGN, optimizing the survey so that we get a representative subsample of Swift-BAT AGN. You can see over here, oops, how they're distributed in the space of luminosity versus redshift. So it goes up to about 0.1 to their local AGN. They are modestly luminous. And the other 3 histograms are showing just that the parent sample and the final sample that we had in 2017 match well. And so that the subsample is representative of a bigger subsample of Seaford type 2 AGN, or for those who like the technical term in the Swift-BAT catalog, that would be class 5. One note here is that because it's based on Swift-BAT, the survey has all the biases and all the incompleteness that the Swift-BAT survey has. We love to think that it's unbiased against obscured AGN, but it's not quite like that. It's just the least biased of all other X-ray surveys. In the end, we gathered about 130, 140 AGN, depending on subsample. In parallel to NuSTAR observations, Swift-XRT also observed in order to provide a broadband X-ray snapshot for all these AGN. And there were 2 aims for the spectral analysis of those data. One was to phenomenologically just see what the variety of spectra is, and you can see some examples here on the right side. For that, we used the simple phenomenological models that have power law continuum, a high energy cutoff, some component representing reprocessing, iron K alpha line as well, and some scattering at the low energy end. And this is mostly for comparison with previous work that used those models, and unfortunately doesn't have any constraining power on what the shape of the torus or geometry of its properties are. But fortunately, even when NuSTAR was starting out, there were already models for obscuration structures, the torus, that had more of a geometry and more detailed properties.
And I'm actually going to focus more on that in the rest of the talk, except that I'm going to mention, so this is a bunch of distributions of these spectral parameters for the simple phenomenological model, but I'll focus on one in particular that I think is relatively unique and hasn't been repeated in other studies. And it's about the high energy cutoff in a sample of obscured Swift-bat AGN. It is very difficult to get constraints for obscured AGN because they have very narrow overall band over which you can even see the coronal continuum. And so very often you get partial constraints, lower limits on the high energy cutoff. These three panels are showing the degeneracy in the plane of gamma, the power law index versus the high energy cutoff. And you can see that this is just a lower limit. These other examples are better constrained. And so all in all, we obtained 45 full constraints and 69 partial constraints. There's also some constraints that are degenerate in the sense that even if you assume that they have a relatively high energy cutoff, you would, depending on just fluke of statistics, you end up with finding a very low high energy cutoff and also very hard gamma. So those are typically degenerate results that we have taken out of averaging in finding the median of the population. So over here you can see the full constraints in black, the red are the partial constraints, and then these degenerate constraints tend to be here at the very low value. So if you were to just average the best fits, disregarding that, you would conclude that the median or average energy cutoff is around 150 kV. But actually, if you take into account all the partial lower limits, then you end up with something like closer to 300 kV. Plus, there's a big systematic uncertainty on that, amounting roughly to 100 kV. Oh, this is also showing how it works. So this is cumulative distribution function. When you do not disregard the degenerate constraints, then if you take just the best fits of the non-degenerate constraints, you end up with a higher median energy cutoff. And then when you also take into account the lower limits, it sort of shifts another 100 kV or so towards higher values, much above the NuSTAR the NuSTAR band itself. Then I'd like to cover a bit more on the X-ray torus modeling. We have had some models since before NuSTAR, and we have many more now. I've myself been involved in this one, Boris 02, where I've made a 3D ray tracing code in a parametrized geometry that provided more flexibility than we thought the existing models provided. This model is publicly available. It's very easy to use. And I'm happy to talk to you in more detail about that model in particular. There are some new features that I'll be putting out soon. But the caveat with these models is that, and also other models of the same sort, is that they have no physical scale. So they don't ultimately help us to determine exactly what the structures doing the obscuration are, but they do give us some constraints on the geometry. So constraints in some of the main parameters, this is from that paper that presented the model. You can see the torus covering factor versus torus average column density. Just 4 examples for different AGN. It's not in detail important what they are. They are different AGN. Some of them are type 1, type 2. The point is that they land in different parts of the parameter space, and therefore that tori that they have are distinguishable from one another. Of course, one has to be aware that this is just one model, and we're still far from figuring out how robust these constraints are, and there are many systematics to take into account. Some of these recent works have focused on how much we can trust constraints from single models, and it was also mentioned today in the talk by Omera Gonzalez Martin. Sorry. You see a range of different constraints on the right side here. Some of the constraints for these AGN from the Swift-bat survey are pretty good. They're up there on top, and then going down. This is the same parameter space, torus covering factor versus torus average column density. Those on the bottom are significantly less useful constraints. But if you have a lot of them, then on a population level, you can do things like plotting the average column density or median column density as a function of luminosity, which is shown here. You can see individual constraints, and then you can see the running median in blue, and it's 68% uncertainty in gray. So this was first time done in the X-rays, even though it has been done before in the infrared torus modeling. And there are interesting implications for this non-monotonic relationship, because at the low energy, at the lower luminosities and at high luminosities, radiative pressure or feedback is maybe in two different regimes, be either dispersing the torus or not being able to support it. There are already theoretical ideas about that, but I'm not going to go into detail on that for now, because I think we have a lot more work to do. I think we can improve this in a number of ways. Last week at the XMM meeting, an obvious way to get better data is replace XRT short observations with better data from XMM or other soft X-ray instruments. Of course, having more NuSTAR data with multiple epochs, and also in the future HMXB would immensely help. The real point is to have really broadband data. So XM certainly helps. All other soft X-ray instruments help, but it's about the band. You have to have covered the iron alpha band and the Compton hump in detail to be able to handle to have some handle on the torus parameters. We can improve and extend both luminosity ends, and I'll briefly talk about that in a few slides. And we can also use multi-wavelength constraints or all of the above, ideally. So I'll talk a little bit about the low luminosity part, but there's a session on low luminosity AGN tomorrow. It seems that perhaps these low luminosity AGN have tori with less column density average and higher covering factors. And to check that, a student, master student of mine, Samantha Cabral, looked at NGC 1052 with all of the available X-ray data to date, which includes NuSTAR and well, basically every X-ray telescope so far. And the model, not to go into too much detail, has a variable continuum, variable line of sight column density, which is slightly ionized, but the constant torus through all epochs, and also no relativistic disk component, which has been identified before in the same data. We don't see evidence for that now. So this sort of modeling would get you relatively stringent constraints on the parameters of the torus, which are relatively, they're not Compton thick, and it's a high covering factor torus. But then we also looked into radio data, and on very small scales with VLBI for AGN that have double-sided jets, you can sometimes see a band of absorption. So this is the jet, very close to the black hole. This is where the black hole is, and this dark band over here, where the spectral index is a different value, is where there's a lot of line of sight absorption towards against the jet. And so it turns out that a model somewhat like this, instead of the uniform model that I was talking about before, if you put in a gradient in the direction of the jets, you can reproduce basically the same X-ray spectra. That sort of model fits equally well, but then also fits the profile across this jet. So this is opacity, it's function of offset from the black hole, and these gray points are the opacity, so cross section through this, and then these lines here are from this sort of density distribution that went into producing an X-ray model. The neat thing about this is that unlike the X-ray model, which doesn't have to have any sort of scale, this directly sets the scale in terms of physical parsecs. So that immensely helps because we can hope to have that in the X-ray band. Just to wrap up and connect again to the deeper surveys, I've recently been focusing on going to a higher luminosity, higher which necessarily means higher redshift, trying to get more better spectra for quasars in order to model them in the same way that we have modeled Swift-Bat AG in the local universe. And those are, the obscuration may not be necessarily the same origin as in the local universe. It could be more contributing, galaxies could be more contributing to the obscuration. And also those objects would be closer, even though they're not really representative of cosmic noon quasars, where radiative feedback from AGN was important for galaxy evolution, or more so than today. And so in some very recent data, this is 50 kilosecond observations with NuSTAR over here, and then XMM and Chandra data for quasars with redshift 0.3, 0.4, 0.7, where we tried directly model in the spectrum the reflection strength, or which describes the contribution from the torus, and that's shown in purple here against the data from NuSTAR Galactic surveys from Zapacosta et al. 2017, where this parameter is strength of reflection versus luminosity, and there's an expectation that would go down because of evolution, but for now we don't directly see that. But I think it will be interesting to put this into context of broader other surveys with NuSTAR that we'll do soon. This is work from my undergraduate student Tristan Fever. And so I think I'll just leave my summary up because I think the time is up. And thank you all for attention.
All right, questions?
So you talk about finally being able to constrain the physical scale of the torus. And I know you can find a lot of like documents talking about how wide the torus is expected to be. Has anyone, or is it possible to constrain how high it would be?
You mean in terms of thickness?
Mm-hmm.
I guess, I mean, covering factor essentially is telling you about the thickness. So if there's a high covering factor to the torus, as long as things are not set in scale, distance scale, you can tell what the height is. But it's always in relative terms, unless you have measurements like these from VLBI, from small scale observations, where you can set one dimension and then compared to that you can set other dimensions as well.
Okay.
We have time for one more if anyone's got a pressing inquiry from his log. All right, let's move on. Thank you very much. All right. So our next speaker will be Peter Boorman. He's going to tell us about NuLANDS, the NH distribution, isotropic AGN.
Okay, so hi everyone. I'm Peter from the Astronomical Institute in Prague. And yes, today I'm going to be talking about the NuLANDS survey, so the NuSTAR local AGN NH distribution survey. So let's get on. Okay, so we've already had a very nice introduction from Tanima and Mislav into the CXB and why obscured AGN are essentially important for the growth of all AGN. But I just thought I'd try and set the scene somewhat with this plot. So essentially the CXB showing this stark similarity between a single AGN spectrum, where I've just colored it by the column density, And you can see that when you get to sort of Compton thick columns, you tend to see this very strong reflection continuum. That bears a very striking resemblance to the observed CXB. And from Tanima's work, the most recent population synthesis model essentially finds that within a redshift of around 0.1, which depending on what cosmological factors you choose, it roughly corresponds to 450 megaparsecs. Around 50% plus or minus 9 should be Compton thick. Okay. And so one question that we wanted to solve with NuLANDS was essentially, can we select a sample in some way that has a roughly equal probability of selecting an unobscured AGN and obscured AGN on average? Okay. And this is where NuLANDS was born. So in terms of hard X-ray flux limited selection, we heard from Mislav some of the benefits from hard X-ray flux limited selection, but also the limitations. So on this left-hand plot, I'm essentially showing the depletion in X-ray flux. So the observed flux you get from X-rays penetrating through a clumpy medium, divided by the equivalent flux from an unobscured geometry as a function of column density. Now, the specific color here just shows the thickness or the scale height of the torus in the model. And as you can see, that a very high percentage of the flux effectively escapes for any column density up to around 24.5, where you start losing a considerable amount of the flux above that value. And this is kind of reflected in the observed Compton thick fraction from the 70-month Swift bat survey, where essentially I replotted this data from Claudio's 2015 paper that shows that as you go out in further and further distances from the Milky Way, the observed Compton thick fraction decreases considerably. So in terms of trying to select a sample with unobscured and obscured AGN, roughly equal probability, we turned to mid to far infrared isotropy. Okay. So the underlying idea is shown in this cartoon on the left, where essentially you have the corona shown in purple and some sort of accretion disk. And the accretion disk photons effectively get absorbed by the dust surrounding the AGN, whether it be polar dust in the polar direction here or some sort of circumnuclear obscura, and then are re-radiated into the infrared. Okay, and in this sense, we sort of treat the infrared dust as a bolometer. Okay, so it sort of absorbs the radiation and then re-emits. And multiple surveys, I'm just showing one here from Daniel Asmus, have found that the anisotropy, when you look at the emission in the infrared, so this particular plot is with 12 micron nuclear luminosity, so really just the AGN component that's resolved from the best ground-based telescopes on Earth. And then the predicted intrinsic X-ray luminosity that you get after spectral fitting, the observed anisotropy between type 1 AGN in the optical and type 2 is only around a factor of 1.4. Okay, so it's roughly isotropic. But this is a X-ray talk, so where did the X-rays come in? Okay, so log NH is an X-ray derived quantity, and I just wanted to sort of showcase why NuSTAR is so vital for this. Right? So these are two galaxies that were selected as part of the local AGN survey, so laser. They're a little bit different, that selection is a little bit different to NuLANDS, but kind of comparable. And essentially these galaxies were selected as being candidate AGN. Okay, but if you take the observed X-ray spectra from the archive of these sources, both spectra are very consistent with just being collisionally ionized gas, typically associated with host galaxy emission. Okay, no presence of an AGN. But it's not until you observe with NuSTAR that you really see the AGN component come out. Okay, so in these particular sources, you see literally nothing until you get to the NuSTAR band, and because of the sensitivities, you really do start to see very strong Compton humps and very strong reflection features. Okay. So now a little bit about NuLANDS. So the NuLANDS survey was, the selection was chosen to be as simple as possible, effectively, to try and require as minimal bias corrections as possible. So I'm showing the selection on the left. And essentially all we did was took the IRAS point source catalog and threw away any upper limits at 25 and 60 micron. Okay, so all the sources are reasonably well detected at 25 and 60 micron. Then it's an extragalactic survey, so we also threw away sources within some region of the galactic plane and also the Magellanic Clouds. That's the whole selection. The idea being that in this final sky map here, there's going to be a lot of non-AGN because we've only made a flux cut at the infrared, but of the AGN that are selected with C-foot luminosities, it should be roughly equal probability between selecting a type 1 AGN and a type 2 AGN. Okay. But we want the AGN, right? So we have to perform some sort of classification and make a choice. So this is effectively our classification before we went on to observe with X-rays. So the left shows the color selection that we used originally proposed in de Gruyp et al. In 1985 to select sources as warm IRAS sources. And the selection is just such that you look for spectral slopes between 25 and 60 micron that are indicative of a warm shape. Okay, so peaking at slightly warmer temperatures than a typical non-AGN, which I'm showing in this sort of pink color, peaking at longer wavelengths, so cooler temperatures. Okay. And this should also preferentially select AGN relative to sources that are maybe dominated by host galaxy emission in the mid to far infrared as well. Then we searched the literature and also performed some updated optical spectroscopy of the remaining sources to find a sample of type 1 AGN and type 2 AGN, where the type 1 AGN are just classified based on conventionally the broad lines that you observe in permitted lines in the optical spectrum. And then the obscured classification was just from BPT diagrams, ratios of forbidden to permitted line ratios. Okay, and then we observed with NuSTAR, and the entire sample is 122 sources. This is not all of those sources. These are just the sources that weren't detected by SwiftBat. Now, what I've done is I've roughly ordered them by signal to noise in the rows, okay, and also chosen a different color depending on the optical classification. So the first thing you probably see is that the vast majority are C-foot-2s, okay. The second thing is that as you decrease in signal to noise, there are a lot more sources that have this classic reflection spectrum shape, strong ion lines and Compton humps, right? It's kind of showing that these missing AGN are essentially, or at least a large chunk of them should be heavily obscured AGN. So what we then did was took all of these individual X-ray spectra and fit with as many different models as we could. Okay, so the original idea was that we have type 1 AGN, we have type 2 AGN, we have narrow-line C-foots, etc. So we wanted to encompass all different AGN types, but also we wanted to effectively overcome any geometry-based degeneracies that might exist from choosing one model or one geometry of the torus over another. So we used conventional models like a PEXRAV that have been used in the past for unobscured and obscured AGN. We've also used more spherical models such as BN sphere, so where you just have a perfect sphere surrounding the source, and also Boris, which was made by Mislav. And then we've also used conventional torus models that are literally shaped like a torus, but also where you can decouple different components to parameterize some sort of clumpy torus. And then we've also, in recent years, more and more exotic shapes and geometries have become available, things like clumpy models, but also things like warp disks, to see if any of the sources might preferentially be fit by any of these geometries. And it's a very wide parameter space. I had to narrow it down for this talk. But one thing I really wanted to flag up was this idea of geometry dependent degeneracies. Okay, so Mislav mentioned this in his talk. But essentially, it boils down to two models can reproduce a spectrum with roughly similar spectral components, right? So this brown reprocessed continuum is roughly similar in both plots, but purely based on the geometry itself and the individual models or the individual simulations that we use to derive the models, you end up with a different column density depending on which model you choose, right? And this isn't just for column densities, this is for all types of parameters. And this is why it requires typically sort of careful fitting when you're doing this in a uniform way. Okay. Yes, and also to flag up that there are two posters at the back there that sort of discuss this in more detail by Christina Kalova and also Devanglia, who is not here, but I'll be presenting his poster tomorrow. So the main event, if you will, for NuLANDS, this is essentially the NH distribution that I'm showing on the left. Now, we generated this in a bit of a different way. Instead of assuming one geometry for all of the individual fits, we found every single geometry that was favored as being reasonable based on the Bayesian evidence. And then all of those, we Monte Carlo sample a given model combination, right? And then use a Bayesian hierarchical model on each sample many, many times to try and reproduce the spectrum and effectively increase the uncertainties between the individual bins. On the right here, I'm showing the full result from the hierarchical model. Because this is a model that we're fitting, all of the bins also depend on each other in some sense. And so you can see the individual relations between individual bins. And one thing that's quite nice that's self-consistently reproduced is this relation here between the Compton thin fraction and the Compton thick fraction. The idea being that if you have some models such as this, the source I just showed, so 76, 74, where you have one solution that might be Compton thin and one solution that might be Compton thick, this model should encompass both of those errors self-consistently into the model, which is why we see this anti-correlation, this idea that if you have more Compton thin sources, you must have less Compton thick sources. But of course, this started out by trying to avoid biases, so it's very important to also check any possible new biases or different biases that might be affecting our results. And what this is effectively showing here, so in our classification, we use the mid to far infrared and also the optical, okay? So for the obscured AGN, we use the narrow line region. That's effectively what the BPT is using when you use line ratios. And so what we did is we plotted the O3 luminosity, which is a good tracer of the narrow line region, as a ratio to the both of the infrared fluxes that we used for our selection, and then separated them into all of their optical types. You may not be able to make it out, but the gray sources are just CFIT 1.9s because they can typically be CFIT 1s or 2s, depending on which source you choose. Then what we did, much like the NH distribution, was fit just a simple Gaussian model, a population distribution to the CFIT 1s and the CFIT 2s separately. And in this upper panel, I'm showing the cumulative distribution from those plotted on top of each other. So you can probably see that they're indistinguishable. Right. And so the idea is that we're selecting in the infrared. There may be some bias going on there. For instance, if we were preferentially selecting dusty systems, the infrared flux might be higher for certain systems, typically for, say, obscured systems and CFIT 2s. We would not necessarily expect the ratios to agree so well between CFIT 1s and CFIT 2s if there was a strong bias in that sense. One final result I just wanted to flag up was the variation with distance. So previously we saw with hard X-ray flux limited selection, this drop up to 100 megaparsecs, but this is plotting this Compton thin versus Compton thick degeneracy as a function of distance, just in 3 distance bins now. And as you can see, the Compton thick fractions are not just agreeing very closely on their median values, which are these squares in the distributions, but also the uncertainties themselves are extremely similar for each distance bin, which is kind of showing a promising result that this is selecting out to 200 megaparsecs in some sort of uniform manner. Okay, so in terms of some take-home points, hopefully I've shown that NuLANDS is complementary to hard X-ray flux limited selection, essentially combining the ability to select sources irrespective of host galaxy contamination in Compton thick columns, combined with these sources that are Compton thick obscured, is extremely powerful. And also based on the optical classification, there is some difficulties in a sense that if the sources have preferentially large-scale host galaxy dust, some of the optical classifications may be affected. But in that case, in a conservative sense, this is a very sensitive lower limit to the overall obscured fraction. Also, just to reiterate that geometric dependent degeneracies are important, right? When you make an assumption on a model, you may get slightly different results if you use a slightly different model. And then lastly, I hope it's kind of obvious, but I just wanted to reiterate that NuLANDS would not have been possible without NuSTAR. with the improved sensitivity around the Compton hump, it's really a vital mission for trying to differentiate between geometries, but also pinning down the column density distribution even into the Compton thick regime. And with my last few moments, I know we're talking about HMXB tomorrow, and I know there's been some discussion recently, in particular, about Athena XIFU, but I really wanted to show the power in one plot, which is very difficult, but the power of the synergy between the two, if it was ever possible. The idea that accretion disk reflection, which we've heard a lot about in the past few days, but also distant reflection, which I've been talking a bit about. But essentially, these two things should be existing simultaneously in every source, right? And so the ability to study the geometry of the obscura at high Eddington ratios or in very bright Seifert-1s, for instance, could potentially be possible with the combination of high spectral resolution in the softband with XIFU or CRISM, then also improve sensitivities up to 200 keV with HMXB would be remarkable. So with that, thank you for listening, and I'll take any questions you might have.
Great. Do we have any questions for Peter? Go ahead. Feel free to put any questions in the chat.
You had a lot of really beautiful figures and logos. I was wondering how you made them.
Python.
Even say the logo for the new thing, the one on the left.
Oh, sorry. Yeah. So this, well, somewhat embarrassingly, this was actually just in Keynote.
Oh.
Yeah, but it was based on the MyTorus model, and then I sort of drew over it by hand. Yeah.
And the figures in the middle.
Oh, yeah, that was in PowerPoint. Yeah.
Okay.
Yeah,
I'm just impressed.
Thank you.
Thanks for your beautiful talk. I was wondering, how did you say that there is a difference in the parameters depending on the geometry of the torus? So how this is reflected in terms of the coronal parameters, like the photon index and the high energy cutoff?
Yes, that's a very, very good question. So I failed to mention. Yeah, so I didn't have time to mention how we're doing the X-ray sets, right? So, oh, I'm no longer, could I share my screen? Yeah, so what this plot shows is just a series of simulations, but what we did was use nested sampling instead of conventional Liebenberg-Marquardt fitting. And so the powerful thing with this is that you predefine your prior parameter space, and then you essentially condense down to a region, the idea being to avoid local minima. Right? But yes, the parameter degeneracies, like the key important ones, I would say are, for this survey in particular, intrinsic luminosity and column density. And you can see the sort of shape that you get with decreasing signal to noise, which I'm showing on the left. So as I redshift this source further and further away, the luminosity decreases until you even get 0 counts. But the idea is that if you have a good enough background model, you know how bright the source should be. And so the degeneracy may get quite strong. You can see this sort of shape here, but even for 0 counts, you know that the source can't be brighter than a certain level. And so that's why this region of the plot, i.e. completely unobscured and quasar brightness, never fills in, right? Because you know that that can't be the case. So yes, the degeneracies are there, but we can also self-consistently reproduce what can't be there, if that makes sense. Yeah.
Thanks.
Thanks.
So just a curiosity, when you computed the O3 luminosities, is there any contribution from the host galaxy, and did you take that into account, and how?
No, so that's a very good question. No, we did not. We used archival values. They are dereddened, but I don't know if the host galaxies are included. But I think I think the key thing with so if I go back to that plot. Yeah, I think the key thing is that if the host galaxy is included or not included, it's included or not included in Seifert-1s and Seifert-2s. Right? So the idea is that on average, it looks like they are consistent. But yeah.
Thank you.
Thanks.
Hi, very nice talk. I would have two questions for you. One was like for the beginning of the talk, you were talking about the covering factor as a height scale.
Yeah.
And I was
Visible? Maybe?
yes, yeah. But in this case, you're using UX-Columbia, so that would be the covering factor of the inner, like.
No, sorry. Yeah. So this is Tor sigma in that model.
Oh, but then there's sigma tells you like what is the dispersion.
Yeah, effectively. Yeah. Sorry. It was more of a like roughly some sort of scale height because it's the thickness. But yeah, it's more of the dispersion. Yeah.
Like it's telling you like more, the dispersion of the cloud. So it's not telling you the the thickness.
Yeah.
Okay, that was the first question. And second, when you're talking about like the NH in this case is the line of sight NH.
Yes.
Okay.
Yeah. So yeah, this
It's
was
not
with a
the
fixed
average.
inclination, so it was always obscured.
Okay. All right.
Yeah.
Thank you.
Thanks.
And we have a question from Zoom, Tonema.
Oh, hi, Peter, a great talk. So I was wondering if the absorption function that you show in one of your slides close to the end, given the selection effect, should we consider it almost close to the intrinsic absorption function? Or is it closer to, is it still an observed one?
Yeah, that's a great question. So actually, thank you for asking that. I have a slide. So yes, one of the things that we're considering is this idea that if galaxies on average have some large scale host galaxy dust, then in the optical, the narrow line region should be broadly obscured, and that can affect your classification. So we might be losing, for instance, some Seafoot-2s on average, right? And so one question that we had from the NH distribution is this difference between the predicted fraction of, or your predicted fraction of 50%. And the idea that that I was trying to investigate, it's definitely work for a future project, is essentially how many of the optically classified normal galaxies, so in the corner here you can see type H2, how many of them actually need to have an AGN to replicate their broadband SED. And these 6 I've just sort of cherry picked because they all seem to require, with AGN fits, some sort of significant contribution from AGN heated dust, which kind of indicates that maybe we are missing some Seafoot-2s.
Oh, okay, I see. Yeah. Okay, so it's like it's still not an intrinsic log NH distribution, but it's close.
So it should be intrinsic. The idea is that this is completely directly observed. It's there's been no bias corrections, but it's just there's this potential thing that might be limiting it to a sensitive lower limit than
I see. Okay. All right. Thank you so much.
Thanks.
All right. Let's thank Peter again. All right. Our next speaker is remote. Zhao, and they will talk about the NuSTAR extragalactic survey from James Webb in the North Ecliptic Pole. So take it away.
Thank you. Can you hear me well?
We can hear you. Go ahead.
Okay. Thank you so much. So thanks to the organizer for giving me the opportunity to talk about our recent work here, and also thanks for organizing this wonderful and fantastic meeting to celebrate NuSTAR 10 years NuSTAR. And today I'm going to talk about the NuSTAR extragalactic survey of the James Webb telescope on the North Ecliptic Pole time domain field. And I'm sure Zhao, my supervisor, is Francesca Chivano, and here is the collaborators. And so what is the JWST NEP time domain field? So the JWST time domain field near the North Ecliptic Pole is a GTO target, which was allocated 47 JWST hours. So the North Ecliptic Pole is in the JWST continuously viewing zone, and the time domain field in the NEP is a region which has the minimum extinction and obscuration in the whole NEP. So the field will be observed 4 times, and starting in this year's August, every 90 days to study the time domain astrophysics in the field. And on the right, you can see the footprint of the JWST and the Hubble and the Chandra observation in the field, and overlaid on the Hubble Space Telescope observation. So the interest from the broad community make this field a comprehensive multi-wavelength campaign, and from the hard X-ray NuSTAR to the alpha radio wavelength, and most of the observation are on the data are on hand, and some are still in progress. And in addition to the photometry from the X-ray to the infrared and radio, there are also some spectroscopy study of the field as well. And here, the NuSTAR NEP time domain field was desired as the other multi-wavelength survey to observe the NEP time domain field simultaneously with JWST. And as we know that JWST was supposed to launch in 2019, so the NEP was proposed to NuSTAR to simultaneously observe JWST in cycle 5, and it was awarded 700 kiloseconds in cycle 5. And we know that the launch was delayed, so the field was proposed again to NuSTAR in cycle 6, which is a 2-year multi-year observation to try to simultaneously observe with JWST. However, the JWST was delayed again, and finally it was launched in last year December, and so we proposed the field to the NuSTAR in cycle 8 this year, and was awarded about 850 kiloseconds. And now we finally can observe this field simultaneously with JWST and other multi-wavelength surveys. And now I want to introduce a little bit of our cycle 5 NuSTAR NEP survey, which was observed in 2019 and to the 2020. So the observation was performed in 3 epochs, and in total of 681 kiloseconds. And on the right, we show the mosaic of the observation in 3 to 24 keV. And in total, we detected 33 sources in different energy bands, from the soft band, which is 3 to 8 keV, to the hard band, 8 to 24 keV, 8 to 16 keV, and 16 to 24 keV, and also in the full band, which is from 3 to 24 keV. And interestingly, there are 4 sources which are only detected in the hard X-ray band, which is above 8 keV band. And those 4 sources are very good candidates for the competency KGN. And I will talk about them more in the later slides. So here I show the sensitivity curve of the NuSTAR NEP survey in cycle 5. The survey cover about 0.16 square degree, and the sensitivity curve is shown as the red on the left figure. And we also compare with the other previous NuSTAR extragalactic survey and the NuSTAR serendipitous survey of the 14 months. And as you can see that the NuSTAR NEP survey, although has only 0.7 milliseconds due to its small coverage area, it makes it one of the deepest NuSTAR extragalactic surveys so far. And so here I want to introduce some results about the source properties of the NEP survey. On the right, I show the number counts of the hard X-ray detected sources in this field as the yellow field region, and we also compare this with the previous NuSTAR survey and also the population synthesis models prediction, and our result is pretty consistent with the previous surveys and the population synthesis models, and we reach even deeper fluxes in the hard X-ray band as labeled in this blue circle. And also, we compared the hard X-ray flux of the sources detected in the NEP field with the optical flux of the and on the right, we plot the sources detected in the NEP field as the red and blue, and compared with the sources detected in the Cosmos NuSTAR survey. And the dashed line cover the region where is the empirical AGN locus, suggesting that sources in this region are most of them are AGN, and the sources below this dashed line are supposed to be galaxies or stars. And as we can see that most of the NuSTAR detected sources are in this AGN locus, suggesting that they are AGN. Most of them are AGN, and some of them may be even heavily obscure, that they have larger X-ray flux, but very faint optical magnitude. Here I show the redshift and the hard X-ray 10 to 40 keV res frame luminosity of the sources detected in the NEP field. That out of the 33 sources, 11 sources in the field have either spectroscopy or photometric redshift, and they are labeled in blue in this redshift and the luminosity plane. And we also compare with the other previous NuSTAR extragalactic survey detected sources, as in different circles and squares. And we also compare the result with the Swift-Bart detected sources. And as we can see that the Swift-Bart samples very different Ricci region on the redshift and the luminosity plane compared with the NuSTAR extragalactic surveys. And here I want to talk about the interesting competence thick AGN subsample of in our detected sample. So we estimate the obscuration of each source detected in the field using their hardness ratio by the hard flux minus the soft flux divided by the hard flux plus the soft flux. And the hard band is defined as the 8 to 24 keV, and the soft band is the 3 to 8 keV. And on the right, I show their hardness ratio, and the red and the black lines shows the compton thick and unobscured threshold, and the dashed line is the as the hardness ratio depends on the redshift when estimating the obscuration. The dashed line is when the redshift is at 0, and the dashed dot line is the threshold when the redshift is about 0.7, which is the average, or the median redshift of the sources detected in NuSTAR extragalactic surveys. And as we can see that those 6 sources which have only the lower limit of their hardness ratio, they are very good compton thick AGN candidates. And but we need to know the redshift to really confirm whether they are compton thick AGN or not. So here we compute the compton thick AGN fraction of the sources of the NEP survey. The right point, the right square, the right star is the measurement from the NEP survey, and this large uncertainty is due to the fact that only 1 or 2 the compton thick AGN candidates have the redshift measurement, so which makes the a large error bar on our measurement. And we also compare with the previous NuSTAR actual galactic surveys, their observed Compton-thick aging fraction, and also compared with what Swift-Bath measured at higher flux. And different colors lines shows the prediction from the population synthesis models. And we find that it's really important to have the redshift measurement, although it's difficult, but we are lucky now to have the access to the JPath data. So the JPath is an optical observatory in the Spain, which features with a large field of view, about 2 square degree, with 56 narrow bands photometry, from 3,000 nanometer to the up to 9,000 nanometer in optical. And the JPath NEP field was observed, and the data was on hand now. And the observation, the survey reached a flux with a magnitude about 23. And on the left, we show an example of the observation, the JPath data of a NuSTAR detected source. As you can see, the emission line are very good shown on this low resolution spectrum. I mean, this 56 narrow bands photometry data. And so with this data, we can perform the SED fitting and to get the source properties, and also importantly to get the redshift of those NuSTAR detected sources. And the work is on progress with the postdoc in our group by Moshe Asadi. And now I want to introduce a little bit about the NuSTAR NEP survey in cycle 6, which has in total 880 kiloseconds taken in 2 years observation. And the observation was taken by in 4 epochs, and with the same pointing, so that it aims to study the variability of the actually detected sources in this field. And there will be one more observation simultaneously with JWST in August. So we are still looking forward to the new data set, and very exciting. And so to reach the deepest sensitivity, we combined the cycle 5 plus cycle 6, 3 years NuSTAR data in this field, which is in total 1.5 million seconds. And we perform the source detection. We find 51 sources detected compared with the 33 sources detected in cycle 5 alone. And as you can see on the right. And here I show the sensitivity curve of the combination of cycle 5 plus cycle 6, which reach 1.6 times deeper than the cycle 5 alone, and makes it the deepest NuSTAR actual galactic survey. And we also compare with the most recent 18-month serendipity survey, as here in the black, which shows that the NuSTAR NEP survey is still the deepest actual galactic survey so far. And with this great data set, we can probe the log-on-log-S in even deeper hard X-ray flux, as you can see here. And the result shows that the log-on-log-S, the observed log-on-log-S in hard X-ray band is still consistent with the previous observation, and also the population synthesis model predictions. And with the NuSTAR 8 cycle data, we expect to explore even deeper flux, but more importantly, we expect to detect more sources so that we can shrink the uncertainty on the log-on-logs a lot, so which can better to constrain the number counts. And in NuSTAR cycle 6, we also propose 20 kiloseconds NuSTAR XMM observation simultaneously with NuSTAR to firstly better locate the NuSTAR detected sources, and also to better study the soft X-ray band variability of the source in this field. And we got 3 epochs of XMM observation, and we lost 1 epoch due to the strong background flare. And on the left, I show the XMM data set, and from 0.5 to 10 keV, and with the footprint of the JWST, HST, Chandra, NuSTAR, and the infrared optical observation. And the XMM observation covered almost all the NuSTAR and the other observations field. And in total, we detected more than 370 sources in the 60 kiloseconds XMM observation. More than 75% of these sources will have the JPass counterparts, suggesting that their optical counterparts has has flux above, lower than the 23 meg. And we're also aiming to study those sources, the property of those sources, and measure the redshift of these sources. So the ICD fitting is ongoing by Michigan. And to really understand the source property and to confirm the redshift of the sources in the field, we also propose to observe the field with the MMT hectospec for measuring their spectroscopy redshift. And the proposal was accepted recently, and we will get more than 200, the spectroscopy redshift of 200 sources in the field. And to not only study the source property, but also to try to calibrate the redshift measured from JPass, the photometric redshift. And also here I show the sensitivity curve of the XMM NEP survey compared with the other previous XMM and Chandra surveys in the soft 0.5 to 2 keV band. And the figure was adjusted from the Marchesi 2020 paper. And we are here. And in NuSTAR cycle 8, we also propose another 3 epochs of XMM observation simultaneous with NuSTAR. So the final sensitivity will be even deeper. So I want to introduce a few case study in the field. Firstly, is the most.
Sorry, hold on. The time is running out. Can you wrap up?
Oh, sure. So the brightest source. Firstly, I want to introduce the brightest source in the field, which is the a fly spectrum radio quasar, has redshift 1.44 with radio loudness 400, and the black hole mass is about 2.5 billion solar mass. It has 20 epochs of X-ray observations with NuSTAR, XMM, and Chandra, so that we can study the X-ray variability of the source with very good cadence. And here I show the X-ray light curve of the source, which show no pattern of variability, but very significant, but it's significant variable. And on the upper, I show the optical light curve of the source, which shows that it was continuously becoming fainter in the last 4 years, which is very different from the X-ray behavior, which might be due to the X-ray, maybe from the jet. The optical emission is from the accretion, which is confirmed by the SED fitting of the source. But we find a very interesting thing is that the millimeter flux of the source is 10 times lower than the flux predicted from the ICD fitting. So there may be very strong flux variability in the millimeter band. So we propose it to the SMA monitoring of the source, and we got 6 observations to monitor the source in the next few months. So another strongly variable source, maybe I need to skip it. And the very important, the prime goal of the NuSTAR NEP survey is to study the hard X-ray variability. So we recently developed a pipeline to analyze the X-ray variability in the NuSTAR NEP survey, and which is very similar to what is applied to the Chandra source catalog. And so we analyze, we compute the possibility density function of the net count rate of each observation, and to calculate the probability that is variable. And we are going to apply this pipeline to all the NuSTAR detected sources. And thanks to its multi-epoch observation and a very good deep observation. And in the last 1 minute, I want to say that the HMXB, which is the hard X-ray probe concept, is significant to the hard X-ray extragalactic survey, with its 10 times effective area and angular resolution than the NuSTAR, and much lower background than NuSTAR, that it will achieve more than 10 times deeper in only 200 kiloseconds than what we have now, 1.5 milliseconds NuSTAR NEP survey. And if we have 1.5 milliseconds HMXB, it will detect more than 100 times more sources than the current NuSTAR NEP detected, and will constrain the log and log S more than 25 times deeper in flux and in the hard X-ray band. And it will also study the hard X-ray variability more efficiently and more better. And this is the outlook. Thank you so much.
Maybe time for one quick question if there is one. It's time for coffee, so let's go do that. And thank all the speakers in the session one more time.
Okay, so next session is going to be related with nearby galaxies. Our first speaker is Wick, who is going to present characterizing the hard X-ray binary population of M31.
All right. Okay, well, sorry, I know you'd much rather have coffee. I might too. So I want to tell you a little bit about our NuSTAR survey of M31, the nearest galaxy to us. It's like the Milky Way. And we've heard a lot about X-ray binaries this week, a lot of wonderful talks. So I don't really need to introduce things, but in case you are out on the beach, X-ray binaries are made from some accreting object that's compact, so either a black hole, a neutron star, or a white dwarf. When we look at other galaxies, we really don't observe, at least at hard energies, the CVs, so the white dwarf accretors. So it's really a focus on black holes and neutron stars, and we classify those as being high mass stars or low mass stars that are the donors that the compact object is accreting. So it's really tied to the star formation history of the galaxy. So why do we care about XRBs in general? I don't think I have to motivate it too much. The main reason is that they're cool, but that doesn't get grants. So other reasons are that they really do trace the history of star formation in galaxies, and cosmologically they're important in that they might be a substantial contributor to heating of the IGM early on. And we can't study those objects directly at high redshift because they're much too faint, but we can learn a lot about the ones that are more local to us, understand those populations, and then translate that to higher redshift. So, we want to learn about these populations, and black holes originate from more massive stars, neutron stars from somewhat less massive stars originally.
And it's those stars that really trace to the total stellar population. And so ideally, we would like to disentangle those from each other. So when we observe with Chandra or XMM Newton, we're really observing in an energy range where we can't easily distinguish what the compact object type is. So this is a standard color hardness diagram for black hole states. You have traces out of Q. You start out in the hard state in the blue, moves over to an intermediate state, which is here in the green, and then to the soft state, and there's a loopy loop and whatever. And neutron stars also move around on the diagram, although they tend to be more located here if they don't have strong magnetic fields, and then the ones with strong magnetic fields, pulsars, are pretty hard sources with photon indices of 1, and so they poke out a bit. But you just don't have really the ability to characterize those well with Chandra. You can really say that they're probably in this part of the diagram when you don't have a huge number of counts, and the hardband sensitivity isn't great. And so you really can't distinguish whether a source is a neutron star or a black hole. For that, you need information above 10 keV, which is what makes NuSTAR so great. So also, but it's not like we haven't been able to do anything with Chandra and XMM. Of course, you can cherry pick where you're looking so that you're looking at sources that are going to be dominated by high mass donors or low mass donors. So for example, the high mass ones are going to be associated with star formation because high mass stars don't live very long. And so they have to be in areas where you have active star formation going on. The lower mass ones, these are long-lived stars. So they're really just going to trace the total history of star formation in the galaxy. So they'll trace the old population. You'll find them in elliptical galaxies. You'll find them in the bulges of late-type galaxies. And then globular clusters, of course, are an old population. So they also host low-mass X-ray binaries, although they may not be the same population as the one that are in ellipticals in the field, because you have these dense environments, and so you can have the binary orbits changed by interactions, and so that could modify exactly what the population looks like. So if we look at M31 in particular, what's been done with XMM and Chandra, we can just count up the number of sources as a function of luminosity. And so I'll be showing a bunch of these luminosity functions. You have on the x-axis luminosity going fainter, and then we just count up the number that we detect. And so you can see here we can compare M31's globular cluster population of X-ray binaries with that in our own galaxy, and they look very, very different. So the Milky Way has many fewer luminous X-ray binaries in M31. And then if you imagine that, well, maybe the bulge population should be very similar to the globular cluster luminosity function. It's more similar, but it's not the same. It's a little bit flatter. You have more low luminosity sources. Now, if we look at Chandra's view of the bulge, you see a relatively consistent picture, which is this fit here. Although you do see, oh, I got an alarm for getting ready for my talk. There's kind of a steep rise here, 10 to the 38 ergs per second. And then you've got one source out here, which kind of flattens the fit out of the luminosity function. But you can imagine ignoring that one, or maybe that one doesn't exist, and then you have a very steep rise here. So what could cause that? One possibility, assuming these are neutron star accretors, then you're going to hit sort of the maximum mass of a neutron star, its Eddington luminosity, and then really you're going to run out of sources at some point. And this will happen at generally a few times 10 to the 38 ergs per second. So that can cause a steep rise as sources kind of bunch up here. So those are for low mass X-ray binaries. For high mass X-ray binaries, again, looking at M31. Now here, you want to eliminate the globular cluster sources because you're trying to only see the high mass X-ray binaries. So we want to see what's going on here. And if we, here there isn't a direct comparison with the Milky Way, but in this plot, this is showing the high mass X-ray binary luminosity functions measured by Swift and by RxCE here. And then it's compared with integral, although in the integral case here, they've specifically just made a luminosity function of the BE X-ray binaries, so the neutron stars, BE stars. But in general, you get just a power loss, though, often with a cutoff sort of at high energies. So seeing a bump like this is not really what we would expect to see based on the Milky Way's population. All right. So, the great thing we can do with NuSTAR is we can classify objects by their type. And we can't quite do it, at least not easily, with a diagram like this. We need to bring in that greater than 10 keV data. And when we do that, we can plot colors, so sort of a softer color versus a harder color. And in this diagram, these types separate. So really, above this line, you're looking at black holes, and below, you're preferentially looking at neutron stars. So you can really separate those from each other. And that allows us to ID whether a particular source is a black hole or a neutron star. Okay, so what does M31 look like with NuSTAR? So this is a nice press release image showing the deep survey that was planned by Ann Hornschmeyer. Oh, and I forgot to mention early on, much of the work you're going to be seeing is due to a grad student, my grad student, Hannah Fritze, so she deserves credit. But this was executed long before she showed up. And so what we can do is we can just look at these colors, basically, put them on the diagram, and then identify what these sources are. So this bright blue one here, this is consistent with a pulsar, and follow-up observations confirm that scenario, although we don't have pulsations, which would be the real kicker. But then we see, all of these other sources, these yellow sources here in the bulge are very much consistent with neutron stars, non-magnetized ones. And this is putting them all on the plot. And we see that from this survey in this particular location in the galaxy, we're really dominated by sources that are in the non-magnetized neutron star zone. And so we're really seeing a large fraction there. We do get a handful of black holes, and we also get a handful of pulsars. Now we can split this up by the location in the galaxy, so we can separate out high mass and low mass X-ray binaries from each other. And you see exactly what you would expect. So in the bulge, you're almost completely dominated by the neutron star population, the old neutron star population. In the disk, you still, in this case, have quite a few neutron stars, but this is where the black holes really live, and it's also especially where the pulsars are. And this is what you would expect. So if we look at here, this is a Spitzer 24 micron, so it's tracing star formation. You can see the rings, the star forming rings of M31 very nicely. And here I've circled in purple the pulsars, and they all sort of creepily follow the two arms here, although I wouldn't say that's necessarily statistically significant. And then in cyan here, these are the old neutron stars, and they're dominating the bulge. But we also have, here in the disk, a lot of globular cluster sources, and they tend to be the brightest ones. And so here, these highlighted in yellow These were published by Tom Macaron, and he argued, based on the NuSTAR data, that they were consistent with being neutron stars. There had been some suggestion that these sources were black hole candidates, which would be exciting because you do expect possibly all these interactions. You could have lots of black holes in globular clusters. They could merge, and this could be a mechanism for creating intermediate mass black holes in the center. But at least in these cases, that is not what's happening. So now if we look at the luminosity functions between the bulge and the disk, we can also see they look very different. And they look different in a way that's consistent with measurements in other galaxies. So again, you have this very steep rise in the luminosity function dominated by neutron stars. And then in the disk, here it's fit by a broken power law, but here we haven't removed any globular cluster sources. So it's not really a clear picture of high mass X-ray binaries. But in any case, if we just compare directly with what we see in the Milky Way, there's a broad consistency. So the slopes are kind of close, although they're offset. So the number of sources in the Milky Way tend to be higher in general. But there's general consistency here. And then again, just comparing the Chandra bulge luminosity function, it looks very, very similar to NuSTARs. Here, there's the luminosity break isn't at the same place, but the luminosities are also in different bands. So that's not necessarily inconsistent. So the problem with the disk survey from the deep observations is that we don't have enough high luminosity sources, really. We just haven't covered a very large area of the galaxy. And so we want to observe more. And so since the main mission we proposed for, and other people have proposed for observations, and so we have this smattering of other data that covers a larger fraction of the galaxy. And this is much shallower, about 10 times shallower, but we're able to pick up those bright sources. And we can classify this. So this is work Hannah has done. And interestingly, we see that these sources are generally, there's a higher proportion of black holes in here. So it appears that the region of the galaxy we chose for the deep survey probably biased the overall population that we were sampling. So these extra observations are quite crucial. And so now we actually have enough sources in the disk to be able to identify the globular cluster ones and remove them. And this is just showing the deep and the shallow surveys here. But so this is the combined luminosity function, which has some interesting features. But if we remove the globular clusters, which actually removes half of the total sources, then we get something that's a bit more similar to a power law. And this power law slope is around 1.8, which is actually quite consistent with all the previous work in the Milky Way. So it looks like the population now that we're seeing at hard X-ray energies, which is the same that we measure in the Milky Way. And it's not possible really to do this kind of work reliably at low energies. So you have to be at high energies. So here we can compare apples to apples, and we see that we do have apples. And then we can also look at the globular cluster luminosity function and compare that to what we see in the bulge. It's actually very similar, but the luminosity is different. So the globular clusters tend to bunch up at a higher luminosity, which is much more consistent with the Eddington limit of an accreting neutron star. And we can just compare that with the previous luminosity functions. And we see we get a cutoff here in M31 as seen by XMM, which is also what we see with NuSTAR. And we can parameterize that as well. And it's roughly consistent. So here so this is a sample from elliptical galaxies by Brett, who will be speaking later. And here you see the same basic trend. So everything looks quite consistent and nice. So what is next? So what we really want to get at is the relative populations of neutron stars and black holes. So now that we're kind of building that up, we can, instead of making luminosity functions that are in specific areas where you may have, a few extra low mass X-ray binaries versus high mass ones, but there, could be neutron stars or black holes. Now we can just create these luminosity functions based on those classifications. It's a little bit tricky because not all the classifications are significant, but we can do our best. And then we can compare the black hole to neutron star fraction to that we see in other galaxies that have been studied in Bulik 2018, where they mostly are looking at galaxies with the high star formation rates. And so they see the black hole fraction increase as you go to higher luminosity. And so it'd be interesting to see if the star formation rate is lower, if that holds. And then I will finish just saying that, it'd be great to get more coverage of M31. There's still a lot of the galaxy that's not covered. And in fact, the southern part, which we don't have a lot of data for, should have more bright sources. So it would be an excellent place to expand. But ideally, we would like more normal galaxies like the Milky Way and M31, but that's just not possible with NuSTAR sensitivity. So while we're here to celebrate NuSTAR, we learned that once we hit 550 kilometers altitude, that's it. So we need a next generation observatory. So if NuSTAR is the original series, I think we need a next generation to do even more. So thanks.
Thanks for this wonderful talk. So does anyone have a question?
Yeah, hi. Have you tried looking at the machine learning methods for classifying the Milky Way, the M31 sources?
No, we have not done anything fancy like that. Ideally, so what we've done essentially is to place the sources in our, really right now it's just in the color space, even though we should be using the luminosity dimension as well. And then essentially, based on the error bars, what is the probability, relative probability that it would be in one part of the diagram or the other. Now, the one difficulty of that is that we're using these underlying sources as a guide. They're in these colors, they're just 6 objects that we're using, but many observations from RxTE. And so it's not really well understood if there's anything weird or odd about those. We get nice separations based on those 6 sources, but I think there are lots of systematics there. So in terms of doing something more complex, I don't think we've had a lot of motivation to do that, but I'd be interested in talking about how we might.
All right, nice talk, Dan. My question is, how much of this field has multiple observations or observations that you can split up so that you can look for transitions along these diagrams? And have you found any interesting changes?
Right, so most of the shallow fields are just single observations, and so we can't really probe transitions over time scales longer than the observation or see any variability. I don't think there's any variability on sort of those 50 kilosecond time scales. In the deeper survey, they're made up of observations, on the order of 50 to 100 kiloseconds each, summing up to about 500 kiloseconds in general. And those were spaced out specifically so that, there was sort of a random cadence in about 9 months. And there's a little bit of variability in terms of the luminosity of the source, but in those fields, almost nothing in terms of state changes, which you do see in other galaxies where we have a few observations. But yeah, not in the survey.
Anyone else? Okay, so as we don't have questions on the Slack and Zoom, let's take again to our speaker.
And then we can have a quick coffee now.
Hi, good afternoon, everyone. I'm Jun Yang from MIT Cagliari Institute. I'm a postdoc. So I'm here to talk about the young black hole and neutron star system in the nearby galaxy M33 with the NuSTAR observations. Why do we study M33? Because it's a long distance, about 817 kilo/s. It's a relatively face-on orientation, about 54 degrees. And due to its active star formation, so M33 is an ideal target for study the actual galactic high mass X-rays. These NuSTAR observations can help us to constrain the distribution of accretion states for low luminosity, high mass X-ray rich populations. As you already know, accreting neutron stars and black holes are about 10 to 6 kilometers apart. And generally, the neutron star and black holes have a radius about 10 kilometers. And their accretion disk is about 10 to 5 kilometers. Their luminosity is about 10 to 36 to 10 to 38 erg/s. And their disk temperature is about 10 to 7 Kelvin, mainly emission X-rays. We use the NuSTAR observations. This table shows the observations in our survey. We used 6 observations. This shows the coordinates and observation time, and in total we have 600 kiloseconds exposure time. And on the left, the upper right corner is an infrared image for this galaxy. The red rectangular is a field view of the 6 NuSTAR observations. They are in 3 fields. Each field has 2 observations overlapping with each other. And we can say in the middle is the brightest source in this galaxy, which is an ultra-luminous X-ray source M33X8, which is our particular interested in this source. And then we can say M33X6, and this is X7. First, we searched for positions in this source, and we found some periodicities from this observation from 2 simultaneously detections of instrument A and instrument B. On the right is a period diagram. So this is a power spectrum. The x-axis is period. On the right, the 98 minutes is orbital period of the NuSTAR satellite. And we found 12 minutes periodicities from the simultaneously detection from instrument A and B, but with a discrepancy about 0.8 minutes. So here, next slide, I'm going to show the details about these periodicities. The left panel is power spectrum and forward light curve detected from instrument A. And we can see from the power spectrum, the left peak is about 12.8 minutes. And the bottom is a forward light curve with this spin period. And on the right, it's about 12.08 minutes period with 99% significance. This is a forward light curve based on this period. As we already listened a lot to talks on Monday about the ultra-luminous X-ray pulsars. So if this spin period is indeed from the source itself, M33X8, it will be the longest spin period of the ultra-luminous X-ray pulsar so far. As in the current literature, we only have 9 or 8 known ultra-luminous X-ray pulsars, and the longest spin period is only about 30 seconds. So if this pulsar is if this source is an ultra-luminous pulsar, it will be very interesting as it has the longest spin period so far. So you might wondering, as we already heard a lot on Monday about with such long spin period, what does the magnetic field look like? So on Monday, we already saw there are different ways to calculate the mass accretion rate and the magnetic field. So here I just show one of the methods. So the first way, use the luminosity in the soft energy band is about 1.4 times 10 to 30 light erg per second within 0.3 to 10 eV. And with this first formula, we use the eta is the energy conversion efficiency for accretion onto a neutron star, and we can get the mass accretion rate. The second formula shows how we calculate magnetic field based on the mass accretion rate. If we assume the spin period we detected 725 seconds is equilibrium spin period, and we put in this formula, and the mass we use a standard neutron star mass about 1.4 solar mass and 10 kilometers radius. We can get the magnetic dipole moment. And here we get the magnetic field is about 4 times 10 to
People on Zoom now? Yeah, we are back. We are back, yeah. Go ahead.
Yeah, so if it's not otherwise, it will be in the higher spin period, and it should be at the end of the power spectrum. We can talk later. Okay. So we also estimate the spin period derivative. Based on this information, we found its spin period derivative is also very large, which is about 10 to -3. So then next we have also extract a counter rate for each source so that we can identify all the source detected by the NuSTAR and to classify the accretion states. For here, this is an example how we did that. So this is a PSF calibrate point source image for M33X8. On the left is a smoothed background subtracted image. And in the middle is a model. On the right is a radio between the data and the model. So first we use the initial estimate count rate from the DS9, which is about 0.1 counts per second. Then with this model, we get a failure counts about 0.2 counts per second. Use this same method, we have identified 28 sources with larger than 3 sigma significance, which is showing in this mosaic image, include 6 observations in 3 fields. So with these 28 sources, with this result, we can construct the NuSTAR diagnostic diagram as a color intensity or color diagram, as also showed by Dan. So first, this is the color intensity diagram. The x-axis is hardness ratio, which is calculated with counts in soft 4 to 6 keV, medium energy band 6 to 12, and hard energy band 12 to 25 keV. The y-axis is a counter rate in 4 to 25 keV. And the colored source are the sources in our own galaxy. The pink is a soft state black hole, and the green and blue is intermediate and hard state black holes. And the purple are the pulsars. So we can say there are about 4 sources are pulsars, and 8 sources lie in the hard state black hole, and the brightest source is M33X8. So we and the brightest source is M33X8 is an ultra-luminous X pulsar, and roughly 4 and 10 and 4 sources within the intermediate and the soft state of black holes, respectively. And in a similar fashion, this is a color diagram. The source distribution are consistent with the color intensity diagram. We can compare the source population with M33 as just discussed by Dan in the talk before me. And we can since M31 are dominated by low mass X barriers, M33 are dominated by high mass X barriers and more black holes. So this allows us to study different population in different galaxies with similar sensitivity because of their similar distance. And with a unique hardband from NuSTAR, we can build a luminosity function. So this is a cumulative luminosity function for the sources detected in M33 with larger than 1 sigma significance in the hard energy band 12 to 25 keV and with larger than 3 sigma significance in 4 to 25 keV, as shown in the blue line. And the red is we fitted with a parallel, as shown in the red line, with a slope as 2. The yellow is the luminosity function for AGN. So this can help us to study the demographics of the high mass X barriers in M33, help us to study the formation and evolution of the high mass X barriers as their dependence on the galaxy properties such as the stellar mass, star formation rate, and the local environment. So we have looked at the sources in M33 and we found some interesting periodicities in one observations with simultaneously detections of instrument A and B. And there are some discrepancy might be due to the instrument error. So we try to figure out the cause of the spin period. And we have identified 28 sources with larger than 3 sigma significance. And most of the sources overlap with the intermediate and the hard state black holes. And we have confirmed 6 new sources. And we use unique luminosity function in hard energy band to study the demographics of the population of the M33. Next, we would like to study the pulsars near the Galactic Center. And since this can use to with multi-wavelength observations and modeling, so we can test the GR, and we can also use millisecond pulsar to trace axion dark matter profile. Our survey will include the other wavelength band satellite, for example, Fermi's gamma ray space telescope and other radio telescope. For example, the 500-meter aperture spheric telescope fast in China. Thank you.
Questions?
About the pulsation search, have you tried to, well, besides the fact that you really should investigate if it's 8 times the orbital frequency, because it's very possible that it's actually a multiple of it. So that thing you should exclude it before going forward, probably. Look if it's really exactly 8 times the orbital period. One thing that you can do further is just to sum up all the events from the 2 detectors, because it makes the signal to noise ratio increase, right? So you might have a better detection and better determine the frequency. What happens there, why are they so different, is that the significance is quite low. So you actually, as Nazma was saying, you are the frequency itself is altered by the Poisson noise of the data. So if you sum up all the events and you calculate the same periodograms with the double of the events, you will see a better determination of the frequency. I mean, suggest to do that and see what happens. Anyway, nice talk.
Yeah. Thank you very much for your comments. Like we try to do the whole observation event list. So since we found like there are some peak, but it's not very strong, so we will do more analysis about to put all of them together. Yeah, we did try that. Thank you. That's a great suggestion.
I just have a quick question about the tiling of the observations. So it looked like you stacked 2 observations on the same, roughly the same area, and then spread that across the galaxy. Was that just to get the most exposure you could, as opposed to doing 6 observations to try to cover the most area of the galaxy? I guess that's my question. What was the strategy for how the observations were pointed?
I'm a bit lost about the question. You mean how did we do that? Or
Yeah, a little bit. Yeah, it looks like, am I right in saying that you had 6 total NuSTAR observations, but it looked like 2 sets of those observations were roughly the same pointing. And you did that 3 times to cover most of the galaxy. Is that right?
Yeah, so there are 6 observations, each 2 mostly overlap with each other. So you see 3 fields.
Yep.
So you mean how did we do that?
Well, I guess was the goal then to just get a more exposure by covering the same field twice?
Yeah, exactly. So get a higher signal to noise ratio. Yeah.
Okay. I just wondered if that was the goal or if it was like checking for variability or something like that. Okay. Okay.
Yeah.
Great. Thanks.
Yeah. Thank you for a great question. Yeah.
Let's thanks again to our speaker.
Thank you. Thank you.
Now it's time for Lehmer to explain us a deficit of high mass X-ray binaries in NGC 6552. So anyway.
All right, thank you very much. Okay, so yeah, I'm going to be talking about this galaxy NGC 7552, which is, as you will hopefully see, a quite interesting case. NGC 7552 is shown here in a Hubble image. The galaxy is a barred spiral galaxy that is at about 20 megaparsecs away. One quite interesting thing about it, it's a luminous infrared galaxy, so a lot of star formation activity. In the central region of the galaxy, most of the star formation is dominated by a circumnuclear ring of star formation, as you can see there from dust emission traced by this Gemini observation. Okay, and this is going to be work that was led by, or is currently being led by my graduate student, Lacey West, pictured here. And so hopefully I'm doing her work justice. All right, so I'm going to start just by, actually, at this point, it'll be a little bit of a recap, right? So X-ray emission from normal galaxies. A lot of what we know about the X-ray emission from galaxies comes from, observations where we can resolve the galaxy and look at the components individually. And that's usually galaxies at distances of less than about 30 megaparsecs or so, and normally observations with Chandra. So this is an observation of M83, which is at about 4.5 megaparsecs or so. And what you see in here is emission coming from a variety of different astrophysical sources. Diffuse emission is shown here at kind of, tracing out the spiral arms, and see a bit of it in the central regions of the galaxy. That's shown in red. That's soft emission that you see there. But then dominating the hard emission, as Dan and June have already told us, is X-ray binary populations. And so when we see the X-ray binary populations kind of coincident with star forming regions, or where you have a lot of star forming activity, it's likely that those are high mass X-ray binaries where the donor stars are of high mass. However, in most galaxies, you're going to have contributions from older populations of low mass X-ray binaries, including donor stars that are evolved low mass stars. So when kind of characterizing the emission of X-ray binary populations with respect to the galaxy properties, a game that we often play is, we take galaxies that we can observe and resolve, take out the point source populations, measure X-ray
luminosity functions or total X-ray emission. And then we try and look for correlations with properties like stellar mass, star formation rate, and now several others are starting to become relevant as we show. So this is a sample of galaxies. There's 38 galaxies within about 30 megaparsecs, where we have nice Chandra observations. We can see the point sources, and then we can, sort of add them up and calculate the total luminosity. We also then have good estimates of the galaxy properties themselves by multi-wavelength data. And one of the things that we kind of expect is that the X-ray power output of a given population or of galaxies in general is related to the sum of low mass X-ray binaries and high mass X-ray binaries, which scale with stellar mass and star formation rate. And so you might see a diagram like the one that I show up here from time to time, where you take this equation, divide it by star formation rate, and you just expect basically that the X-ray luminosity per star formation rate will have this 1 over star formation rate per stellar mass or specific star formation rate relation, as is shown here in this equation. And then, we can fit this for samples of galaxies and pull out these constants of proportionality, these alpha and betas. Okay, so here, the low mass X-ray binary signature on this is shown here in this kind of red line, and then the high mass X-ray binaries are tracing star formation rates, so that should just be a constant line there shown in blue. All right, and so the idea then is that if you have very high star formation rate, very active star forming galaxies, that those will be dominated by high mass X-ray binaries. However, when we go and look at galaxy samples that are further away, where we can't really resolve the populations as well as we can at distances less than 30 megaparsecs, we're able to look at galaxy samples there that have extreme star formation rates, up above 10 solar masses per year or so. And these are luminous infrared galaxies and ultraluminous infrared galaxies, the most kind of star-forming powerful things in the relatively local universe. And what we would expect there is that the X-ray power output from those galaxies would be dominated by high mass X-ray binary populations. They should follow these correlations quite nicely and everything. But one of the things that's sort of challenging here is that when we look at these galaxy samples and X-rays, we're not able to resolve them, and they end up being quite faint. All right, so we don't have very good spectra of X-ray spectra of many of these. Nonetheless, we can put these on our sort of correlation diagram, as I had shown before. This is the same kind of diagram, but now in kind of with this green and red are the luminous infrared galaxies and ultraluminous infrared galaxies. And then the black is showing kind of our best correlation. And one of the things that is noted is that several galaxies in this population of extreme star-forming galaxies have an X-ray deficit that's quite significant, factors of 3 to about 10 or so, as you can see from this kind of circled region in here. Sorry, I can't really point very well, but I'd like to. All right, so anyway, one of the questions then has been, well, what's causing that deficit? Why are we missing high mass X-ray binaries in these populations? And when we first discovered this result, one of the ideas was that, or the most likely scenario to us was that you have a lot of obscuration that's just basically blocking out a lot of the population. It's just buried underneath a large column density. LIRGs and ultraluminous infrared galaxies are, a lot of them tend to be in mergers, so you have a lot of gas and dust, and so that seemed to be a plausible explanation. All right, but still, there are other ideas that we should at least consider and study in detail, and the other fall into the category of maybe those high mass X-ray binaries really just aren't there, and so I'll talk about that. But first of all, if you're going to obscure a population of X-ray binaries, how much obscuration do you need to actually get deficits on the order of a factor of 10 or so? Well, typically in galaxies, you do have some obscuration to X-ray binaries on the order of a few times 10 to the 21. Column densities on an order of a few times 10 to the 21 is typical. And so to get the observed luminosity down to factors of 10 lower, you need an order of magnitude or 1.5 orders of magnitude more, or excuse me, 2 orders of magnitude or 2.5 orders of magnitude more obscuration to get down to those levels. So that is quite extreme. So in the missing scenario, okay, this has actually become more relevant recently. One idea is that, maybe in the regions of these luminous infrared galaxies, the populations of stars that form are forming in pretty extremely high metallicity environments. Lately, we've discovered an anti-correlation between the X-ray power output per star formation rate versus metallicity, such that at higher metallicities, you actually get less power output from X-ray binary populations. And so potentially these LIRGs that are way down below the typical relation could just be due to having very high metallicity. Another possibility that we're entertaining is that maybe HMXBs have not had time to form. Okay, so in this diagram, this is a theoretical model of X-ray binary formation as a function of time. And certainly, of course, you have to evolve the first black holes in order to produce X-ray binaries in the first place. But you can turn on star formation and then wait a little bit before you get those. And so maybe what we're seeing in these populations is actually a delay. Okay, and so here's where NGC 7552 comes in. This is the nearest LIRG that has one of these noted deficits in the X-ray emission. Of course, I've said